Hello everybody, welcome to the stream. I have to find a better way of doing this transition because it's so lame right now. Hello Yo-san. Welcome to the stream everybody. Hello Gu Hursi. Welcome. That's cool. Yeah, we're gonna continue today with the compiler. Hello, I almost can't see your name. It's blue on gray. Defense. Hello. Welcome. Let me just get rid of this background. That was the wrong one. There we go. Is that the right one? I think so. I think my windows are messed up. Huh, that's strange. I always turn off the secondary monitors when I play Fortnite and stuff like that. So maybe that's a problem. Yes, okay, this is good. Thank you for following. Thank you. I'm gonna place that on top. Hello Giuseppe, welcome to the stream. It sounds like a cool project what you had with Arduino. I like working with that kind of stuff, so that sounds really cool. Yeah, so how long did we stream for yesterday? I think we streamed for like 10 hours. Yeah, it was quite a long stream. But for those who didn't see the whole stream, we're now able to compile expressions, which is cool. So I'm gonna give you an example. So this can we compile now? So I will show you. If I type make, it is gonna give me 2, 3, 4. Not that one. And if I do this, it is gonna give me... Yeah, you can't really type this because it's equal and it's like relational expression, so it doesn't matter. But in fact, this evaluates to true or maybe false, and then you just add this factor. So if I had like bigger, it will give me 1. It would give me... I don't know what this evaluates to. Let's try this. It's giving me error 5. So if I do this is less than 5, it should give me 0, which it does. And if this is less than... if this is bigger than 5, or if this is bigger or equal to 5, we have to do equal as well. Then it's gonna give me 1. And it works. So basically whatever you can think of which has these operators can we compile now. So that's really cool. What is this compiler compiling? It's compiling currently just this. It's gonna be a really cool stream today. We're gonna add in... what are we gonna add first? Like function calls, functions, identifiers, probably pointers. That is not so difficult. It sounds more difficult than it actually is. Types, probably. If statements and like conditional control flow statements. That's super easy. Also, I want to, because now it's generating this assembly code here. Which is actually really bad. But that's fine, I'm not gonna care about that. But I also want to have, like, if you're commenting in the code, if you're, for example, doing something like this, I want this to actually be placed in the output file as well, like as a comment here, so you kind of know what's going on. So we have to make the Lexer support parsing, like parsing comments and identifiers. So that's going to be the first thing. Do you archive the videos on YouTube or so? Not currently, because this is my second attempt on writing a compiler. So I'm not that like stable on this. But we're gonna rewrite this in our own language, and then I will probably make a series on that. Yes. So this is cool. This is actually really cool. And also yesterday we did this tree printing. I don't know if this makes sense, but it is basically, let's get up this again. It is basically printing the top level structure. So it will basically print how do you make this one. So you can see that it's, in order to compile this one, it needs to do an relational expression between this binary and this number. So that's what you see here. And all the precedent stuff is being taken care of. So in order to evaluate this binary, you have to recurse down and do this one plus this one. And then you recurse down all the way to the final point. So you basically start by doing 4 times 2 and 2 plus 1, which is in here and here. Yeah, so that's basically what you see. We're going to continue just adding more stuff today, I think. Yeah, that's the plan. But actually, before we do that, we're going to clean up the code from yesterday because that's a mess. So I'm just going to clean up a little bit. It's not going to take that long time. Do some commenting, and I'm just going to explain how it works because it's not that much. Yes. First of all, I want to disable, get rid of this exit statements. I still wanted to exit, but I wanted to describe what's going on. Yeah. So top level, we have the Lexer, which is the first stage. It's not really a stage, it's so tiny, but it is splitting this complex statement up into different tokens. So this parenthesis will be a token, the number will be a token. Even if I would have said like something in hexadecimal, this will get parsed, and I'm basically getting a number from that one, just a regular number. So it doesn't matter for the compiler if we do this or if I do just this. It is still a number. So that's the Lexer. It just splits this up, and we have this kind of API. Which we're using. So before everything, we have to call new Lexer, and we're giving it a source file. So what you see here is being loaded into memory, and we're giving that file to the Lexer. So this will contain that entire file in memory for the entire compilation. So therefore we don't need to copy anything because we can just keep pointers to that specific file, which is very nice. And we keep the file name. I don't think we use that for now. Maybe we do, maybe we don't. Thank you for following. Welcome, welcome. Okay, so next token, this is basically the API. This is every function we can call from the Lexer. So we have a token stream, and we have 2 pointers. Let me make some more space here. So we have the file pointer. I'm gonna mark it like this, and then we have the token pointer, and then it's the actual file here. Oh, that's stupid. Okay, I'm gonna mark it with this. So this is where the token is pointing. This is where the actual Lexer is. So when the Lexer this main like thing works, it's going to move this file pointer, and it's going to get the O, K, E, N, and so on. So this is going to move. The token pointer is going to point to the start of each token. You can just think of it as that. So when I do next token, I will first instruct the Lexer to actually process a new token. So this is going to move over there. Actually, it's going to move at the very end of the word. So like around there. And then we're going to move the token pointer so that this is pointing to the beginning of the token. And then we return this pointer here. Is that better? So that's the next token. This is just getting the new one. Peak token. This is not moving the token pointer. This is forcing the Lexer to process a number of tokens here. And then we return one of these tokens here. But we don't move this one. That's the thing. So if I now call current token after this, I will still get this one. So I can peak a number of tokens without having to move the Lexer. So if I for example need to check if, like let's make a nice example. If you have some kind of declaration and you want to know if the next token is some kind of type, and if it is, you have to do something. If it's not, you have to undo. Then you can use peak token. Or you can just use next token and then you can undo. We also have functions for that. In some occasions that's better because you don't need to do next token all the time. Yeah, peak token, this is returning the current one. This is returning the current one and getting the next one. So basically it is doing, it is processing the next one and it's moving this pointer, but it is returning this token here. So the next time I can just get current and I'm gonna get this one. Expect, that is returning the next one under the condition that that's a specific token. And if it is, I'm gonna return it, otherwise I'm gonna have an error. And this is probably not implemented. Yeah, it's not implemented. We can implement that. And skip token is what we're usually doing. And that is basically checking that this token here is, or the current token is of a certain kind. And if it is, it moves to the next one and returns the next one. So this is the one we're usually using. Okay. So let's implement this expect token first. So this is gonna, this is going to check that the next one, we're not caring about the current one. So we're gonna get the next token, and we're gonna check that this is of a certain kind. So if token kind is not equal to kind, we're gonna return an error. So here, this is gonna return an error. Possibly I would like this to print what it's actually expecting. Because I'm gonna be expecting something here. Okay, so I'm actually gonna make a table. Yeah, I'm gonna make a table. Thank you for following, welcome. So just before we start, the token is what we're returning all the time. So each of these things here are tokens. And we store the kind, which is what kind of token it is. So we can either have a number, and we're also gonna add token identifier. And we have all these like plus, minus, multiplication, equal, and so on. And we also have token none. This is no token is processed, so it doesn't really recognize the token. And we have end of file. So this is the kind, And then we have the string name, and this is a reference into the file. So this is pointing into the file where we can find that token, and it also has a size. So that's how I can print these things. I'm probably not printing using this, but if I would print this string, I would get exactly the same as this. And then we store the pointer to the lexer, and the reason is we can just write that. And the reason for this is that we can it is so we can get the start location of the source file. Okay, so the reason for this is that we can get the start location because sometimes we need to backtrack. So we're getting, for example, like we have a pointer right here, and we are gonna print, for example, the previous 3 lines. So we can't really just go back 3 lines because it's stopping here. So because we need to know that location, we need to contain that pointer. And you keep in the line number and the column number, which is nice for the printing. And if this is a number, I'm storing the number here. If this is something else, like an identifier, something not a number, I'm gonna store it here. So that's that. The lexer is just containing the file. It has a cursor, so it knows where in the file it's currently at. It has line, column number, and it has this token buffer. So this makes us, or this allows us to like peek a number of tokens ahead and go back again after. So we can currently peek 10 tokens or undo 10 tokens. And this can just be changed later. We can even get rid of this. It depends on like how much we have to peek. Yeah. So I'm gonna do this. Okay, so I want to print something. If I'm expecting a token and doesn't get it, I'm gonna print what I'm expecting. So this token kind, which is defined as this enum, I'm gonna print that. Okay, so I'm gonna make a token kind. This is an array. And we have none, number. This is just so I can print a string representation of these. I probably should take them after each other, because then it's easier to add more stuff later. Plus, minus, multiplication, division. Is this gonna be a C compiler? It's gonna be like for a language which looks kind of like C. It is not gonna be exactly equal, but it's gonna have like a lot of the same features. Did you see what I did now? I typed equal, and I found it in the sentence as well. Less equal. Yeah, it's gonna be a nice language, I think. Greater equal close parenthesis, open, curly, close curly, semicolon, and we don't get the last one. Wait a second here. I'm gonna say a number. This is never gonna happen. None is never gonna happen. Expecting a number. Expecting plus. I'm gonna do this instead because it's easier to understand. Open parenthesis, close parenthesis, and semicolon. Okay, so that's the only thing we have now. And this error token, does that take in some parameters? Because I wanted to take in some parameters. This only takes in a message. So we're gonna take in ... Clone. Oh, I guess it was this one. I actually I actually saw that that was a typo, but thank you. Multiplication. Yeah, okay. I'm typing so bad. Like unusual words, I'm bad at typing. If it's like statement, it's really fast. Yeah, so we're gonna include std_arg, and this we're gonna use for getting a number of arguments on the command line. And we're gonna print it here, here, print a message. So here I want to actually print not just a message, I want to print the message as a formatted string, including these arguments here. So what I'm gonna do, I'm gonna make a static char buffer, and I want to print this message including the formatting to this buffer. So you're gonna do va start, no, we're gonna do va list, va start. Okay, so here we're just making some kind of object that can contain these arguments here. And we're saying that this argument is gonna start after the data, which is supposed to be a message. So we're telling the argument before the ... And you end it here. And do I use size for something else? No. Okay, so we're gonna do vsn. Is it this one? I keep forgetting what this is. Strict. I can probably see what I was doing other places. So I want to print to this buffer. The buffer is this big. And the formatting is the message. And we're going to give it the arguments. So instead of just printing the message, I want to print the buffer, but I also want to print a number of bytes. So we're going to print size number of bytes from this buffer. So we're returning how many bytes we have printed here. So now I should be able to call it like this instead. Like this, and we need, of course, the standard arg for doing this. Okay, so this is the message. I'm gonna say expecting this. We can just say this, but got that. So that will be the token kind. We probably want to assert that both the token kind and the kind here is actually valid. Is lower than token count tokens. It says count tokens here. I don't like that name. Token kind count. That's better. And we're gonna assert that kind is also less than token kind count. Oh, just no autocomplete. So I'm gonna say token kind, which is this buffer here. Oh, thank you. Someone is awake in the chat. That's nice. Guess I have to take myself some more coffee. That's bad. So stupid mistakes there. So we're expecting this kind, but we're getting the token kind. Because this will actually print a more nice error message. And if this doesn't happen, which it really should not happen, that's an compiler error, it's going to return this new token. And the same thing here, I want to be a little bit more verbose here. So this is a different kind of error. Yeah, we can say it's the same. It's the same error. And let's do this here again. All right. So those are just printing stuff. So let's try and see if that works. So I'm gonna go into the parser, and this expression statement, which is sort of a line, is gonna end with a semicolon. So let's change this to a close parenthesis and see what it does. Fuck. Open curly. Didn't I copy this? I didn't mean to do that. Oh, that's probably why the error, that autocomplete didn't work. Because this still says the same. Token kind count. So there we have it. We're expecting a something, but got a different thing. That isn't really right. Expecting less equal, but got something else. Wait a second, is there something 1, 2, 3, 4, 5, 6, 7, 8? No, 5, 6. 1, 2, 3, 4, 5, 6. That is supposed to be correct. This is parsing an expression statement. That is supposed to be really simple. So now it works. If we're getting this. I want to see if this is happening 2 times. I'm not getting it once. Wait a second, parser lexer skip token semicolon. I don't understand this because the token is supposed to be somewhere else. Let's print a token. Let's just print it. So it's a semicolon. And if I, for example, ask for something else, it is still a semicolon, expecting that, but got something else. So it's printing the wrong thing. And it's also giving me the wrong index. So that's why I'm like, that's the problem. Skip token. Oh, this is supposed to be an S though. So it's saying expecting a closing parenthesis, but got this one. So it actually got this token here. So the question is why that token is wrong. So I'm just going to print a token here. Token name size token name text. So the token is here. So what I'm giving to this error function is the right token. So I just wonder why I'm getting this column here. Also, I want to try something. I want to do a for loop because I want to check if the indentation is right. Let's do this. So I'm just going to print that number of column number of times. And then we print a new line. So that is only going here. So I'm starting to think I'm not changing the column number. So this is probably an error in the lexer when I move the lexer pointer right here. Because I'm increasing the column number there. Because this is certainly not working. I should get that one. I'm calling advanced lexer. As long as this is a white space, I'm just calling advanced lexer. And if this is 0, I'm returning. That's fine. And you increase it once. And this will only happen if we have a new line. And that, like, if this is even happening, I'm gonna reset the line, the column number. Oh, wait a second. I know what the problem is. The problem is here in the skip punctuation. Because this is manually increasing this lexer pointer. That's a problem, really. So I think either we can just call advanced lexer, but that's a bit slow because we have already checked that it doesn't do anything wrong. There isn't like a new line or something else. So I think we're just gonna increase this column number automatically. skip count. So now we're getting the right one. So this is telling us that this is the error. it's almost invisible because of the since it's just one letter. That's a parser. So now we can just delete this. It is working as expected. So we say like expecting a opening parenthesis but got a semicolon. That's good. Yeah, and it prints a line number as well. So I'm happy with these two functions there. I can just ignore this for now. Okay, so let's start actually making something new. First of all, I want the Lexer to be able to handle words and comments. Yeah, so I'm gonna be able to lex comments and words. And we're gonna support nesting of comments, like multi-line nesting, because that's very neat. Yeah. So the main function here is process next token. This is gonna actually move the pointer and try to process a new one. So we start by just skipping the white spaces. So in case the Lexer is, for example, here, it's gonna skip like new line and all these spaces in there. And it's gonna skip all these spaces in there, and it's gonna stop here. So after this skip white spaces, it's at the start of the token we want to process. And then we just save the line and like information about the location. And we check if the pointer is 0, in which this is the end of the file, because it's always terminating with a 0. And then we check if this is a number, and we're gonna add 2 more functions here. We're gonna check if this is a comment. Yeah. So if C I'm actually gonna, you know what? I'm going to language. Thank you for following. Welcome. I'm going to remove these. Remove. And we're gonna switch keywords. Dang it, stupid fucking keyboard. I don't like it. Alright. Okay. I hope this is gonna go faster. Thank you for following, welcome. Okay, so we're checking if this is it might be a little bit slow now, and it's gonna probably be fine in like 5 minutes. The first thing we're checking if is the current one is a forward slash, and the Lexer cursor a 1, which is the next one. Like this is the first character, this is the next character, is the same. So if both of these are valid, this is a comment. And then we're gonna check if this is a valid identifier. I'm just gonna say is valid letter. So as far as I know, C doesn't allow to have a number in the beginning of a line, which makes sense because then it's going to be misinterpreted as a number. So we're just going to check if this is a valid letter, and we're going to implement that function. So if this is a valid letter, we're going to return if C, let's do, what is a valid letter? Yeah, we're gonna just do it in if statements. So if C is equal to underscore return, you know what, we're just gonna do it in one single statement here. Return true if C is equal to underscore where's that one? There we go. Or it's a valid capital or non-capital letter. We have to do it like this. So if C is equal to underscore return true, it's gonna be better in like 5 minutes, by the way. And if this is not a valid letter, we're gonna transform this letter to uppercase. No, to lowercase. Yeah, we're gonna do this. So this is transforming from uppercase to lowercase. And then we're just checking if the C is between A and C. So if this is between that, you're just returning true. Return false. Start with what do you mean? Start with, yeah, because I need to convert it to lowercase, because this is a little bit faster than checking both, I think. So this is checking if it's a valid letter. Okay, so if it's a valid letter, we're gonna parse identifier. And we're gonna always give it a lexer and a token we're gonna change. So this function is getting the token, and we're just handing that over to the next function, and it's gonna return that identifier in this token here. Parse identifier, and this is gonna parse a comment. Parse comment and parse identifier. Let's make those. Let's have it down here. That's supposed to be a pointer. Now the speed is going to go up a little bit at least. That's supposed to be an identifier, which is just a name if you don't know that. This is just a name. Yeah. Oh. Why don't you use regex? Because regex are much more complicated, to be honest. It's much more complicated and I don't need it. This is gonna perfectly find lex 100,000 lines in 5 milliseconds. And that's like 1% of the compile time. So it doesn't matter. And this is much more clean. This is going to be in below 400 lines. Hello, Rockat. Welcome to the stream. But I did regex. I think we made a regex parser on the stream once. So like a table parser, generate the table. And it's just a mess, really. Parse identifier, we're going to continue with this as long as we know the first letter is valid. So this is just going to have like a loop here. But first, we're going to save the start location. So the name size, no, the name text is equal to the lexer cursor. So this is just saving where the token starts. And then we're going to compute the size afterwards. So name size is equal to Lexer cursor minus token name text. So this is just computing the difference in where the token cursor is. Thank you for following. We're working on a compiler, so now we're gonna try to support identifiers and function calls and stuff like that. That's gonna be cool. So we're gonna make a while loop. We're gonna just wait until we're getting something that is not a valid name, which is a number or a space, probably. So while is number, I'm gonna say the first one. Char C is equal to Lexer cursor of 0. That's the first one. And we're gonna iterate until, like, while this is a number, or while this is a valid letter. And so this contains the underscores as well. So we can write any name which has numbers and has valid letters. I don't think I want to add anything more here. So just this. And while this is happening, we're gonna advance the Lexer. This is just moving the pointer one step. And we need to keep it in a function because we need to update these line numbers and column numbers as well. So that's why we have a function for it. Hey, welcome to the stream. Yeah, so this is just waiting. So currently the cursor is pointing to something that is not a valid name. I'm just saving that. We also have to make some token kind for the identifier. Token identifier. And also, this is like this is after number. So we're gonna go down here, after number, identifier. So expecting an identifier, for example. Yeah, we're gonna set the token type. Identifier. Do we need anything more? I don't think so. I think that's gonna handle identifiers. If we have a comment, we're gonna just do a while loop. So now I can try to, probably we're gonna have a parser error, but that's fine. We're gonna write some kind of like test, and we don't support this one yet. So the Lexer should handle that. So after the Lexer, we're just gonna do while loop. We're gonna say token next token, we're gonna give it the Lexer. So this is gonna return a new token. And if the token kind equals token end of file, then we're breaking. Otherwise, we're just printing that we have a new token, and what a string is, like what is its representation. And that will be token size and token name text. And yeah, so let's try. Undefined reference to printf. Okay, this is hanging, so probably we're getting the comments. Do I have a commentary? I don't think so. So this is happening. No, we're getting a token there. Is letter parse identifier. While, or okay. So this is the number and this is a valid letter. This is gonna advance Elixir. Maybe this is overflowing or something. It is still in, is it still in here? Yes, it's still in there. I don't know why it's still in there. Parse identifier. Oh, we're still using the C. We have to update the C. Parse character doesn't check if a character is already lowercase. I don't have a parse character. But this valid letter checks if that's a underscore or an uppercase or lowercase. And this is actually returning the next char, so I can just say C is equal to that, and it's gonna work perfectly. And there we go. So we're getting this token stream, which is what we want. So this is because we're starting to parse, and it doesn't work. But you see we are getting all this data here. This is wrong. We should not be getting that one. And this is also wrong. So it seems like this is one step ahead. Because I guess this is a space. Like we're at the current location. Let's print the size. So the size is 5. 1, 2, 3, 4, 5. I don't understand why the size is 5. Why would the size be 5? Let's print the character before and after. So the first one is T and the next one is something else. So we're taking Alright, so the first one it's T and is getting that one. So 1, 2, 3, 4. I don't understand why that should be wrong. Cursor minus name text. Yeah, I need to update C. His editor theme will happen. Yeah, probably. Maybe because of the \0. No. Or that is strange. Let me do this instead. So we're updating the size here, but I'm gonna say Elixir cursor of 0. C is equal to that. And then I'm gonna do the same with token name text. So just printing those there instead. So token test size is 5. Yes, we're getting nothing there. Wait a second, is that a number? It's between those. I'm just gonna print false error. I'm gonna print the letter. It's printing false on that. TT. Like, what the fuck is going on? I can just take -1 because I think that's gonna work, but I just doesn't know why. I just doesn't know why. Okay, we have to figure this out. This is getting after. I feel so stupid now. Before. For some reason I'm getting after is equal to nothing. After is supposed to be equal to semicolon here. Okay, so this is while this is a valid letter. I'm gonna print a letter. If this yields a semicolon, we know where the error is. Stupid thing. It doesn't yield a semicolon at all. Maybe this is giving the wrong char. Lexer line. Yeah, Lexer cursor ++. But we're still not updating that, so that's a problem. We're returning the wrong value here. So what I have to do, I have to return the actual Lexer cursor 0, and then it's gonna work. Okay. Stupid me. Dang it. That should not take that much time, to be honest. I guess now we have identifiers. Let's do comments as well. And we're gonna support nesting, so we have to keep some kind of track on the nesting level. Yeah, I could add -1, but apparently they were a different error. Yeah, the last one was right. Okay, parse the comments. How are we gonna parse the comments? We already know that the 2 first characters are some kind of comment. So we either have a single line or a double line. We know the 2 first characters are correct. We already know this, so we're gonna check the next one. Parse the comments. So if we can probably just advance the Lexer 2 points. Advanced Lexer. I'm gonna make a new function. Advanced Lexer width. Or width. You said width or width? Advanced Lexer width. It's gonna take in the Lexer pointer and it's gonna advance it with a number. So counts. And this is just gonna do 4. Actually, we just use a while loop here. So while count minus minus, we advance one step. So then I have a function for advancing with a number of tokens. So I could probably just use that here. But this is gonna work, that's fine. Advanced Lexer with Lexer 2. We're gonna skip the two first ones. And if the Lexer cursor of 0 is, I'm gonna have a different commenting style because I want to be able to, I don't like this commenting style here. That's stupid. That's not stupid, but I don't like it. So we're gonna do this. There were actually one on the stream who suggested this. So thanks to that guy. This looks much more clean, I think. So this is gonna be for multi-line comments. So we want to check if this character here is an opening parenthesis. If that is equal to open parenthesis, multi-line. And also I'm gonna have a static variable here. U32 nesting level. Is that a nice name? No, this doesn't need to be static. I can just mark it as the nesting level. So this is starting with 0. Each time it goes into a multi-line comment, it's going to increase this nesting level. There we go, and then we have a while loop. We're going to wait for something to happen. So while let's just use 1 here, and I'm gonna break manually. Why not just not? That's a good question. So why can't we just do this? It makes it harder to do errors though. Because if I forget these, I'm gonna get a valid multi-line comment, for example, here. And then the user might get a compiler warning here, and he doesn't know why, because the error is actually here. So I guess it is better to have it like this, or this. This is gonna be fine because this is the same as a comment. I don't know. What do you think? Should we do this, or it's better to C language compile? It's something like, it's my own language, but it's gonna be very similar to C. Let's just stick with that for now. So we're gonna wait for something to happen. We're gonna check if we have a 2 consecutive opening, not opening, but 2 consecutive slashes. So if token if Lexer cursor of 0 equals this, and the Lexer cursor, oops, a 1, so we're going to check the next one as well, equals this, then we either have a new sub multi-line comment, or we have the ending tag. So we're going to check the next one. And if we know this is correct, we don't need to check for 0, because it is first going to check this one, then we know this is not 0. And if this is correct, we know this second one is not 0. So we don't need to check for the 0 termination here. If that is equal to 2, yeah, we can't advance the Lexer at this point, because maybe the user wants to do like 1, 2, 3 and the starting comment there. or basically this then. So this is the ending, these three, and it has one before. So we can't really check this one and then advance the Lexer 2 points, because this is not valid then. So if that is opening parenthesis, else if Lexer cursor 2 is equal to closing parenthesis, let's just use a variable here. Char c is equal to Lexer cursor of 2. If c is equal to 2, do something, and if c is equal to closing parenthesis, do something else. So this will just increase the nesting level here. So I'm going to say nesting level plus plus, and here nesting level minus minus. And in the beginning, this is going to be 1. So if it receives this sequence here, this is going to be 0 again. So after this statement, if nesting level is 0, we break. And then we probably need to, because we have this statement here, so we need to advance the Lexer with 3 places. Oops, forgot a parenthesis there. Thank you for following, by the way. Comment. I don't like that one. Did you study at university or self-learn? I studied at the university, but you don't learn this at university. Even though I have a subject called compiler construction. You would expect to learn something about this at that subject, but you don't, in my opinion. Yeah, let's move this down here. This is only going to happen if we have a multi-line comments. Oh, and let's just set this to 1 in the beginning. We can get rid of this. So nesting level is 1. And you wait for this sequence. If the next one is an opening, you increase the nesting level. If it's a closing, you decrease the nesting level. If the nesting level is 0, you just skip those that sequence and you break. So you break down here, and then we have to set. Should we have a different comment for multiline and for regular comment? I think so. I think we're gonna have a different token for both. We need to check for that. I think we're only gonna have one single token for both. So it doesn't matter if it's a multi-line or a single line. So comments. After identifier, we're never gonna expect a comment, but I probably should add it here as well. This is never gonna happen though. You're never gonna expect a comment. We could possibly add that, so if after each single statement you have to use a comment, otherwise it's not going to compile. Can be like a compiler feature. Yeah, so we have to set that the token kind is going to be token comment, and a token. We're going to set the size as well, but that probably doesn't matter. So we're going to save the size at the very beginning here. By the way, we're not going to skip this, because we still need to detect the sequence. So this is just, it's a little bit more overhead, but it makes the code simpler. Or no, in fact, we're still gonna have it like this. Yeah, it's right. Before this, we're gonna save the start location. Lexer cursor. At the very end, we're gonna say token name size is equal to token minus token name text. This is just updating the length. So we don't need to do that here. We just said that this is a comment. And if this is not the case, it's a single line comment. So this is a single line. And we're just gonna set the token kind equal token. Well, both are comments. Actually, we don't differentiate between those. Token comments. Yeah, sounds like university. Don't learn shit. Yeah, that's right. Totally right. What kind of parser are you making? This is a recursive decent parser. I don't know if I'm pronouncing the word decent correct. Decent. Decent, probably. Yeah. Cursor sees only the current and next character. The cursor is a pointer to the character in the file where the lexer is at. So it can be, that's just an array. You can look ahead as many characters as you want, but if this number is too big, you're gonna get out of the range and probably get a segmentation fault. Yeah, that is right. I feel like using goto is the perfect candidate for handling parse and syntax errors in a compiler that is recursive. We're not going to use goto in this case, in our parser. Goto is probably if we need. But goto is very nice for like having, if you want to do some cleanup after a function, goto is a really nice keyword. This language is not going to have a goto keyword, we're going to have defer. So if I, for example, open, if I like the token, token is equal to new token or something, I can say defer free token, or I can say defer free token here. So this is just going to happen after this function returns. So if I, for example, return right here, this is going to happen before I actually return. So that basically eliminates the use for goto. So I'm not going to add that. Will this work? Yeah, that will work. That will work. That is correct. So here we're just gonna wait for the new line, which is either, yeah, we're gonna wait for a return character, and then we're gonna check if the next one is a new line. If that is not a new line, we're gonna just skip it. And if it is a new line, we're gonna skip the new line, if that makes sense. So character is equal to lexer cursor of 0, and yes. So while c is not equal to return, and c is not equal to a new line, we're gonna just update this. So lexer cursor of 0. So at the very end here, c is either the r or the n, which is a new line. It doesn't really matter. We're gonna say the start location there. So now c is pointing to either the r or the new line. So here I want to update the token name size, because that's going to be a little bit different depending on the comment type here. Do I want the actual comment to be? I don't know. I can take that later. Yeah, okay, let's take this up here. Because that's gonna save the name size there. That's gonna be including the last closing parenthesis. This is gonna save the name in a different manner. This is gonna be -1, and it's gonna happen here. And then you're gonna check if C equals R. And no, we don't need to do that. This is gonna be handled by something else. The advanced lexer will actually handle that. So we just need to do it like this. So we're not gonna skip the new line. That's gonna be skipped by something else. Okay, so I think that's good. And once again, we're just gonna do this. And advanced lexer. Okay, I think that will handle every single comment. And this is not supposed to be -1. Yeah, let's see if it's working. So I have some comment here. It is stopping somewhere. I think it's stopping here. We're not advancing the lexer. So after each iteration, we have to advance the lexer. There we go. So we have the token, which is the comment, and it's printing the entire commentary. I think this is right as well. Let's see if we can nest comments into each other. So if I have like a comment here, and I'm placing this at the very end, this entire thing should be a comment. This is the first one, this is the second one. And I have a segmentation fault. That's not good. I don't know where that segmentation fault is. This is getting the right thing though. And token is new. This is probably from the parser. Or maybe I'm printing something and I'm not allowed to. I think I'm printing something and that doesn't exist yet. Because this is while, if I print done here, I think it's gonna be done. So the error is happening in the parse statement. It is not printing anything, so let's eliminate the parser. So done, the error is in the parser. If token kind is equal to open curly. Make arrive from instead of go to. Jumping code is defined by the destination rather than the origin. Arrive from. Yeah, that's better. I like that much better. That is super easy to read. Fun idea. Yeah. No, I'm not gonna have go to at all. But that's actually an interesting idea. But I'm not sure that's gonna be better to read though. Like go to in general is bad, I think. Yeah, it's not in the x86 output. It's in the or I don't think it is. because it's saying done here. So it's in here somewhere. And we're getting the current token. Because we're not getting anything. Print the token. Maybe we're getting end of file here. I don't know why I wrote end of file. But this basically doesn't print the token. So this is certainly not right. An expression statement. This will make a new expression. It will actually call the expression statement. And this will parse a unary expression. Okay, so we're actually assuming we have something valid. So this is not happening. We're down to parse primary expression. This is the issue. It's consuming a token that doesn't exist. So it's getting auto. That's the segmentation fault. Yeah. So parse expression statements. Parse compound statements. We're gonna check if this is not the end of file. Just return. Should it return 0? Yes, probably because it can't parse a statement. So I'm gonna return 0. And we have to check what we're getting from this. So that's the segmentation fault. This is something else. This is the program running, I think. It's in the generate statement, because now this is a null statement. So that will trigger, yeah. I guess that's fine. We can just handle that later. We know what's going on though. But it handles the comments correctly. Let's try finally with a single line comments. Just see if we can see if that works. Insertion failed. I hope this is my mouse. Yeah, give me 2 seconds. The mouse has doesn't have more power. There we go. I have to use my Fortnite mouse. I actually don't like to use my Fortnite mouse because I don't want to break it. Not that I'm gonna break my mouse, but yeah. Okay, that's fine. Yeah, empty block. It should be able to parse an empty block. It should be able to do this. Wait a second, that's not really... it should parse a statement here. Parse statements. Yeah, I'm gonna take it later. This works. So we're getting this as a comment and it gives us the entire line. So comments are working and identifiers are working. So we can have identifiers. So let me think what I'm gonna do next. We want to add support for functions. Yes, functions. Can make it a little bit smaller. I can't read this. Is this fine? I can probably make it a little bit bigger. Yeah, that's good. Okay. Yes. Okay. So let me just quickly recap how this is working. Like the entry points. So when we're calling this function, we're parsing an expression. We're parsing a statement. And a statement is either a compound statement or it might be an expression statement. So this is a compound statement, and this is an expression statement, which has a semicolon at the very end. And you can also have if statements and so on. So that's the statement function. This is the thing which parses the entire thing per now. And we're getting the current token. That's going to be the first one. And we're checking if that's the end of the file. And we check if this is an open curly. If this is an open curly, we parse a compound statement. And this will check for, it will skip the open curly and it will skip the close curly. So if I, for example, forgot to use this, I would get an error, I think. Assertion statement failed. Fine. Because it's going in there. So the statement shouldn't track that. That should the compound statement track. So I think I'm gonna do this and take it in here as instead. It's gonna skip token close curly and return a compound statement. Yeah, so here we have to track that. So I'm going to move this up. And if token kind equals end of file, then you return then you return 0. Let's just see how this goes. We should get an error. So it's you're expecting an opening parenthesis, but you're getting end of file. I'm getting a close curly. I should get a close curly, not the opening parenthesis. I think maybe we're adding more stuff in here. Expecting something. There's an elixir. Okay, now I'm very confused. Like, so far this is right. We're just adding stuff in here, and they will be converted to something else. This is an error it is expecting something. So what is it expecting? It is expecting this kind here. So I'm gonna print what it's expecting. The number. Or it might be a skip instead. I think so. We're not using the first one. So let's get in number 14. Type number 14. 0, 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14. skipping an open parenthesis somewhere. Oh, here we go. We're skipping an open parenthesis. This is supposed to be semicolon. Yeah, of course that's supposed to be semicolon. It was just that the command line was a little bit tiny. We're gonna have a semicolon here. So it is expecting a semicolon but got end of file. Print current token. Token is 3. How can a token be 3? Wait a second here. Okay, it's expecting this but got the end of file. Where am I expecting this? Only one. It is basically failing here. Parse expression statement. I'm not gonna figure out where the mistake is. I'm just gonna make sure it's right. You're making a new statement, you're parsing an expression, and you check that it's ending with a semicolon. This is correct. 100%. Parse compound statements. Yeah, this has to check if the current token is end of file. Or okay, I'm gonna make it so that if I call this function parse statement, I has to have a statement there. There has to be a statement. So wherever I'm calling this, I have to make sure it is not end of file. Yes. So we delete this. Put this down here. We're skipping the open curly. And we're doing this while this is the end of file. And while the token kind is not the end of file, you're parsing these statements here. So after a state, like this should work. Expecting something but got end of file. $18. Token is this. It is not moving the... It seems like the skip token doesn't actually skip. It doesn't return. That's the problem. It doesn't return. Okay, now we're getting it. I think that was the mistake here. Expecting this but got end of file. In the skip token. Got end of file. Let's have it all like everywhere. That is only happening once. Token is this. Wait a second. I think the main function is messing up. Because this is starting. This is already the new line. Alright, this is already the new line. There we go. Expecting something but got that. That's fine. Okay, I think I'm back on track now. I'm sorry about this. Now this is supposed to work. So we're expecting a closing parenthesis but got end of file. So this is correct. What's not correct is that this is pointing to the wrong line. Because it is expecting something here. And it is pointing to the end of file. So I'm just gonna ignore this warning here. That is fine. I'm gonna fix that later. I want to get on with actually coding something cool now. So we have support for comments, that's good. Yes. All right. So what's happening is that we're parsing a statement. This is gonna check if it's a compound statement, so we can just check it here. Compound statements. Hello LXR. Welcome to the stream. Is it going like not so good? We have been a little bit slow, or I have been a little bit slow this morning. So we haven't really done anything. Yeah. Or actually we haven't made support for identifiers and comments in Elixir. So now we're gonna get tokens, which is either a comment or an identifier. So that's cool. Is end of file after semicolon? Yeah, so the problem was that the end of file is actually here. But since that's an end of file, I don't know, maybe the Elixir thinks that this is the end of line, but is making a new line so the line is underneath. Like, I don't know exactly. There might be some like a little issue there. But anyway, end of file is after this last one. It's when you receive the 0 character. And if the statement has an opening curly, you're going to parse a compound statement. Otherwise, you're just parsing an expression statement, which is an expression followed by a semicolon. So let's check out this first. This is allocating a new statement. And the statement expression pointer, so this statement has an expression field, which is pointing to the expression. So we're parsing the expression and we're expecting a semicolon to follow. In case of a compound statement, we're skipping the open curly and we're basically parsing all these statements. As long as this is not a closing curly, this is going to end the statement and this is going to end the file. And so here we have to check if this is an end of file. So if token, no we don't, because we're gonna skip the close curly here. So if that's not right, we're gonna get like expected a close curly but got end of file. So that's right. I'm gonna I actually love colors. Like, let's choose a little bit simpler theme. Yeah, let's use the one I did last time. Okay, Anyway, let's before we're starting to make new stuff here, because we're gonna do that right now. Let's just take a look at how the structures are. So we have, these are the structures currently. We're gonna add a few more, but we have a statement. So a statement can either be a compound statement, I'm using a union here, or it can be an expression statement, in which is just a pointer. And this kind field will actually determine if we're gonna use this one or this one. So this is this is the first member because we need these fields to be cast compatible with the statement. So I can, for example, say that I have a statement pointer and I'm casting that to an expression pointer, double pointer, or a compound pointer, because they have the same address. And then we have a compound statement, which is just a list of statements. We have an expression, which is either binary, unary, or primary. They're different. They're only like telling how many, like the binary is pointing to two expressions, like the left-hand side and the right-hand side. The unary is pointing to the operator. So you kind of have, if I have like a deref, then the kind is going to be a deref. The token is going to be this start token, and the operand is going to be whatever after. So that's the unary expression. And binary expression is, for example, a number times a different number. So the kind is going to be this star, the operator is going to be the star, and then you have the left and right, which is this number and this number. And the primary can either be a number, or it can be an identifier. So we're going to add this now. Identifier. So we have to check if this is an identifier. We're going to make a new structure. Maybe we can make an identifier structure because we want to support namespaces, and then we might need to store additional information from an identifier, and we need to probably get the namespace from an identifier, so it might be nice to have a structure there. I'm not sure. What do you think? I think I maybe want to have because each single identifier can have like a namespace. I don't know. I'm gonna do it now. So this will perhaps have like a namespace thing. So we're at least having like a token for the name. Yeah, token for the name. Token for the identifier. No, I'm gonna change that later if we have to. So we're saving the token here. If this is an identifier, we're gonna store two things. We're gonna store the declaration and we're gonna store the actual name. Identifier. So this is just a string. And after this, we need to store the actual declaration. So this is gonna be filled in by the second pass. We're gonna talk about that in a few, like probably 1 hour or something. And we're gonna add declarations. So declarations are completely separate by than statements. So if you write something like data has type U32 and has a value like this, then this is gonna be constructed to a declaration, which is data should have the type U32. And this is just going on the scope. This has nothing to do with the code. And then the statement is going to be data equals 456. So this is going to go on statements. So we need to make some kind of structure for this to bind this name to a specific type. But that's for later. So that's why I'm making it the structure. Yeah, so this primary token is an identifier. We're gonna place it here. We're also having it here, but it's easier to access it from here. Let's use a name instead. Yeah, for comments, I probably want to ignore comments in the middle of something. So both like all expressions and whatever are just gonna ignore the comments. If it's a comment between statements, I want to store it and I want to print it in the assembly code. So we want to make a new statement for a comment. This is just to make it very visible. This has a token. I'm just gonna say token here. So the statement can either be a compound, an expression, or a comment. And this is not a pointer. Comment, and then we're gonna change the type as well. So now the expression can be, no, the statement can be an expression, a compound statement, or a comment. So now we're gonna support that. This one we need to make a type def for. So I'm using a separate file for the type defs because I don't like them. I liked them before, not anymore. Oops. Primary is a weird name. You would have to be nullary. Nullary. Yeah, because it's pointing to, like, so you describe it after how many expressions it's pointing to. Nullary. Yeah, I'm not thinking it's too bad, but I'm gonna call it primary for now, because it makes sense to me that it's kind of a primary expression, like a basic expression. But we might change that later. It is just like an F2 and we can rename it. That's what's great with Visual Code. You can just rename and doodle around. So now we have all we actually need for identifiers. We need functions as well. Okay, let's just add in all the things we might need here. So there's going to be a few structures. And let's think bigger for a second. So first of all, I'm going to split this so we can have the type defs here as well. Thank you for following, welcome. So at the highest level, you have a program. So this is going to be a structure. A program. Thank you for following, guys. Welcome to the stream, everybody. So we have a program, and the program consists of maybe some compiler options, maybe some, like, we can put in whatever we want there, but it's gonna have a list of translation units. So I'm gonna call it code units. Code units. Oh my god, thank you for following, everybody. And we have a structure called code units. So this is gonna list multiple code units. And since this is listing these structures here, I need to make sure I have a list node here. I'm gonna make this as well. So that's a code unit. That's describing one single file. And one single file has one big compound statement. So I'm not gonna make that much difference of a global scope and a local scope. It is basically the same thing. The only difference is that in a global scope, if you have a variable declarations there, they're gonna go in the data section or BSS. Otherwise, they're gonna go on the stack. So in that matter, they're different. But I think I'm just gonna ignore that for now. It's very easy to change later. So that's a code unit. And this is really just gonna list the scope. So we have to make sure we know what a scope is. So let's make an example. If I do something, let's make a program. Let's make a program that this is gonna be able to parse now. Yeah, let's make an actual program. So we want this to be able to parse. I'm gonna have a function, so I'm gonna call it main. And I'm gonna use this type layout in my program, in my language, which is gonna be like, you have a variable, then you declare the type, and then you can have like an initialization if you want. For example, this. And optionally, you can disable this, and then the compiler is gonna figure out what the variable is depending on the right-hand side. So it makes sense if you think of it as, here is a type, then main is also a function type. So it makes sense to write it like, this is a function, and it takes some arguments at the input and returns some arguments at the output here. And then we might change things later, because maybe we want to do tagged outputs as well. So maybe I want data to be an output, and probably a result. And then I can just say data is equal to something and return. That should be valid. But this is like what I'm thinking. So with that in mind, it makes sense to have a function declaration look like this. So we say that this function has this type here, and it is equal to this compound statement. The problem is that I don't like that equal sign. I really don't. I don't know. This is a compiler for a custom language, yeah. I don't have a documentation. We're just doing it on the fly. I kind of know what I want it to look like. But let's make this the syntax here. So this is the function type, and you can have parameters here. So we're gonna have a construct for describing this, and inside the function, we can have some variable declarations. So I'm gonna say data is equal to 50. We can actually do type inference right now. It is very simple as long as you don't do something like this, because then the compiler would need to do like first a pass to figure out this, and then a second pass to figure out this. So there's probably an algorithm for doing that. I don't know how the type inference actually work, if it just does many passes, because if you have like multiple of these statements below, if you do it the naive way, you would probably have to, in the worst case, like 10 passes if you have 10 different variables. But I think there's a better way. Anyway, we have some kind of number here. So this is a declaration. Let's make it a type just to make it simple. And we're gonna have an if statement. We're not gonna force any parentheses because I absolutely hate that. So if data is equal to 5, which is not, it is gonna do something here. So it's gonna declare a new variable, temp. This is a U64, and that's the value 56. And then it's gonna declare a new value, which is called data, which is a char. This is actually a pointer to char. So you read it the right way. You read this as a pointer to an array of 8 pointers to char, for example. I think that makes much more sense. So this is a pointer to char, which is equal to 0. The problem here is that we already have the char, the data variable. So this will actually be two different variables because this is defined in a different scope. I almost never uses this in C, but I know it's a thing, and it is actually very simple to implement. So you want to track variables within a scope. So when I open a new scope here, I have to make a new construct which is called a scope. And whenever I'm declaring something, for example like this, like let's just see what this is gonna look like. So this is not gonna look like this. So this is gonna be temp, which is a U64 on the scope. And then you assign temp to 56. And then you're gonna have data, which is a type pointer to char, which is going on the scope. And then you assign data is equal to 0. So this is the same. So the thing is that where is this gonna go? This is gonna be placed in some kind of list or hash table on this scope here. So we're gonna have a scope which is sort of containing all the declarations, because they're the thing which are important. We have to look up the declarations to know the type. So basically we have to save these things here. We're also going to be able to do whatever we want in this scope. So if I, for example, want to have a new type, I want to have an IPv4, which is of type U32. So I'm using 2 colons here because this is a type def. The same way, if I want to have a structure, I can just say I want to have like a token structure. I'm going to type the token to this structure here. Then these things also need to go in the scope. I have to say that this name here means this type here. So this is also going on the scope. I don't know if this makes sense, but and also I want to separate these. So I want this to be placed in the scope in some kind of type list. And this is going to go in the scope in a variable list. Variable. Also, if I have like a local function, we need to figure out that that's going to be able to use local variables. I think so. But if you have like a local variable, for example, like a loop. Oops. This is also a declaration which binds the name loop to this function here. So that's not kind of a variable, even it is a variable. So we might even put it here, but I'm gonna make a new list for it because it makes it a little bit simpler. Yeah, so we need to have some kind of scope structure, and we need to be able to place all these declarations and type defs and function definitions inside that scope. Also, when I want to parse, let's make it a little bit more difficult. If5, I'm gonna do something else. I'm gonna make a new variable. This is 100 U32s. The thing is that when I'm gonna parse this function, or when I'm gonna generate the code for this function, I need to set up the stack frame first. So I need to go through all the variables here, and I need to assign them to a specific place on the stack frame. So basically I need to list all the variables. But this function is only having the top level scope with like the data declared inside it. So I have to list the scopes together. In other words, this scope needs to contain a number of subscopes. So if I have like an if statement here as well, this is going to open a new scope. Open a scope. And this is going to open a scope. So then this top level scope needs to have 2 pointers, or like a list of subscopes. And also, we need each of these scopes here to have a backwards pointer to the parent scope. Because if I want to use the data variable here, data is equal to 56. Actually, let's do F5 again. So we declare data. So U32 is something here. If I'm going to use this variable, like this is an assign statement, and I want to assign the value 56 to this variable, I need to go up. I need to check if the data is present in this scope here. And it's not declared in this scope. So I need to go to the parent scope, and that's where the parent pointer is coming into place. So I can get this scope here, the parent scope, by looking at that pointer. And here I can see this is declared, and from that declaration I know where on the stack frame this variable is located. So this is going to be data U32 going on the scope as a declaration. This is going to have an offset from our base pointer, which is the base of the stack frame, and then it's going to have an assign statement after that. So data is equal to some value. So here I'm going to go up one scope. I see that this has a declaration. This is on this scope, and I can get the offset here. So when I'm assigning a 56 to this variable, I can get the offset here, which basically means I can get the address. So I'm going to load the address into, for example, the racks, and then I'm just storing this into that address. So that's how it works. So declarations are completely different than actual statements. So therefore we're going to keep them totally separate. Did that make sense? I don't know. It took a while before I knew it, before I understood it. A lot of try and failure. Do you have plans to make a specific project in Luxor later? This is I'm gonna totally switch to this language because I like C. I don't like any other languages out there. So I'm mainly making this for myself, really. Because I like programming like operating systems and embedded systems, and I like programming that kind of stuff, but I want to have a better language. I don't care about the speed, I care about the coding experience. So probably if I need a speed, I can make an LLVM backend. But as long as this works, I'm going to be happy. It shouldn't be that much work to make an LLVM backend. Just made a sub RSP for every scope. Is that going to work? Sub RSP. That's not an instruction, right? Is it? How much of writing a compiler is thinking in assembly, and how much is thinking in C? They're actually very similar. C is very close to assembly. Like very close. Coffee, I'm actually drinking coffee now. Iced coffee. It's an espresso. An Italian espresso. It is really good. No, Brazilian espresso. Any error handling in your language, it is going to be like, what kind of error handling are you thinking of? Like if you write something stupid, or like some kind of Rust safety checking? It's going to have some safety checking, like null pointers, and if you're doing something really stupid, it is going to warn you. So if you're returning a pointer to a local function, for example, then it's going to warn you, because that stack frame will probably not be valid anymore. Okay, so let's actually make... The only thing you really need to remember is that we're keeping declarations separate from the actual statements. So this entire thing is a very separate thing from, for example, this. So that's the only thing you have to remember. I'm actually going to bring this up here. Thank you for following, welcome. First coffee is hot and after a few moments coding is iced coffee. Yeah. This is cold though. I mean, return errors. Yeah, it's gonna like return errors. I plan on having you can return multiple things. There were always this, like, also this guy who told me something about return values as arguments. So passing references and values are kind of the same thing. So maybe I read what he said, but I didn't really understand. I think I understood it when I read it. But it was actually really smart. You can say something like in or out. Like how is this going to be? Like data, this is an out, U32. So this means that I can say data is equal to a value, and that is actually a reference. And it makes it really simple to understand what this is. And you can have like an in, or you can have an in out. Like kind of in HDL programming. But I don't know. I'm gonna check that later. But it's gonna be able to return multiple values. So error handling should be fine. And the first statements is also gonna handle that. So you can, yeah. Okay, so a program has a number of code units. Each code unit has a name, like a file name. And this has a global scope. So I'm gonna make a scope pointer global scope. So we need to make some kind of scope here as well. Program code unit and scope. So ideally we would have a hash table for the scope, because if the program gets big, I don't know, probably list implementation will be faster than a hash table, depending on the site, like the number of elements. And it is certainly, we can make a scope there, like a hash table there. There is a cool algorithm for computing a hash value for strings. So it's actually kind of simple. I think I even have the implementation somewhere. But we're gonna start with just lists. So this is gonna be a list of declarations. So let's make a declaration first. So this is the thing which is, like if I'm declaring something, data is supposed to have the value or the type U32, that's in a declaration. So this is a declaration. I'm gonna have typedef here because we're gonna add a few more now. Thank you for following. Welcome to the stream. Welcome, Mr. Hammond. A declaration is gonna be a mapping between a name, and it's gonna be a mapping between a name and a type. So we need a type. So we need a type. And what is a type? We can have multiple types. So we're gonna have a type kind. We're gonna say what kind of type we have. And this is where I'm using kind for a thing, because I don't want to have type, and I want to be consistent. So it's an enum type kind, and that we're gonna place up here. And we're gonna say, what kind of types do we have in the language? Well, we have some, what are we gonna call it? Like usual, like basic types. I'm gonna call it basic. which is just like U64. It is just, it has a fixed size and a fixed, and it has a signed. It has a, what do you call it? It is either unsigned or signed. That's a basic type. It is not a struct type. And by the way, struct type we should also have. So I'm gonna use the same for structure and enum. So I know structure and union. So we could say like, no, we're gonna add structure later. We have pointer type, and we have type kind counts. Okay, so currently we're only having basic and pointer. So that's a type kind. So we're gonna add a type kind down here. This is also gonna be CAS compatible. So we're gonna have a union. So this field is telling what kind of union member we're gonna access. So we might have a pointer type. I think I'm just gonna call it pointer. No, I'm gonna call it pointer type. That's a great name. And basic type. So this is really the difficult thing, I think, with making a compiler. Just knowing what kind of structures you're gonna be needing. Basic type. So this is gonna have either a pointer type, pointer, or a basic type, basic. So that's a type. And a declaration is then a mapping between a string, which is the name, and the type. So each single, I'm using a type pointer because we're going to point here. Type. So each single declaration has a mapping between these two. And also, so what I'm doing here, this declaration structure is basically for this part. Yes. And we need some more things here as well. So the declaration, I want to keep some token pointing in here. So I'm gonna save the token which is pointing to the identifier. So I'm gonna say name token. So that if I have, for example, a declaration, like if you do like this, if you do this 2 times, then this is gonna perform a lookup in the current scope, and then it's gonna find it here. So by saving this token here, I can actually see that, I can actually say that this was declared, but the original declaration was here. So that's why I want to save the token as well. And the declaration needs one more thing. We need to know what kind of declaration we have. So if this is a function declaration, we can probably just do it here. So this is a function declaration, we have an offset. Now, if this is a variable declaration like this, then the data has an offset. And if it's a if it is a function declaration, so this type here, when you write this, that will basically be 2 things. This will be a declaration which looks like this will be something like function data returning a U64, and this will have a type which is function U32 returning U64. So we know identifiers. So this type here is going to be where this is pointing. And we also need to store the actual data, like the identifiers here. So I'm going to make a function structure. Let's actually make a variable structure as well. So the variable is containing just an offset, probably more later. And then we do variable, and function. And both of these are going to be defined on the typedef list. All right. Are you making a mini helicopter game? Isn't that Gamoso? Didn't he make a mini helicopter game like a few days ago? I just saw it on GitHub that he like mini helicopter game. I watched his stream. I don't know why I did it though. I don't know. Okay, so now this should be valid. So declaration is mapping, this is very simple. And declaration is mapping a name to a type. This is the mapping we're looking for. This is just more data that we might need. So if I have like a function declaration, I can go in here and I can get more information about the types and stuff like that. But this is really the core thing, which is important. And since we have multiple things here, we need to know what kind of declaration we have. So you're gonna have a declaration kind. Which is an enum. All right. That's supposed to go 2 times. So we have a declaration variable, and we have a declaration function. We're also going to have like a declaration for the types. So if you can declare a new type, like a typedef in C. So this is going to be allowed in our language, but then it's going to be like IPv4. It's going to be a U32. So if you write this one, oh, that's wrong, IPv4. So after this, you should be able to write like, I want an IP address, and the type is going to be IPv4. That's fine. So we might have a declaration for that as well. And I don't know if we really need it, because this is going to be implicit from the scope list. So the scope is going to have 2 lists now, one for the variables and one for the functions. So depending on what list you're looking in, this is going to be like a fixed value. But I guess it's nice to have there as well. So what does a function have? We should have a function name here, which is the name. We don't need it 2 times. What more do we need? We need a list. We need a list of declarations. Basically, we need 2 lists because we need to know the function arguments. We can make it very simple. Like we have 2 options here. Either, like we're gonna try to make some structure for describing this. So either we can open a separate scope right here, and then these declarations here go in that scope in the right order. That's gonna fix the issue. The problem with doing that is that The problem with placing this on a separate scope, that is perfectly fine. The problem is this. This will then be allowed because the compiler is going to look for the data in the current scope and it's not finding it there. So it assumes that this variable here is valid. So that may be, possibly that can be checked from the second pass. So when I'm actually parsing the function, I'm going to go through all these arguments and I'm going to check the next scope, which is only going to be one. Yeah. Can you make more features when you use channel points? Yeah, I can. I'm going to try to see how I can do that. Definitely. We have to find some cool things there. But I don't know how to use it myself. So I have to watch a YouTube tutorial or something. Would IPv4 be a type def or would it be a unique type that just shares the underlying type? It would be a type def. So the thing is that if you're describing a new type here, so I'm having a variable and I'm having not like a U32 or a char, but I'm having like a name. So this might be a token. Then the compiler doesn't know what this thing is. So if I were to parse this now, I would just say that, okay, variable is a declaration because we have the colon here, and it is expecting a type, so it should be a type here. So it's just going to assume that the token is a type, and then it's going to parse the rest. So maybe after this, we say that the token has a type U32. So this is just going to go in the scope. And the second time we go through this tree, we see that the variable has type. Then it's not going to be token, it's going to be token, which is an unknown. So it doesn't know what this is. So then it's going to look up on the current scope after this token identifier. And it's going to find a declaration for this token here. We're looking in the token, the type list. And then it says that this token is the same as this type here. So it's basically going to say that this variable type is equal to this mapping type here. So at the very end, the name you're using here doesn't matter. Like when you parse the tree, when you're done parsing the tree and traversing the tree later, this is basically going to be like variable U32. It's going to look like this. It's going to be the same type. Same pointer here as here. I don't know if that makes sense. Do you have a context-free grammar? What book did you use to learn operating system programming? I didn't use any book. I saw one tutorial on like 1 hour how to do the context switch on ARM, which I think was very nice. Unfortunately, that's taken off, so I can't find it anymore. But that was really nice. But in fact, it's just like it's just like 30 lines, and you have the context switch. And then it was just like trying, testing and failing. And I'm not an expert on operating systems. I just enjoyed doing that. So, yeah. I haven't been programming for more than like 4 years. 4 years, 3.5, 4 years. Seriously. 3 years seriously. So I'm not an expert on this, not at all. But I'm very interested in this. Yeah, so my operating system is not that good. They work. But I don't read any books. I think it's a waste of time. For me, it's a waste of time. All right, let's recap here. We have a declaration that is mapping a name to a type. We're also saving a name token, and we're saying what kind of declaration this is. And we have some additional information here depending on what we're going to use. For the function, we need to store the return type here. Multiple return types, fuck. We're gonna store the return type just in the first go. Return type. Nothing more. Probably we will have the address of this function if we're gonna make a linker. Yes. So a scope contains multiple of these declarations. It contains lists of these declarations here. And if I want to list something, I have to make a list node. So I'm gonna make a list node. And then I can list these together. So I'm gonna say like variables. I'm gonna make a list for functions and probably one for types. We're not gonna use that though. So this is the scope. Additionally, we want to have the pointer to the parent scope. So I want to have a pointer to the parent, and I want to have a list of subscopes, child scopes. And since I have a list of child scopes, I'm gonna have a list node. So this is just for listing these together. This is for this is for iterating through all the scopes in something, in a function or whatever, and for recursively looking up variables. Did I have the looking up? Looking up variables. Yeah, so that's the scope. So I should be able to list those scopes together because I have this. And also I also should be able to go back because I have the parents. So then, the code unit will contain a global scope, which is pointing to the main scope here. And from that scope, I can get all the subscopes. And all the functions and all the variables. You can't really have... Yeah, you just have variables here on the top level scope. Also, the variable declarations might have like some expression in it or something, in case of the global scope. I'm not going to do global variables just yet. Okay, does this make sense? And declaration as a function. We have a return type, we have an offset here. We have a type. Okay, so let's do this one. So we have either a basic type or a pointer type. So the basic type will, first of all, each type should have a size and an offset, no an alignment. So we have a size and we have an alignment. A size and an alignment. Basic type. Do we need to have basic type here? I don't know if we're gonna put anything in here because a basic type is just using these really. Oh, we need to know if it's unsigned. We can take it there. Is signed. Yeah, so I have a boolean is signed. A pointer type. This is gonna contain. It's gonna contain a pointer to the base type or the subtype or pointer to. So this is what the pointer is pointing to. And in case we have an array, So let's make things a little bit more complicated again. If we have like, I'm using the old syntax here. It's gonna be like this. U32. 30 and 10. If I have something like this, then this is gonna be a pointer to, this is really an array of U32. So this means that we have one pointer type, and since we have an array here, which is the same as a pointer, I'm gonna give it the element count. I'm gonna call it element count. Yeah, I'm gonna call it just count. So if this is an array, this is gonna contain like 30 or 10. If this is just a normal pointer, like for example this, that should be 0. So this array is pointing to this type, and this is pointing to this one. I don't know if that makes sense. A pointer is basically containing what it's pointing to and the number of elements it's pointing to in case of an array. In case of array. So either a pointer type or a basic type. So this is, and we need to know like struct type and stuff like that, but we can do that later. So we have a type. If we have a type, we can type this out. We can map these names together. We can do this. We have a list node for listing multiple declarations in the scope. So this one is for listing inside the scope. And we have the scope. A function also has one more thing. It has we can either do statement or compound. I think I'm gonna say compound. Body. This is really the same as a statement. They have the same address. It is just how the API is gonna look like. So I might change this to statement later, depending on how ugly the code is gonna be. But this is the compound statement body, which is this part here. That's a function body. And we need a scope pointer, I think. This is the first function scope. So this is the scope here. This is the function scope. And then that is pointing to the next scope, which is the actual body. So we have to check when we're parsing this function or like post-processing it, we have to check if this function scope contains something in body scopes. So the compound statement will also have the scope which is which contains that compound statement. So you need to check if this is containing something here. That's an error. That would be like this. So you have a data here and you have the same data here. These are in two different scopes, but you shouldn't be allowed to do this. So a compound statement need a scope pointer. Okay, any questions about this? I think we're done. Let me just check and then I'm gonna check the chat. Identifier, we're not gonna use that one. I don't have identifier. Let me just check if I have everything. Basic type, pointer type, normal type, function variable, declaration, scope is there, code unit, program. That seems right to me. Okay. Written by Andrew Tannenbaum. Is that the same Andrew like built the language SIG? He's also called Andrew. I don't know if that's the same guy. but I haven't read the book. L value. Yeah, so L value is, I don't know where the name is coming from. Is it like left value? L stands for left, and you have R value, which is the right. But L value is basically what's on the left of an assign statement. So we have to be able to store something there. There has to be some kind of deref to an address, or some identifier you have to store things in. That's the L value. Good luck, thank you. Good afternoon, welcome to the stream. It's a big book to read. Yeah, it's a big book to read, but I don't think it needs to be that big. Anyway, I think this is gonna make much more sense once I start actually parsing this. So any more questions before we begin? The program consists of code units. A code unit is basically this entire thing. It has a global scope, which contains all the variables, functions, and types in that scope. And it also has these elements for listing subscopes together. The reason I want to have this is that when I already said that, but if I have, for example, many scopes in here with declarations, I need to go through all of these and assign them to a place on the stack. So I need to iterate from the main function through all these statements here. That's why I need the child scopes. And these are just declarations, and a declarations maps a name to a type, and a type is just a size and alignment, and eventually like a pointer if it is a pointer. And basic type pointer to, and then we have the statement, which is either a compound, a comment, or an expression. The statement kind, statement node, and then we have these different things here. And an expression can either be a binary, unary, or a primary. And we have added this identifier name here for the primary. So this is going to be if I have like a variable, data is equal to something, and data is going to go in here in a name. And just the enums. So I think this is good. Let's start with our return values. We can make a return type here. And yeah, let's just do this. I'm just thinking how much we're gonna implement before we try things out. Let's do the declarations as well. So I have a data. I have a data which is a U32 equal to some value. And I assign it to, for example, this equals something like this. It doesn't matter. Thank you for the follow, by the way. And thank you again. Compiler can sometimes be very reasonable at first. Yeah, so this is actually the simple part. And because you actually just know how to do this. This is the hard part. This is actually simple as well, but once you know how to structure the compiler, like the parse tree, it's very simple to actually parse the tree. Yeah, this is a compiler for my own language. Public members variables in the CPP. I noticed that you have a lot of public members. I'm not using C++. If you're talking about this, this is just define. I'm just type defing this. And I'm gonna use a unique name for all the structures. So this is just hiding the fact that I have to do this in C, because I don't like it. All right, let's start. Our Elixir can now parse identifiers and comments. So I want to make a function in the lecture for recognizing a keyword. And I'm going to make some keywords because the function is the first thing we're going to recognize, and that is a keyword. So I'm going to go in here. That's a token kind. Let's have an enum keyword kind. Oh my god. Keyword kind. And we're just going to start with function. The function keyword. And the types, we need types. And we're going to add a few more keywords. So U64, I'm going to have U32, U16, and U8. This is all the types we're going to have on the unsigned side. And then we're going to have the same for the signed. I'm not going to call it integer. I'm going to call it signed, like this, because it doesn't make sense for me with integer. It's unsigned or signed. Also, we have a char type. The char type, and this is the same as a signed 8-bit integer. It is just a better name for it. So it makes the code simpler to read. Yeah, let's make this as typed as well. This an enum. Keyword kind. And then we're gonna make a function which is recognizing these keywords. So as they are operating with tokens, I'm gonna do kind of the same on the keywords. So this is a bool. Is keyword. I'm just gonna make a function for checking if something is a keyword. And this is gonna take in a token, and it's gonna take in a keyword kind. And then we're gonna implement this. I'm gonna do it at the very end here. So first of all, I need to define what they are supposed to look like. So I'm gonna make an array of strings. Char pointer, keywords. And we're gonna start with the function. And then we have U64. And then we have U32. We can actually make this very fast by computing the size for each of these, because I know the size of this word here. So if this is not a match, that's going to be very fast. But I'm just going to check it for now. U16, U8. Now let's copy those. And we have S for signed. And we have the char type. Yeah, and we also need to know the final size here. So the keyword kind is gonna also say where it ends. Keyword count. I'm gonna say kind count because we might have a keyword named count. So if kind is bigger or equal to this, we're gonna return an error. We're gonna say error. We're just gonna print something. Keyword not handled. And then we have to compare them. So I'm gonna do a string compare, but I don't know the size here. I think I'm just gonna do it manually. So I have I'm gonna say string A, and this is equal to the token name text, and we have a char pointer B, which is equal to keywords, this array here, of kind. So this is gonna give us a pointer to the right thing here. For a long time have I been coding? Like 3 years, 3.5 years, like seriously. Something like that. I had a few subjects before, but that's like, I didn't even know what a pointer was. Yeah, 3-4 years ago. Okay, so we're gonna also track the size here, because this has a specific size. This doesn't end with a 0. Actually, let me do a for loop here. Yeah, so for I is equal to 0 up until token name size. So this is going to iterate through the entire token name. And then we need to check if either b is 0. So that's the end of the end character here. We're checking that first. Or the value of a is not equal to the value of b. We return false. So if they're not equal, we return false. So if we're exiting this for loop here, then we should have a match, but we still have to check the size. So let's say the token is like, the token is char. No, the token is like, the token is just ch, and we're looking for char. So this is gonna go through CNH, and after that we have to check that the b pointer actually is 0. So if b return false, else return true. Is that gonna work? I hope so. I think so. Let's test it. Yeah, so I want to have like is keyword. I'm gonna make a fake token. I'm gonna say like token, and we're gonna say token dot name dot text is equal to CHA, and token name size is equal to 3. This has to be the same though. And then we're gonna look for, we're gonna give it this token here, and we're gonna look for keyword char. So this is a Boolean. All right. So let's see if this is working. Okay, we're missing some semicolons on the tree here. There we go. So bool is 0. And discarding const qualifier. Okay, we're not going to use it. So This has to be a const char pointer, which means I'm gonna have to say like const char here. In fact, I can do them both because I'm not gonna change any of these. This is gonna give me 0. If I have like char and give it 5 characters, it should also give us 0. And if I have exactly char, 4 characters, it should give me 1. Fuck. Am I returning? Keyword char. Return false. I'm not increasing this, I think. Yeah, I'm not increasing these pointers. We can also do it in here, I think. A++, B++. Is that cleaner? I don't know. Do you think this is cleaner? This is gonna return 1 though. And this is gonna return 0. And this is gonna return 0. So that's working. This keyword is working. Be right back, gotta get a cap. Okay. It's a custom language. Boolean C, this I'm actually using the C11 extension. So you can see I'm compiling with std equals something. std equals C11. So then I can use bools and stuff like that. I think C should include bool, and I'm definitely gonna include bool. B of I. I could use B of I here as well. I'm actually gonna use B of I, that's cleaner. I agree. Thank you, that's a good suggestion. All right. And if B is 0, no, this is gonna be, no, I'm not gonna do that because then I have to make this global. Like, I have to increase the scope of that variable. I'm gonna do it like this. So I think we have everything we actually need now to make, to parse this thing. I'm gonna get go fix Elixir. Why do I have to go fix Elixir? Am I writing something I'm not allowed to? Probably. We don't support this one. We have to add support for colon and this arrow and equal. I think that's it. Yeah, so colon. Let's just move this over here. Okay, so we're gonna try to recognize these new things. So I'm gonna add it after here. So I'm first gonna add the arrow. Actually, I'm gonna add the semicolon, the colon first. The colon, the arrow. Yeah, the colon and the arrow. Do we have equal? We do not have equal. So I'm gonna add equal as well. Yeah. So I'm adding arrow and equal. After this, so token colon and token arrow. That's a colon, that's an arrow. And then let's go in Elixir. We have to recognize these things. So we're gonna say if we have a minus sign, which is the first character here. If we have a minus sign, and if the next token that's a char, I guess. If the next token is equal to this arrow thing, then we're gonna do something, then we're gonna parse an error, no, then we're gonna parse an arrow. Otherwise, we're just gonna parse the minus. Skip punctuation, lexer 2 token, token, arrow. So this function tells the lexer to skip 2 tokens. It is going to skip this one, and it's going to skip this one. And it also tells the lexer to assign the token type arrow to this token. So this is basically doing what like everything we ask for. And then we're going to do a case for this. We need 2 columns there. Because we're going to recognize this and we're going to recognize this as well. So we can just add both, I think. Just 2 seconds. This is actually not going to go faster, so I'm going to switch back again. Oh, that's funny. And I have a standing desk. I'm gonna stand for a little while. Oops. There we go. So there we go. Yeah, C has bool. I'm writing a compiler in C. Yep. Electric table, yeah. All right, let's see if I still have this. So we're gonna skip a punctuation here. Actually, we're gonna check if the next one equals to the same. Punctuation. So we're gonna skip the lexer with 2 tokens here, and we're gonna say that the token is gonna be a token double colon. Lexer 1 token colon. So we're gonna make the double colon. So that's the first one. And after the colon, we're going to do double colon, which means that after this one, we're going to say double colon. Okay, so we should be able to parse these new symbols now. So we can ask for an arrow, and that's going to give it to us. Okay. Now we're actually going to start parsing this. Is there a better way of doing this than using a bunch of cases and if statements? It is not that slow, to be honest. The case is probably going to be like a jump table, and it is not that slow. I've benchmarked this lexer like something similar, and it lexes 100,000 lines in 5 milliseconds. That is really fast. Like, the compile time is not depending on that. There is a different way by using some kind of a, what they call it, like a regular expression table, like some parse generators. We tried to make one of those, and that is not better. That is not better. It's very similar to Go Odin, but I'm gonna make it more similar to C. State machine scanner. Yeah, like it's gonna be faster. but let's say we're gonna multiply it by 10, then I'm lexing 1 million lines of code in 50 milliseconds. So the question is that gonna be noticeably faster? Like, is the speed up gonna be noticeable? I don't think so. Yeah, optimized code is definitely less readable. So there were really cool guy on the stream for like a year ago, like a few months ago probably, and he saw that I was doing this regular expression shit, and he just said like, you can't do this. And I'm very glad he said that to me. And this is actually based on his implementation. The previous one was very similar. Okay, let's start. So we're not gonna parse a statement here. We're gonna parse the entire program. And this is gonna get in the lexer. And it's gonna get in the parser. So we're gonna remove this, and we're gonna parse the entire program instead. We don't know all the units we're gonna process. We're gonna have it like this. Parse program. So this is going to parse a program, takes in a parser, and we're going to implement that. This is also going to get, because here I'm actually making a new parser. So this parser will be for the current file. So this is probably not right. I'm still gonna have it there, and then we're gonna parse a code unit instead, which is probably better. Like, parse a code unit. So this is gonna parse one single file. They're really similar though. This is just going to call into this. No, this is just going to call into this multiple times. So let's do this instead. So we're making a new lexer, a new parser, and then we're actually parsing the program down here. And then we're going to replace print statement with actually print program. And this is returning a code unit instead. Code units. Parse code units. Let's return. Let's just not return anything. Let's return 0. And if code unit is 0, return. We're just going to return here. And I hope I'm not doing too much of a change now, that this is going to be hard. Generator init. So this is generating the actual assembly. And we're generating the program, which is just a statement. I'm actually going to generate the program instead here. Yeah. So program, and we're going to give the program here. So this is going to be replaced with actually generating a program. So now we have a generate program. It's taking in a program. So this is not going to do this. Let's just try to write something. This is going to generate a translation unit or a code unit, which I'm going to call it. So this is going to call into this one. And the generate code unit is going to generate some kind of function. Generate a function. And we have a function in the, I'm going to get the tree here. So we have that on the side. This is going to get in a function. Or possibly I would have a function declaration there. But I know that the function is also a declaration, so I can just cast. It depends on what's easier to read. I'm going to take in a function. Static, both are static. So we're only going to support functions in the top level global scope. And that's fine. Yeah, generator init. Okay. Shit. We're gonna emit a function here. So that's gonna have the text, the global main. I'm gonna be doing so much changes now. So generator init is only opening the file. This is only opening the file so we can do emit, which is basically just writing to this file, which has been opened. Generate program. This is gonna iterate through all the code units. So I'm going to say list iterate. And what am I going to iterate through? I'm going to iterate through the program code units. And each of these is supposed to be a code unit. So I'm saying code unit equals list to structure iterator code unit list node. This is basically telling that we're having this pointer here and we're going to get this pointer here. So this is the structure here. And that has a file name and it has a global scope. So probably we should emit something like separator. So 1, 2, 3. Let's just use this. Commenting in x86 assembly is with a hashtag. This is going to emit a line. And let's print the name as well. Code unit file name, which is a string. So this has a size, and we have code unit file name text. So this is going to emit on each translation unit or code unit. We're going to emit this, and then we have the function underneath. I'm going to do one more line break here. That is the wrong one. Let's see. Yeah, like Seb Code was telling, that's a really important statement. You have to make it work first and then you can optimize. That's really important. And that's partly why I'm using lists here. Like this is probably going to be replaced with hash tables once the programs I'm compiling is going to be bigger. But like that's an optimization. This is going to work as well. Or probably faster even if the programs are small. But if the programs are small, the compile time is so tiny it's not going to be noticeable. Yeah, this is not optimizing. I have not done any optimizing yet. I'm using, the backend I'm currently using is this. So I'm just generating the stuff myself. Okay, so here's a code unit, and then we're gonna parse, we're gonna generate, so we have used the file name, and then we're gonna actually generate the scope. Generate the scope. And we're gonna call in with generate scope. And I'm gonna be using code unit global scope. So I'm gonna use a global scope there. Maybe we can, maybe this is gonna take in if this is global or not. It doesn't matter since we're not allowing global variables yet. Okay, and generate scope. This is gonna also iterate something. This is gonna iterate the functions. We're only gonna generate functions. No, we're only gonna generate stuff for the functions. And then I'm thinking this should probably be a function declaration. Declaration. And then we can just use a function here, which is just a cast. Let's do this instead. So these are the same, it's the same pointer. So I'm just gonna cast to get the more information here. Simpler. So I don't have to write like function declaration, function, and so on all the time, because this is longer. So generate function takes in a declaration, and I'm iterating it through all the function declarations. So what I'm getting here is a declaration. Yeah, this is supposed to be a function, so I'm just gonna assert that declaration function. And then we're gonna generate the function with this one. The global, that's supposed to be global. Some people like to have like shorter names if it's possible. So yeah, and hello by the way. All right, so that's generating a scope. Basically just iterating over the functions and generating those functions. And generate code unit. No, generate program. Wait a second here. This is wrong. We have to generate the code unit first. Yeah. Yeah, so that's still gonna work, but I'm gonna make a different function of it just if we need it. So generate code unit, and this is gonna print that. Code unit file name and the size. Let's have a string. Name is equal to code unit file name, which is a string. So then I can just say this. And generate scope and global scope. Perfect. And the global scope is just going to generate the functions from the declaration. And I have the declaration and the function here. So from that, I can get all this information here, which should be more than enough. So first I'm going to replace the function main. This is not going to be main. This is going to be the function name, which is the declaration name. So here I'm going to have a string. Declaration name. Is that right? I think so. So here I'm going to write name size name.text. And I'm going to do the same thing here. And this is not going to be main. It's going to be the function I'm parsing. And I'm moving that base pointer and so on. This is really going to be, I'm going to move this up here. And I'm not asserting anything. So the only thing that generate program does is to generate the code units. That's the only thing it does. And the code unit generates a scope generates a function, and that's up here. So then we're going to generate the statement, which might be a compound statement as well. So the function has a body, which is a compound, which is the same as a statement, so I'm going to call it a statement. We can just assert that this has type statements, no compound. Function body kind is equal to compound. This should be the case because you can't really have a function. You can't really just have this. You have to have some kind of compound statement after. So we just assert that that's the thing. And then we generate the statements, body, which is a pointer, and after the statement we assert that the stack level is 0. That makes sense. So after each function the stack level should be 0. We should push as much as we're popping, just to make sure we're not doing anything stupid. Also, this is wrong. This is right for now. But we're gonna adjust the stack pointer with a, so this is right, but we're gonna adjust the stack pointer to actually allocate a stack frame. So we have to do a sub instruction on the stack pointer. And this is the same, and a return. Yeah. Okay, let's see if this is working. I don't expect it to work. Print statement. Access statement is undeclared. So that will be a problem here. We're in fact going to be getting rid of everything here. So we're gonna print the program. And we're gonna make the program printer. So I have like 4 different parts. I have the backend, which is the Lexer. This is splitting up the token stream. This is handing stuff over to the parser. And when the parser is complete, this is gonna generate some kind of abstract syntax tree. And then we have the tree printer, which is gonna print that in a nice way. And then we have the generator, which is actually generating code from that tree. Yeah, so let's make a new print function. That is supposed to be print program. Print program. This is just going to print program. Print the entire program. So now that should work. Function declaration, that's wrong. I know what the problem is. Okay, so it's printing program, and then it has a segfault, and that's fine, because we're not handling everything here. I also want to know where the segfault is coming from. Okay. As we're parsing the program, we're printing and we're generating the program. So the generator is starting and we don't have anything there. And this is probably because the parser is generating a 0. It's not generating anything, in fact. So the parse program will parse a list of code units. This will in fact only parse one code unit. So we need some allocation functions. This is a mess. So here we're going to allocate more stuff. We're going to allocate a program. Thank you for following, by the way. Welcome to the stream. New program. It's not going to return any, like, taking anything. It has a list of code units. We're going to initialize this list here. We're going to initialize this list. And then we're going to return the program. Thank you for following, guys. Have you ever tried doing web development in C? No, I haven't. I've never done any web development, to be honest. Out of curiosity, how did you get into low-level programming in C? I'm just embarking on the same journey myself, coming from a decade of web programming. That's cool. Personally, I started with microcontroller programming, so Arduino. In fact, I started with Arduino in like a school project, and then I had this cool LED strip. That's like, I'm obsessed with LED strips, and this project is actually coming from the LED project, because I wanted to have something more powerful to drive the LEDs, and that kind of led me down the road to more powerful chips, and then I felt like making an operating system. So I might, like, everything I'm making now, I will eventually go back to the same problem with LED strip and make that actually work. Yeah, but I start with Arduino, and then I use the chip which is sitting on the Arduino. I can show it to you. Oh my god. There's this chip here. This one. Or there's probably a better picture somewhere. Like this one. And we have like this workshop on, not workshop, but workplace, where we can actually make printed circuit boards at home. So we have like an etcher. I don't know if that's the right name, but we can basically make it on the school in a few hours. And then I started placing those chips on the board, and yeah, and you can actually program this in C by using some kind of programmer. So that's where I started, and I moved from this one to more powerful chips, to ARM microprocessor, and yeah, that was the last project. So just starting simple, and that was what I did. Yeah, this rabbit hole. Head first. And getting started, I don't know, like I will probably make a YouTube video. I'm like, it was so difficult to start, and I don't know what's out there now. There might be good resources, but I only need to have like one step-by-step guide using, for example, an Arduino or a simple ARM board. Like, how do you make things work? Like, how exactly does things work? What is a linker? What is a makefile? How do you write the startup script? Why do you need to copy stuff around if you have like Flash, internal Flash? Like, what is that stuff really doing? So I'll probably make a video on that somewhere, sometime. Probably a stream. I don't know. Casey Mattery is making course. Hama Hero, yeah, I've seen that guy. He's really cool. Isn't that the guy who is on the stream with, what is it called, like, Jonathan Blow? Jay Blow? I think he was on the stream with him. Yeah, John Blow. But he's a really cool guy. Like, I've seen some of his videos. I just haven't had the time to follow this entire stream. But I really want to make video games sometime, because I have a really cool display. And so I'll probably follow the video sometime. Yeah. Like, he definitely knows what he's doing. Definitely. It is just starting, like, you can't know it all. Like, at least I can't know it all. So I have to start someplace and just learn. Alright. So parse a program. We're gonna make a new program. This has to be exposed. So new program. And this has a list which is already initialized. So then I'm gonna make a code unit. I'm gonna parse a code unit. I'm just gonna call this function here. So parse code unit with this parser. And then I'm gonna do list add last. So I'm gonna add a code unit list node to this program code units. So this is adding it to the list, to the linked list. And return the program. And for the code unit, we're gonna allocate a new code unit. Yeah, we're not gonna have anything in the code unit yet. Yeah, we don't have anything in the code unit. We can just allocate it. Okay, so that's allocating new code units. New code units. And I'm gonna return this code unit here. And then we're gonna actually parse. So this is where we parse a file. So this is supposed to parse an entire file. And it's going to return that code unit to the program, And we might add some more logic here, because we can't really parse the entire thing before we know what to parse. So there's going to be more logic here later. Jay Blow is a very good programmer. But I find it way too opinionated and elitist. What does that mean? Yeah, he's a very good programmer. Get overwhelmed while still being really excited to learn. Yeah, there's so much to learn. But I just find it very interesting to just start with a thing. It doesn't matter if it's something big or something smaller. Like maybe just go and check out like a list allocator or something. Try to make a list allocator. Just try to make something, and as long as you learn, you should be happy. That's at least what I think. As long as I can go to bed and I've actually learned something during the day, I'm very happy. So yeah, it doesn't matter if the project is big or small. You kind of have to start small. Yeah. All right, parse a file. How do we parse a file? Well, we're gonna parse a scope. So there's a difference between a scope and a block. I'm gonna call it a block. The problem is that this is really just a scope. This entire thing you see here is a scope. If I have something more here, like data is a U32, this is also like everything here is a scope. The problem is that this isn't a close by opening curly brackets and closing curly brackets. So this is really a scope, but it's a different kind of scope. So I want to make two functions for parsing a scope and parsing a block. And this is going to return a scope. Both are going to return a scope. Oops. Thank you for following me, by the way. I'm gonna call it parse block. Actually, I'm gonna make this on top here. So parsing a scope will actually be skipping. Let's fix the lexer first. So I want to have a lexer, which is the parser lexer. So I want to use this lexer to skip the token open curly. And then I want to skip the close curly. And inside the open curly and close curly is going to parse the scope. So you're going to save the scope. And it's going to return this scope here. And now we have to think a little bit. So this is really just calling the parse block is going to be parse block. So this is really parsing a scope. It is just not. It is just not treating the opening and ending curly brackets. So here we parse a file. We're going to call into parse block with a parser. And the parse block is returning a scope. So we can just say code unit global scope is equal to parse block, which is the top level block. So now we have to make sure that this is parsing a block. And we're going to be using these like enter and exiting a scope all the time. So I need to track like what is my current scope and what is my previous scope. I can get the previous from the actual parser. Let's track where I'm currently at. So the parser should have some information about the current scope. And the previous scope. The question, do I need a previous? I don't think I need a previous. Because the scope itself will hold a pointer to the previous one. So I'm going to call it current scope. And this is 0 initialized. So initially that's going to be 0. So I want to make 2 helper functions for entering and exiting a scope. A new parser, okay. This is a static function. We're gonna delete this one. We don't need it. Okay, so let's make 2 functions for entering and exiting a scope. So I'm gonna enter a scope. I need a parser for this because I need to update what the current scope is. And I need to allocate a new scope. So I'm going to go into the tree and we're going to make a function for allocating a scope. So this has some variables. So let me just go into the tree real quick so we can see what it's having. So we have 1, 2, 3, 4 lists. So we need to initialize these 4 lists here. So the variables, functions, types, these are these lists declarations. So these are declaration lists, and these list scopes. So I need to do list init functions variables types, and what is the last one? Child scopes. So this is just initializing all the lists. So we're not going to have a save fault when trying to access those. And doing the scope. So if I'm entering a scope, I'm going to allocate a new one. And this is initializing this as well. So what I need to do here, because if the parser currently has a scope, so if the parser has a current scope, so in the first time I'm calling this will be 0. But if it's non-zero, we need to add this new scope to the parent scope list. So I'm going to say list add last. So this is really the previous scope. This is the old scope. And this has a child scope list. Let's just make it explicit here. So old scope, that's parser, current scope. So I want to add the scope list node into the old scope child scopes. Also, I don't need to do this in the checker. So in any case, I want the scope parent to point to the old scope. I don't like the word old scope. I'm gonna say previous scope. Okay, so we're setting up the new scope parent is the previous scope. This might be or not be 0, but that doesn't matter. Yeah, let's see here. So isn't this everything we need to do? Yeah, we need to update the current scope. So parser current scope is equal to scope. And then we return the scope as well. So this should enter a scope. And we have exit scope. So exiting a scope means we should go to the parent scope if that's available, or no, we should just update the current scope. So we can probably assert we can't exit a scope if the current scope doesn't exist. If the current scope exists, we're gonna say that the current scope is equal to parser current scope parent, which might be or not be 0, but that's also fine. Don't need to return anything here, I think. So that is exiting a scope. So when we parse a block, that's going to return a scope. We're going to enter a scope. And exit a scope. The question is, do we need to do anything more here? Do we need to use the scope variable? I don't think so. So now we have a new scope. So basically we're still up here, and we have a new scope. So everything which is declared in the code here will go on this scope. So inside this, I will just parse a compound statement. So a compound statement will be a list of statements, and that might be a declaration, a type def, function, whatever. Like really whatever. If this is a global scope, we know that the current scope parent is 0, so we might use that for restricting the access to some of these things. For example, I can't say like data is equal to something like this on the global scope. I have to say data is, for example, this or this. So this is really just going to parse a compound statement. And this is returning a statement. Okay, so parse the compound statement. This is parsing a block. That is not really correct. You can't really write anything here. A block will only consist of declarations. For now, I think. So we're only going to parse declarations there. Parse declaration. So we need a scope here. enter scope. We're gonna just parse the declarations until that's false. So let's just do a while one loop here. And I'm gonna try to parse a declaration. I'm gonna make that up here, I think. Can you give me the settings for VS Code? Yeah, I should make it available there. This is just GitHub Sharp Dark, and I have the Source Code Pro as the font. Feels nostalgic. Yeah, C is a really cool language. And now my keyboard is messed up. There we go. So this declaration so this is supposed to parse a declaration, and again that's just a function call or like some declaration like this or anything else. So this will just be a declaration, and that declaration might just go on the current scope. So I don't think this might return 0 when it's done. All right, so parsing a scope. We'll parse a block. It will do something like parsing a block. This will do something while the current token is not end of file. We're gonna get the current token here. Lexer. So while the token kind is not end of file, it is just going to do this. This is parsing a block, a scope. So this is really, yeah. I'm actually going to look for end of file or this ending one. Yeah, so if it's either one of these, it is going to quit. So if it's either this or token kind token close curly. So if it's either, let me make some space there. If it's either end of file or close curly, we're gonna have and here. So as long as it's not end of file or not close curly, this is gonna just parse declarations. And this is parsing a block. So we should probably add it in here. I don't know. Maybe we can, like, this is gonna return a declaration. This function here. The question, like, what I'm thinking is that function gonna push these declarations on the scope itself, or should I return them here and I push them manually here? The thing is that if this is not true, yeah, because if this is end of file, that won't work. So if this is not end of file, we should have a declaration there, or we should have an error. So this won't really happen. So I'm just going to do this, and we're going to assume that that's being tracked by something else. We're going to do this though. C is the best language ever, yeah. What font is this? I've actually tried Hack. I don't know if I remember it, but I tried it. This is called Source Code Pro. Is it Hack? No, I don't think so. I think it's Source Code Pro. This is the one. It's very similar, I think. Okay. Parser block, and we're updating the current token there. So we don't do this. And then we exit a scope. We enter a scope, we parse all the declarations on the scope. We might push them here. Actually, I'm gonna try to be explicit here. I'm gonna actually push it. Because maybe in a for loop or some absurd thing, I don't want it to be on the scope. I don't know. Let's make a function which is pushing a declaration on the scope. Static void push. Oh my god, I'm not gonna do that. So we have the scope, which is equal to parser scope. So I'm gonna push this. I'm also gonna get the declaration. I'm gonna take in a scope here instead. So I want to push this declaration on the scope, which basically means I need to place this one, more specifically this list node here, in one of these lists, depending on the kind here. So to avoid duplication of the code, I'm gonna make a list here. And I'm going to say the list is 0. And if we're actually going to switch the declaration kind. Switch declaration kind. If there's a function, do this. If it is a variable, do this. Default, we're gonna error. We're not gonna have a default case. So just exit there. So we break here. This is just gonna update the list. You know what? I don't think this is a good idea. I'm just gonna do it manually. If declaration kind equals declaration variable, equals function, we just do this, and we're gonna update this list pointer. So if it's equal to variable, list is equal to the scope variables list, and this is an address. Functions. And if the list is equal to 0, which basically means we have not set it, this hasn't been happening, then we're gonna error. All right, so now we have the list. Let's do this. Declaration is horrible to write. Okay, so now we have a list. We're just gonna push this declaration on the list. So list add last. We're gonna add this list node to the list. And that's it. Let's assert that both the declaration and the scope are something. Will the live stream be uploaded on YouTube? I don't know. Possibly. I never uploaded stuff on YouTube before. But it is available like a few days after I've streamed. I can probably like tag it with something in Twitch and it prevents Twitch from deleting it for a while. I think I can do that. I can try to do that. C is good, but I'm not sure whether it's because they got a lot of things right when it was designed or because it's a lot of tooling around it. I feel like it is very similar to how the computer is executing code. So that the compiler needed to be simple. I feel like that's like it is very similar to assembly. Like you just know what the computer is doing when you write C. That's the thing which is great. Yeah, that would be great. Yeah, okay, nice. So assuming we have a declaration, we're gonna push this declaration to scope. And I'm gonna get the current scope from parse the current scope. And we're gonna push this declaration on scope. And this is a void. All right, so assuming we can parse a declaration, which is gonna be this structure here, we know we can push this on the scope, which means that the scope is gonna contain the correct variables and structures in these lists here. Also, because we have these functions here, node enter scope and exit scope, we know that we can dynamically like iterate through all the scopes, which is very good. Thank you for following, guys. Welcome to the stream. I wrote scope wrong. Where? Oh, thank you. Thank you very much. Okay, I think that's good. Now we can actually start the parsing. So we're gonna make a function which is parsing a declaration. And if that declaration happens to be a function, then we're gonna parse the body and stuff like that. So let's make a test here. And then we're gonna have what we had like previously. We laid some variables and minus something. Let's have a declaration. No, let's stop with a declaration. So I'm just gonna have this. All right. Something like this. And we're gonna parse this. So when we call this function, we have a lexer, which is contained inside the parser. We have also a token. We have a token. And this token will point to the first identifier here, the first token, which will be main. And now we're going to parse the declaration. So what we have to consider, we're going to check if this is a colon, which is mandatory, and yeah, really if this is a colon. and then this can be a type or something. We're gonna at least check for, like this has to be an identifier and this has to be colon. So what we're gonna do, we're gonna make two tokens. One is called token and one is called next. And we're gonna peek the next one. So we're still at this token here. Because that's a declaration. We also want to parse comments here. So comments will be injected in here and in the compound statement. What happened to that ARM OS you were writing? Did it get finished? No, it didn't. Like the last OS I did, or tried to do, I didn't really, like it's working. I have a TFTP bootloader. Like all we did was a TFTP bootloader. Some, yeah, some simple stuff. I think it was like 600 lines or so. But then I started with a compiler, and then I didn't want to write anything more in C. So I'm stopping with the different projects before I'm having this compiler actually working, because then I'm going to switch to this language here. Yeah, chat is being the best spell check ever. Very nice. So if the token kind, remember we're tracking identifier as well, is if this is not equal to an identifier, or next kind is not equal to token colon, we're gonna return. Thank you for following, by the way. Actually, we're gonna check a few more things. We're gonna check if next let's just do two things here. So if the token is not equal to an identifier, we're gonna return, we're gonna have an error. Or we're gonna return 0, I think. Because we might have a comment. So maybe we'll have a parse comment up here. If this is not equal to identifier, return 0. And if next kind is not equal to token colon and oops. It's not equal to double colon, because we might have a typed of as well. So as long as they're not equal to colon and double colon, I'm gonna return 0. So here we have a new declaration. There should be a declaration here. And we don't have a new declaration, so we're gonna make that. And a declaration might be multiple things, so I'm considering returning a void pointer. Let's just do this. New declaration. A declaration might also take in some parameters. And this is really the only place where, what is it called when a function can take multiple types without being called multiple things? I don't know the word for it. But that's where that come in handy, I would say. Function overloading, yeah. Okay, so we're gonna We're gonna make a new object here. We're gonna say declaration. Do we have a list? Function kind, no, we don't have a list. We're just gonna return this. So we're allocating a new declaration here. And as we know, the first token is an identifier. So we're gonna write into the declaration that the identifier we know. So we have the name basically. We have a name token and we have a name. So the name token is gonna be a copy token from this one. Remember, the token here is the current one. So this will be the identifier. And this token only lives inside Elixir. And it's in a tiny buffer so we can look ahead some tokens and look back some tokens. So we need to copy this one. That's why I'm calling this function here. So we're gonna copy from token, and then we say the name is equal to token string, like token name. And this is just reference into the file. So now we have a declaration name, and now we need to parse. Now we need to figure out what's on the other side, like what is after this colon here. So first of all, I know this is a declaration, so I can skip this one and I can skip this one as well. So I'm gonna call skip token, and I'm gonna skip the identifier. I can just do next here, but it's nice to have, this is making the code look it is making the code easier to read because the reader knows what I'm skipping. Skip token, this is either gonna skip the colon or the double colon. And we probably need to check that as well. So we can make a bool is typedef. That is equal to token, that is equal to next. Kind equal token. What did I call it? Colon, double colon. So if the next kind, so next one is this one, if that is a double colon, it's a typedef. And then I can successfully skip these things. I'm gonna just say next token here. And we're gonna comment what it is. Okay. That's a really good idea. Thank you. That's a really good idea. I can say next kind. I didn't think of that. That's so cool by streaming. You can get these cool ideas. But actually that makes less sense because then you have to know like what is next kind. You have to go up here to look like, oh, that can be a token or a double colon. It is more expressive like this, I think. But that's a really good suggestion though. I like that. The LLVM output arm, it output basically everything, I think. Will you do code generator by yourself or use something like LLVM? We're using a generator by ourselves. So we're going to be generating code for this today. Weren't you the streamer making the ARM kernel? Yeah, kind of a kernel. I don't know how good it was. It could do a context which I could load processes to it in like its own memory spaces and making a standard library, some syscalls, but that's pretty much it. I'm gonna be making a new one in this language, and that's gonna be better. Probably run slower, but be better. Manage respect for people programming big applications in low-level languages. Yeah, but I think this is a like. I don't really fancy high-level programming languages. It is just my opinion. But it depends on the use case. Python is great for something, and it's probably not great for other things. You know your pointers. Yeah, you have to know your pointers when you're programming C. I know assembly language. I'm better at it for ARM. But kind of, it is gonna work. This will always fail, I think. What will always fail? Make a compiler. I don't like compilers. Okay, so we're basically skipping both of these. So that if I do now current token, that will point to the function, this name here. Actually, this will. I'm just gonna do this. And then this last token will point to the function. So now we're gonna actually check what kind of type we have. So I'm gonna check for the function type first. And then we're gonna have all the other types. Actually, we're gonna just parse a type here. No, because this is not really a type. That's the problem. I don't know how to interpret a function. I'm gonna fix that later. We're just gonna check for is keyword. Is this the keyword function? If that is the keyword function, you have to parse the function. And then you have to do all the other cases. And this is like, it is pointing here. Okay, so we have to track if it's an infer type. We don't have infer type just yet. So I think we're gonna add it now. Just so it's there, you know? So a type might also be inferred. Inferred. An inferred type will... Okay, we're going to represent an inferred type as nothing really. This is... I don't think we need to have an inferred type there. We're just going to mark it as inferred. It is going to have a type and that's going to be inferred. Because we only want to know that it's an inferred type. So we might use a little bit more space because we're using a type which is not really used. But I think that's going to go fine. Inferred. And it's inferred if the token assign. And we don't have token assign yet, so we're going to add this first. So we're going to go into Lexer. We're going to add the assign token. This is just equal. And this is after greater equal. So after greater equal, we're going to add assign. And then we're going to go up to the punctuation parser. And we're going to check for equal. So if it's equal and the next one is equal, we're going to skip this one. Else, we're going to skip the punctuation Lexer one character assign. So if this is only an equal and the next one is not an equal, it's going to be an assign token. Yeah, we put assign at the end. So this is an assign. And here I'm actually gonna backtrack. Wait a second. The declaration is gonna, because we need to know, like, a declaration might also be an expression, like an assign statement or something. So we need to know what to do with that. So since we can backtrack now, we could do something like, no, because it's this is not really equal. In C that would have been simple. So I have to sort of return the expression if I have some kind of initialization here. So if I have like data is equal to like some variable, I need to do this in that function here. So then there's the question, what is this going to return? Parse a declaration. So what's happening? This is on the scope. If this is right up here, I need to insert the data equals test in that current scope, in the compound statements. So parsing a block is really parsing a compound statement. Like, how are we going to do this? Like, parse block is really just parse compound statements. So I think this is going to be compound. I'm going to rename this to parse compound statements. All right. So a compound statement is having this open curly and close curly. And then this block is going to be the same thing. It's just like without these opening and closing curly brackets. So here I'm actually going to return not the scope, but I'm going to return. And again, this is not going to return the scope. This is going to return the compound statements. Hello, thank you for following. Hexadecimal integer. Welcome to the stream. Are we going to return a statement here? In fact, a compound statement. Returns a compound statement. So this will be a statement parse block. That's going to return a statement instead. And now we have to know, like, I'm parsing a block here. This is returning a statement. But a statement, if that's a compound statement, we also have a pointer to the current scope. So this will actually open a new scope, and we're gonna allocate a new compound statement here. Like this. And then we're gonna say that the compound scope equals scope. I'm gonna say make a new we're gonna link the current compound statement to the current scope. So we're entering this one, and this new compound statement is gonna point to the scope here. So in other words, I can assert that this statement is a compound statement, and if that's the case, I can also say that code unit global scope, like the global scope in the code unit, is the statement's compound scope pointer. So this is just making it simpler to access the global scope, and I like this. Why does everything need to be a function in a C thing? That's kind of how it works. It's that's just how it works. It makes sense if you think about it. Statement missed the okay, thank you very much. There we go. So now this is returning a statement instead. And it's returning that statement. And here we're making a new compound statement and linking this. And we're having a new declaration here. So this is either gonna parse a declaration. I'm actually gonna move this. A declaration is kind of a statement. So yeah, for sure this declaration need to like return something. This declaration here. So when I'm parsing this, I have to return the init expression if it is any. So I'm gonna return an expression. So I'm just taking that in as a reference. And you know what? I'm just gonna push the declaration of the scope here. So I'm returning a bool because I now have to know if this is failing or is successful. And then if this is true, it might or might not return this one. Let's just see how that's going. So we're setting it to 0 by default. If it's a sign, we don't really need to check this because it might be an assign after the type. So we can't check that here. We're gonna check for the type though. Might have a function like isType or something. Anyway, like after this function, the token is pointing to the token is pointing to the token after this. So each of these functions here need to move the pointer. Okay, so after we have parsed the declaration, we're gonna check if the current token is equal to equal. So if current token is equal to assign, then we have an equal. So if we have an equal, we're gonna make a new assign statement. So we have to make an assign statement. That is really just a binary expression. So I'm gonna make a new binary. And the kind, binary kind. Isn't that supposed to take in the binary kind? That is supposed to take in the binary kind. I'm gonna take in the equal to kind. And then I possibly have to check that all over the place. But we're gonna make it a sign. So binary. We don't have a sign yet, so we're gonna make a sign first. So that's in the tree. Binary plus binary kind count. So let's make it here. Binary assign. So now we can use that. And I'm also using binary expression once, one other place in the parser, which is in the main expression parser. So this would be kind here. Okay, so going back here, we need to set the kind because this is going to be an assign. As sign. And then what more do we need? We need the operator. So this is an assign operator. And this is really the token assign here. So I'm gonna copy from this token there. And the left hand side is an expression. And now we have to consider what the left hand side is going to be. So when I'm writing something like this, or let me use a number instead. This is really going to be first data is this, and this is going to go on the scope, of course. And then we're going to assign data to 4, 5, 6. So this is being handled, like this is happening up here. And this is going to happen up here. And then we're checking this equal sign. Thank you for following, by the way. And then we're checking this equal sign. And if this is in fact equal, we're going to construct this here. So I need to make this. That's what I'm doing now. So I'm going to say that assign left. And this is supposed to be a primary expression. So I'm going to say new primary here. New primary. Don't I have a new primary expression? I thought I had that. Oh, I'm just using new expression primary. But this primary needs a kind. So I'm setting the kind here. I'm probably going to replace this with just a new primary expression because it's a little bit cleaner. So I'm going to allocate a new binary. The same way I'm going to allocate a new primary. And this wants to take in the binary kind. Primary kind. So I want to make this function. So first of all, I'm allocating a new expression here. And the expression type is going to be expression primary. And then we're setting primary kind equal to kind and returning primary. What language is this for? This is for like just for something for myself. Like something very C-ish. Have we done a function that evaluates an expression yet? We're going to be using stack for that. We're going to be using that, like, we're going to be doing that very soon. But I know it can parse expressions. So I just have to make the variables work and assign the stack frame and function names. It is not very hard to do. It is just a little work. But we're going to be done today with variables and perhaps pointers. Compound statement. Where was I? Thank you for the follow, by the way. I was doing something with primary kind. Yeah, we're not setting a primary kind here. I should be setting primary kind here. I don't know why I didn't do that. primary number. So that is actually fine to do here because I don't need a primary kind. Okay, we're copying the token. So I'm gonna just comment a little bit. If the declaration okay, so do global scope. This might not be the way we want to do it in the global scope. So we only have to track that. Assign left. This is going to be an expression, and that's going to be a primary expression. New primary. I'm actually going to make a new primary expression up here. Primary identifier. I'm using identifier because I need to save the name here. I need to store this one. And primary is equal to identifier. We're gonna do the primary first. So we're saying that primary kind is being set. This is a token. And we need to set the name as well. This is the identifier name. And we're just linking this with the primary. And please ask if something is unclear what I'm doing now. So primary token, that's the data here. So in fact, the declaration looks like this. So that's the data token up here. The declaration name token, and that's already copied, so we can just use that pointer. So we're going to be using the declaration name token for this, and we're also going to be using the declaration name for the primary name. So they are the same, and that's fine. And then you assign the operator, which is the copy token, which is the equal, just so that if we have an error, we can always print the expression here. And then the left-hand side is just going to be this primary expression, which is the data, and the right-hand side is going to be this expression here. So I want to parse an expression statement. And I need to make sure that the lexer is pointing to the first token in here. So now it's pointing to the assign token. So I need to move the token, the pointer one step. Copy token. We're going to do it before here. Skip token, lexer, token assign. So we're skipping this assign token here. And then we're left with the expression, and we're parsing this. That is going to make the token point after this last colon here, which is fine. So this is if we have an expression, and if that is the case, I want to say the init expression equals this assign expression. So this is the one being returned from the function. All right. We still need to return the actual value here. Yeah, okay, so let's start with the function actually. We need to parse the function. And if it's a type, we're gonna parse the type. Yes, we're handling this and we're handling... So what is a double colon? Then it probably should be also parsing a type. But you can't really parse a function with a double colon. That doesn't make sense. So I'm gonna say if this is a function and is typedef is equal to 0 or false, and not is typedef, then this is a function. Else if is type, I can just do else parse type. I'm gonna do else here. So here we expect that the user, or wait a second, let's do else if. So let's do else if token. Token is pointing after the colon. So else if token kind is not equal to token assign. Here we expect that the user, here we expect a type. If the assign would be there, it would be an inferred type. Okay, so if this is actually false, this will be like it's an inferred type. So we can probably do equal here. Let's do equal. So that's an inferred type, and then we do else. That's cleaner. So this is inferred. This is a regular type. Regular, and this is a function type. Does this make sense? Function, inferred, and regular. If it is a function, we're just going to return because you don't really have this. I'm going to return true. Yes, I'm going to return true here. Yeah, so I'm going to return from this function here. We have to make a new declaration and pass it onto the function list on the scope. What would you recommend for someone totally new to parsers? I don't know, just try. I was getting some inspiration from one guy by mail, so that helped a lot. But just see what structures others are using. The structures help a lot, and the basic idea. I think the basic compiler, like parsing ID, can be thought in an hour top. Like how a parser work. I don't know. But they should probably give you something, if I'm not completely horrible at explaining things, which I probably am. But I don't know. Yeah, okay, so let's start with inferred. That is simple. If this is an inferred type, this will also happen. That will also happen. And so if this is an inferred type, okay, so what we're doing now, we're basically linking, as I said, the declaration is a mapping between a name and a type. So we have to make that mapping here. So the declaration type is equal to new, and we need to allocate some types here. So the type allocator is going to be like new type kind. I don't know if we're going to do anything more here. We're going to start by doing this at least. So we're allocating a new type. Calloc. And we're just going to return the type, I think. So what I want to do here, I want to allocate a new infer type. And this is not going to have anything. This is just going to mark it as inferred. That's the only thing we need. This entire type run is going to be replaced in the later paths. I need to finish watching the first part. Oh, I see. YouTube DL. That's cool. Yeah, it should be like, I did everything this day and yesterday. We streamed for 10 hours yesterday. So if you watch that, you should be able to write this. Yeah, so this is a new type. And else, we're gonna try to parse a type here. Because it might be a type, it might not be a type as well. Because many places in this code we need to parse types. And we might not need to know, like we might not know if that is actually a valid type. So we're gonna make a function called parse type. It's gonna return a type, and this might be 0. So if not type, we're gonna generate an error. And what token are we gonna use for that error? I think we are gonna use, we can maybe use this one. We can maybe use that one. I'm gonna say undo next token from this lecture. It doesn't matter because we're gonna quit here. And expecting a type after the type or equal after the operator or something. Like we have to fix the messages here. So after this, we know that the type is right. Actually, let's not make the type. Let's say declaration type is equal to this. And if declaration type is equal to 0, then you do this. So that's the only thing you have to do. So the type should be something when you go here. Or, yeah, it should be something. So we can possibly just assert that the type is something. We need to make parse type. Static type. Okay, so the pointer is, I'm gonna say where the pointer is pointing. It is pointing here. It is pointing to the type. How much are we gonna implement there? Are we gonna implement pointers? It's a question how far we want to go with the syntax here. What if this is an array? This is a pointer to an array of 56 U32s. We probably should add that. So in order for us to do this, we need to have the, well, this, we already have this, but we need to have the square brackets. So we're going to implement the square brackets. Token open. Is it square? And token close square. I think those are the things we're gonna call them. And we're gonna go up here. Oops. We have to go into the list, otherwise we're gonna have a segmentation faults. And we don't want a segmentation fault. This is added after the curly braces. So we're gonna go in here, we're gonna add them here. Open first and then close. There we go. So if this is an open square bracket, you do this. Yeah, we're only tracking one of them. Token close square. So now this lecture is going to recognize these as well. So let's go back to the parser, parsing a type. So this function will parse a type, and it is currently pointing at the first token in that type. So you're going to first save the lecture, just so it's easier to type. And get the current token here. So now we need to think. We're going to do a switch on all the different types. So is keyword token keyword u64, you do something, and then we have an else if. This is because we need to compare the keywords, not the tokens. So this is not really a switch. And this is u32, u16, u8, there we go. So that's all the types. I'm actually going to make them global. I'm going to make them global. That's going to make it simpler. And we have the chart type as well. Chart type. What more do we have? Oops. Multiplication. So this will be a pointer. This is just a regular pointer. So I'm gonna say like pointer type is equal to new type, where the type is pointer, and the pointer is pointing to yeah, so what is this pointing to? This is pointing to a type, so we're going to recursively call ourselves here. Parse type, and we have to make sure we're pointing in the right place first. So the token here is I'm actually going to use eToken. This will get the current one, and I'm advancing the pointer afterwards. So the current pointer will actually point to the next token here. And if nothing of this is happening, I have to undo that token. Undo or something. So we're parsing a type here. And then we're going to track the array expressions. Open square. So if that token is an open square, then this is going to point to the index, like the number inside the square brackets. So 56, the token will now point to 56. Since I'm getting the current, since I'm eating the token here, then the current will point to after the square. That's some original syntax. That's not my syntax for it. I know both Go and J is using the same syntax. But it makes it really cool to read. Like, I want a pointer to an array of that. It makes it really clean. Also, function pointers are the same. It's going to be a pointer to function whatever. Will we do tuples? We will do multiple return values from a function. So I don't know if that requires tuples. Maybe. It is going to be for 1 byte ASCII. For now. Maybe there's going to be a data type for Unicode. Like uni or something. A uni keyword. So here we're actually going to expect a token. Instead of doing the current token, we're going to expect a token. Actually, because we're already getting it. So I have to first use it here. If token kind is not equal to number, I need to say something that I can't evaluate constant expressions currently, because we cannot. Something like this. So at this point we know we have a number token. So we're just gonna make a new. Actually, let's just make a new pointer type. Type pointer. And the type count, which is the U32, is gonna be the token number. And the type pointer to, let's first skip the number. Skip token. Number. And we're going to recursively call parse type. All right. Yeah. So I'm going to return a type after this. Return a type there. Return a type there. If this is the case, we're going to return 0. If it is none of the above, return 0. But that might be fine. But first we're going to undo next token. That is going to undo this eat here. Do I have a token? I don't have a token. I have consume token, which is the same. And then I'm gonna make some types here. And this is a type pointer. Yeah, so type U64, that is going to be the address of a type pointer. Fuck, you can't do this. Can you do something like this? Or use this is supposed to be a type. There you can do it. So we're making this a type and then you take the address of that. So kind is equal to token basic. The alignment here is 8. The size is 8. And the basic is signed is equal to false. And the kind is basic pointer size basic align. Okay, I think we have everything now. Let me just do this. So this is the object for U64. That's for unsigned. This is for signed. This is for char. And this is a new type. I'm gonna make a new function for this because this is really a pointer. So I have to assign the size here and alignment as well. So I'm actually forced to make a new pointer instead. So new type. Oops, there we go. So new pointer. This is just going to return a new pointer. It is almost the same as a type. So we're going to first allocate a new type. And this is a type pointer. And we need to set the size here. So depending on the architecture, you can change this number. So by making a new function, you're only going to change the number one place. Size is equal to 8. And alignment is also equal to 8. Thank you for the follow. Thank you for the follow. Welcome to the stream. That was me. Charity 4byte. Yeah, the space is I don't like since I haven't used this language before, I have to like develop my own style of coding in this. So I'm not sure I want to code it like that. Yep, remember size modulo alignment is equal to 0. Yes, that is important. That is really important. Like the reason I have the size here is because when we want to do structures, then the size and alignment is going to be different. And the unions and yeah, then those are going to be different. It is not very hard to compute those, but it's just going to be different. So I need to have, this is supposed to return as pointer type. Let's return this as well. Dang it, fuck that. Just gonna return a void pointer. That is probably bad, but I don't care. New pointer. So I'm gonna say new pointer here instead. and here as well. And then I don't need to set the size or anything. Okay, so we're getting the size here. Skip token number. We're jumping past the number. Then it will point to the closing bracket, so we're going to skip that as well. So skip token, lexer, token, close square. So we're skipping both of these. And then we're recursing down here. Let's do this. Alright, this might also be a size pointer. I'm not sure if I'm gonna do like dynamic erase. Here we're gonna return and the type casted to pointer. I'm gonna rename this with pointer. Pointer count, pointer, pointer 2. And return this. I need to cast there because the function is supposed to return type, while this is a pointer type. It is the same matters though. So now we need to just fix those. The alignment here is for, let's fix the names first. Thank you for following. Welcome to the stream. I'm having more and more delay between thank you for following and welcome to the stream. I should try to achieve the same delay between what I'm saying there. All right. So alignment on the char is 1. The size is 1. The basic is signed is true. In fact, all these are true. And then we have 8, 8, 4, 2, 1, 4. No, that's 4 and that's 2. So there we go. That's the types. This is the built-in types. Wait a sec. Actually, that's gonna also be something I want to do, because I wouldn't need this in a typer. Because now that we're starting to include types, we need to have a separate file where we're gonna type this tree, and we need to access this from the typer. And it doesn't make sense for the typer to include the parser. It makes more sense that the parser is including the typer for the types. Or maybe place those a separate place. I don't know. If this is a U64, we're going to return type U64. U32. Return type 16. U8. S64. S32. S16. S8, and for char we're going to return char. So these are just returning those built-in types. I'm going to in fact use one, no line between. So I think this is going to parse a type successfully. Like everything we're like with pointers, arrays, everything is going to parse that. So we need to check if this is a type. If this returns 0, it's going to be an error because we're expecting a type. So after this, the declaration has a type, and then we're parsing the init expression, if we have any. And then we return true. So is this really going to return false if we don't have a declaration? Like, when is this going to return false? Maybe we can just return the expression here, because this needs to be in a declaration. Why no void here too? Yeah, before I was using like the void pointer cast all the time because I don't know the. And that's the thing I want to include in the language. I want to include this autocast operator because I'm very tired of doing like data equals, and I have to type out something here, but I know that type is the same as this one. So I want to have an operator for like implicit casting between this and this one. So this will be casted to the same type of this, like kind of like cast inference or something. Yeah, that's gonna be great. But you can't do like, yeah, it has to have a type. So you have to know the type of data for that to work. Login search and insertion looks pretty good for types. We're gonna change that. It's gonna be, we're gonna use a hash table instead. So it's not gonna be login. Void is the definition of nothing. Yeah, you got it. Let's parse the function. That's the last thing we're gonna parse. Yeah, let's parse the function here. So the current token is the keyword function. Yeah, so this is pointing to function, the function type. So we need to, we're gonna allocate a function. And this is not really an allocation because the declaration is containing the function. So we're just gonna say, we're just gonna get the pointer. And then we have to fill in the body, the function scope, and the return types. Okay, so now we're gonna be a little bit smart. We're gonna open a new scope here so that all the declarations inside here is gonna go on that scope. So I'm gonna call parse declaration recursively, and probably I want to like avoid something here. Because when I'm parsing this from a function perspective, I don't want to have like a new declaration somewhere. So I can either make a new function or I can make some restrictions there. For example, I can say that I only want like function arguments, and then it's going to not allow init expressions, and it's not going to allow inference. It's really only going to allow this. Maybe we're just going to make a new function for that. I think so. Parse function argument. And again, this is taking in the parser, so we have access to the current scope. So we're just going to parse it on, we're just going to push it on the scope here. Do we have a push on scope? Yeah. Let's make a push on current scope as well. And this is just going to push the declaration on the scope, this declaration on parser current scope. This can be inline. Be right back. Okay. How do you differentiate between as autocast or comparison? Yeah, that was also what I was thinking. The autocast will only work here. So what we can do, we can make like this an assign statement. So this will only work if that's the operator. Like if you have a new statement, and this is a binary expression, and it's a something like this, then it's an autocast. Otherwise it's just gonna be something else. So as long as it's a statement binary, as long as it's the first binary expression, because this will be the top level. Or unless, wait a second here, unless this has higher priority than something else. If I have like or, then the parser might think this is going to be parsed first. Okay, so we might add some logic there. There might be a step before the actual expression parser, which is parsing like autocast or something. But that should be fine to implement. But we have to consider that. That's right. Will you roll your own hash map? Yeah, of course. There should be a hash map here. Like all the scope things are going to be hash maps. Yeah. So now we have push declaration on the scope. We should start to make these like define them up here. Push declaration and current scope, enter scope, exit scope. I think we need both of them because we're going to manually exit and enter a scope in case of a function. And parse declaration we're going to need, parse function argument we're going to need, and this is stupid that I actually had to do this. But I guess it makes sense if you want a single pass compiler. I think we have everything now. Enter scope. We need a second push declaration thing. This one. Okay, I think we have everything now. We can probably take the parse block and parse compound statement as well. I might reorder these a little bit. All right. So parsing a declaration. Yeah, function. So here I want to open a new scope. So basically I want to manually open a scope when I parse this thing, and when I call parse compound statement later, because when I want to parse this, that automatically opens a new scope. So this is going to have two scopes, one for the argument 0 and one for the body. Enter scope. Parser and exit scope. And inside here we have to parse the arguments, and actually this entire thing. So we're going to start by parsing the command line arguments. Lexer is equal to parser lexer So we're getting the current one. Actually, we're also getting the next one. Peak next token. You know what, we can actually eat both of them. We're gonna like eat. We're gonna skip. We're gonna skip the token. Well, let's say, how is that Lexer implemented? Like, how's the skip function implemented? Because I want to have the current token and I want to skip next one. I'm returning the next token here. So I do not really have a function for exactly that. What we can do, we're gonna eat the first one. We're gonna skip the next one. What happens if they are... Yeah, that's still gonna return end of file. So that's fine. Eat token, then you're gonna skip the token semicolon. No, just colon. Thank you for following me, by the way. Because you can't have a type def in a function definition. And then the next one is gonna be eat consume token, is it called? Yeah, consume token. So this is gonna give us like a function argument. It's gonna be some name followed by some type here. Okay, so we're getting the name, and this is consumed so that it will point here the next time. Here the next time. We're skipping the colon and we're consuming the next one. And then we're gonna check if token kind is not equal to token identifier, or this is supposed to be or. Now we have the next kind there. If this is not the identifier, we're gonna say like error. Wait a second, this is gonna parse a function argument. This is a declaration. Let's make a declaration first. That's gonna make it simpler. New declaration. And then we're gonna say the declaration name token is equal to copy token from consume token. So this is gonna copy and consume the current token here. Yeah, all right. And then we are skipping, we're doing this, we're skipping this, skipping the colon, and then we say type is equal to parse type. We're skipping the token and we're parsing the type. Yeah, so now we have the name token and the type, and now we're just gonna assert, so if declaration type is equal to 0, or declaration name name token is not equal to token identifier, then we're gonna error we're gonna error at Thank you for following, by the way. We really need two different error messages here. If this is false, you have like an unknown, like an undefined type for the argument. You're, for example, saying something like, I want data to have type something, or like percentage sign, for example. If this one is not an identifier, then this is wrong. So I'm just going to say if one of these are wrong, I'm going to give the error at the declaration name token. And I'm just going to say arguments argument error. And then we have to check what the error is. So after this, the token pointer is pointing after the type. So we just want to push this declaration on the scope. It is really simple, because we're going to force a declaration error. Do we need anything more? Yeah. So after this, we need to do declaration name, which is equal to declaration name token name. Just storing that so it's a little bit easier to access. Variable function, and this as an offset. Okay, perfect. We're just gonna return. We're not gonna return anything. So this is supposed to work. It is either gonna work or it's gonna return some kind of error. We still have to push it on the scope though. So push declaration on current scope parser. Declaration and parser. And then we're going to say while. So first we're getting the current, well, token is equal to the current token. So I'm going to say while token kind is not end of file. End of file, and is not equal to closing parenthesis. We're just going to continue to parse these arguments. So I'm doing parse function arguments with this parser. All right, and after this, we need to know, like, we need to check for this comma. So I'm going to say token is equal to current token of the Lexer if token. Okay, I'm gonna say if token kind is not equal to token close, is not equal to token comma. We're gonna make this one. If this is not equal to comma, we're gonna break, because the next token has to be a comma. So I'm gonna break here, and here we're gonna skip the closing parenthesis. I actually have to skip the opening parenthesis here. Skip token, Lexer token open, parenthesis. So now it's pointing to the first argument. Or, if it is none, it's pointing to this one. So as long as I do this, as long as I do that, this will be right the first time. So if there is no arguments there, this will happen the first time. And then I can just do skip token close parentheses afterwards. And then we're exiting the scope. Not yet. Let's make this first. I'm gonna add it here. This is a comma. After the arrow. So I have to add it. Wait a second. Why the hell is equal there? There is equal. Like this is supposed to be comma. And then we have to add it in the actual Elixir. So this is a function we use for recognizing different punctuation characters. So I'm just gonna add a new entry here, looking for the comma. Skip punctuation, that's Elixir. We're gonna skip one token, and we're gonna set the token to token comma. And break. So going back here, this is now valid. So we're breaking if that token is not comma, because it should be comma. And if it is not comma, it should be close parentheses. So I think this will work. And if the kind is not comma, we're gonna break. Otherwise, we're gonna say next token. We're actually gonna say skip token. We're gonna skip the comma here. Here we're checking that the current one is a comma, here we're skipping the comma. Parse the function arguments. Sorry if I'm just missing something. I just joined, welcome. That isn't gonna conflict with less or than equal. Yeah, that's right. So we have to restrict the scope of that operator. So we have to like say if it's we have to be careful when we use it. That's the only thing. You can't really have a like if you think about it. Let's do this. Like in C, this will evaluate to, let's do numbers instead. This will be like 1. So 1 is going to be in the register racks in my current implementation. And the same way, this will be like evaluate to 1. Because it's an assign statement as well. It is not really just, okay. Maybe we can choose a different operator. Like this is not going to have any problems. But I don't know if I like that. Like data. How's it gonna be like? There we go. Something like this. I don't know. We have to see. Wow, what a progress. Yeah, I've done it before, but I wanted to clean up the code. So I just decided to do it on the stream instead. Skip token raises an error if the current token is not equal to what I'm skipping. So this asserts that the current token is equal to comma, and it gives us the next token, if that's true. Maybe we can do something like that. Yeah. Like that's an edge case, so I don't know if I want to introduce that. I want autocast. That's like, period. I want autocast. We just have to find a way of implementing that. So here we're parsing the function arguments. Yeah, I think this is going to work. And after the function arguments, like this is skipping the close parentheses and giving us the next token. So if that is token arrow, then we have this case. So then we're going to parse the return type, which I'm only going to allow one return type per now. If that's an arrow, we're going to skip the arrow. Skip the arrow. And then we're going to say function, which is up here, has a return type, and I'm going to parse this return type here. Parse return type. Okay, so there's a return type as well. And what more do we need? We need a function scope. Okay, so I'm gonna give the function actually the top level scope. So I'm making a function here, and I'm gonna say that. Actually, let's make this on the top here. And then we're saying that function function scope equals this new scope there. This one, which is the scope of the arguments. And then that scope is pointing to the next one, which holds the actual body. So we're setting the function scope, we're setting the return type, if any, and now we have to set the body. We're skipping the arrow, and we're parsing the type. So if I'm parsing this type, the pointer will point after this type here. So it will point to this opening brace. So here we can just type parse compound statement. And that's going to parse this entire thing. And then we're exiting the top level scope, or the function scope, and then we're returning true. We have to push this declaration on the scope though. Push declaration on. We're exiting the scope here, so the right thing will be to push it on the current scope. Welcome to the stream, Iron Spark. Thank you for following. So we're pushing this on the scope. We have to make sure we do this here as well. So here we're not doing anything with the declaration. So we're asserting that the declaration has a type, and then we're pushing declaration on current scope. All right. Okay, let's just go quickly through it. We set that to 0. This is just making sure we have a declaration. Have a declaration at all. And then we make a new declaration. We're assigning the name token and the name. And we're saying if this is a type def. We haven't used that yet. So this is a declaration. I'm gonna say, if this is if the next token is assigned, wait a second. We're basically skipping either this token or this token. If it is a function, we can't have a type def. And we can also see like if this is an assign and not this type def. So otherwise this is gonna happen. And we're adding a declaration here. So we have to set the declaration kind here. This is really a type declaration. No, this is a variable declaration. Declaration variable. Variable. Okay, so here we have to choose if this is a declaration variable or a type def. So here we have something like token, and we define that to be U32, or we might have something like this. So both of these cases might occur here. I'm going to use a variable instead. And if we have this one or this one, that's determined by is type def. So the declaration type, we need to make a new declaration type for type def. Declaration type. So we're declaring a new type there. And then we're going to say if is type def, this is going to be a declaration type. Otherwise, it's just going to be a declaration variable. So we're asserting declaration type, and we're going to assert declaration kind here, just to make sure, you know. Or maybe when you know variables exist, you can do variable equals second. So when the variable is declared, that's an interesting thought. We might do that. We might do that. That's a good thought. So we want to have some foreign how do you pronounce that? I've never pronounced that word in my life. Foreign function call, in which case it won't be a function body. No, we're not gonna, I don't think we're gonna have that. Yeah, I don't know how to pronounce that. Probably just check it out. No, I don't think we're gonna declare a function. Oh, like a for, yeah. Well, syscalls isn't really that. I'm gonna like the one of the things I don't like about C is the inline assembly stuff. So I don't know with x86, but kind of you have to write assembly to get the syscalls right. So I will like have something, for example, alloc. I'm gonna write a normal function. So I want to write it like this, but this is not really a function, this is an assembly function. So I want to write like ASM here. And it takes arguments and return arguments. This only tells the compiler what to do. And if we want to have like inline assembly and stuff like that, you can just inline or something. We can fix that later. But that's easy to change. But here we're basically telling the compiler what it's supposed to take in. So for example, like U32 and U32. And then you should be able to write normal assembly inside here. So this is going to require the parser to be able to parse assembly code. So in ARM, I would probably place, like, how do you do assembly, like syscalls on ARM? I've forgotten it. Is it like, I've done this before. It's an instruction. It is an exception you actually call. I think you call SVC. I think you call SVC and a number. So for example, number 3. And you, for example, move R4 into R2 or something. I want to be able to do this. So writing an assembly function is just like writing a normal function. You just write assembly. So I think this should work. So that will be the system call. You just do this and SVC number 3. Yeah, I think that's foreign function. All right, foreign function. Thank you very much, foreign function. Define a custom assembly that can be translated to another standard assembly. That's also a good idea. I will consider that. That's a good idea. Foreign. Okay, I think I got it now. So here we store this, and this is fine. I think actually this will work now. But let's just check the function once more. So we already have the function name, and we're getting the pointer here. So we're opening a new scope for the arguments, and we're allocating a new function, or we're getting the pointer. We're setting the scope, and we're skipping the open parentheses. We have to skip something before, because this is pointing to function, and yeah. So this is actually pointing to function. So you're going to skip the function call first. Skip token. I'm actually going to do the next token here. Lexer. Yeah, just Lexer. I'm going to just comment here. Skip the function keyword, and then you skip the opening parenthesis. You're supposed to have one, and while not end of file and not closing parenthesis, you're just doing this. So either of these will fail, and then it will expect the closing parenthesis there. Otherwise, you just parse the function arguments, and they're going to be pushed on the current stack. And you get a new one with a comma between. Sounds good. Skipping the parentheses, and you check if this is an arrow. I didn't like that. Yeah, and you push the declaration on the current scope. All right, this is a function declaration, so it's exiting the scope first. That's looking really good, to be honest. And we're return true here. Are we really returning false somewhere? If not, we're just gonna delete this. We're just gonna return that expression there instead. Yeah, so this will always succeed. And if this is returning 0, oh, it returns fail there. Okay, I'm gonna have it like it was. That was why. This is probably gonna fail anyway, because we have to have some kind of declaration there. So this returns true. I'm gonna just write it. Otherwise, it just returns 0. Like I'm talking about this one. Seems good. So this we're calling. Where are we calling that one? We're calling this in the parse block. So this is going to parse the declaration. This is not right, because the block might be this as well. So this is a block. I'm gonna write it like this. This is a block, and you want to be able to parse like statements here, expressions, and or declaration. So this is gonna be parsing we're not gonna do this. We're gonna be parsing statements here. Do we have a statement parser? I think it is there. And this is returning a statement. And since this statement parser has to include the declarations, it might be that the statement doesn't return an actual statement. So we're gonna check if statement is something, and if that is something, we're gonna add it to the scope. No, to the compound statement. So if the statement is something, we're gonna do list add last. We're gonna add the statement list node to the compound statements up here. So this is parsing a block, which is a compound statement, and we're just doing this. And we might also like restrict the access there. So for example, if this is the top level scope, you just like you give an error if this is happening. For example, yeah, probably give an error there. We'll have to see that. Yeah, we can probably mark an expression as an init expression or something. It's very easy to fix later. We must track if we are in the top level scope or global scope. The G sound, foreign. Parse block is now working. So now we have to make sure a parse statement is actually like handling these declarations as well. So this is happening if this is a compound statement. And then we're going to try, actually I'm going to call it try parse declaration. So it's going to try to parse it. The second thing we're going to do is we're going to try to parse this. Wait a second. This is not supposed to return an expression, because if you think of it, this is supposed to be, this is an equal sign, so this is a statement actually. So this is going to return a, this is going to return a statement there. In its statements. So init statement is equal to, it is really just a sign, but we have to make a statement of it as instead. New statement. This is an expression statement. And the kind is that the expression is going to point here. Oops. The expression is going to point here, and we return this instead. Statement. This is basically the same thing, it's just making the API a little bit cleaner. What language is this? This is something custom. I want to make my own language. Okay, so parse a compound statement is going to parse statements. And a statement, so we're going to make it here. This is the way it is. This is actually dynamically allocated. This is going to return a statement pointer. And this is actually wrong, because this needs to be a double pointer. Yeah, I'm going to make the double pointer. So if you dereference a double pointer, you're going to get the pointer. So this is a pointer. So now I should be able to say like statement pointer, and we're going to say if try parse a declaration, and we're going to give the address of the statements, so that if it succeeds and the statement is something, we have some kind of initialization expression. If that is true, I can probably do this, but I'm going to do it in a separate thing here. And statement, we're going to return the statements. And this is returning a statement. So this might also return false, because if this is failing, it should either return 0 or because this might fail. This might not fail, but if it, for example, if you parse a statement and that statement ends up being a declaration, for example, then it's not a statement. But sometimes you want to just parse a statement and force it to actually be a statement. So actually what I want to do, I want to make a new function. I'm going to make it static. This is going to return a statement. This is going to try to parse either of them. So try parse declaration or statements. This is going to try parse a declaration or a statement. So what I'm going to do, I'm going to say if I'm gonna try to parse this declaration first. And if that is succeeding, I'm gonna return the statements. Otherwise, I'm gonna return 0. So it still succeeds, but it's not returning anything here. So this will still be a valid return code. And then, if that's not happening, I'm gonna force this parse statement. So this will always return something. And if this fails, I'm gonna return an error. So this is gonna force it to be something. You can see that it's actually parsing an expression statement there. Yeah, parse declaration. Open curly. Okay. Return parse expression statement. And then we add the try parse declaration or statement. This is also a static one. Thank you for following, Oliver. Welcome to the stream. And we're going to use this one instead. So enter scope, push declaration scope, parse the block. We're going to use this one instead. We're going to try to parse a declaration or statement. If that yields a statement, we're going to add it to the list. If this does not, that means we have pushed some kind of declaration to the scope, but it's not really an expression or a statement. So that's also fine. So if this might also fail, but then we're going to get the actual error code. So that's good. I'm very happy with how this looks now. It's going to need some commenting though. But I don't know if you notice it, but I've actually been inspired by the guy named like JBlow or something. And because he's typing out the words, and that is not really his thing, because when I started coding, I was coding the exact same way I'm coding now. Like when I started coding, I was really like making fun of people who did like use abbreviations and stuff like that. And then I saw like Linux code and was, yeah, you can say like a little bit moved. And I started to make like shorter names and stuff. But I guess I get back to what I was originally doing. And if you like look on code I've been writing like a few years ago, it is exactly like this. So I think this is better. And like you don't need so much commenting here. Like this is parsing a compound statement and making the lexer, you're skipping a token open curly. You don't need to write like you're skipping a token there, because the code is so expressive that you don't need to write it, in my opinion. It is very easy to see what the code is doing here. I think. Let's do this. Oh, that's not so many errors though. Passing argument 2 of try parse declaration from incompatible pointer type. Okay. So this, I probably have a declaration somewhere saying that that's a single pointer, which is a little bit stupid. Try parse declaration. This is supposed to be a double pointer to the statement. There we go. Error token, implicit declaration of error token. Parser 244. That is not really... Oh, I need to include error. That's that one. And parse expression 377. How do I go to like 377? This is an expression, and this is an expression statement. Assign rights. This is not really an expression. This is going to be parse expression, and then we're gonna check for the ending thing, because normally, like what was there originally, whoops, was like expression statement. So an expression statement is something like, I want to have like something equals something, or probably like plus plus something. The thing is that you're not really doing this. You're constructing this tree node by yourself. So there is not really any function for getting an expression and a semicolon. So we have to track that yourself. So you're going to just parse an expression, and then we're going to skip the semicolon. Okay, parse expression needs to have an initial priority. So we're using like a recursive parser with like priority tracking. So I have to give this priority -1. So this is basically using this running priority to determine if it's going to recurse or not. So by giving it -1, it is going to force it to not recurse if it goes out to level 1. So if the nesting level, or if the recurse level is like 1, so it's the original function, this is going to make sure it doesn't return. And I call this init priority something. And it's really a tiny function, this parse expression. It is only this, literally. Parse compound. Am I parsing that 2 times? It seems like I'm parsing it 2 times. Oh yeah, I actually am. Parse compound statement up here. Let me just get rid of this one, and I'm gonna copy it down. So we're using this parse compound statement here instead, which is really just parsing a block. So just have to compare these. So skipping open curly. Okay, so we're not doing that. This is gonna skip the open curly, okay. And you're allocating a new compound, we're doing that. We're linking in the scope, and we're doing basically the same. So we can delete this. Okay, it works. So we have expecting something but got the semicolon there. This is just trying to start the, like, what am I generating now actually? I'm generating this. Okay, I'm generating nothing. So I'm trying to run an empty file. So that's the last error. Let's take a look at the program we're gonna try to parse here. Let's make something valid. And this is the main function. We initialize a new lexer, new parser, and then we parse the program. So I'm getting expecting semicolon but got a colon. So that's not right. So we have to figure out what this is. And by the way, why the hell is this 0? Why is the starting line 0? I thought I changed that. This is gonna start at 1. The line is gonna start at 1. I don't know why that happened. There we go. So it's expecting a semicolon after this one, which is a little bit strange. So we're just gonna trace down where the problem is, starting here. So this is gonna parse the entire program, and we just have one code unit now. So I'm just gonna parse the first code unit. And that only contains one single block. And a block is the same as a compound statement. It just doesn't have this like curly braces. But it returns though, I think. No, it exits here. So we're parsing a block. This enters a new scope, that's fine. We're making a new compound statement. Linking it with a scope. We're getting the current token. So in this case, this will be like main. We can say this is main. So that's main. And then we're checking if that's not equal to end of file and not equal to close curly. We try to parse a declaration or a statement. So this will try to parse a declaration with this parser. So this is happening first. So this current token will also be main. That will also be main. And it is. And then next we're going to pick the next token there. If that is not an identifier, we return false. If that is not colon or double colon, we return false. And then we make a new declaration, which is the function declaration. And we're copying in the this is the main token, so the main function name. And we're just checking if this is a type def. Is this colon or? Yeah. Okay, let me check what this next area is. That's supposed to be a colon. That's a colon. Okay. So we're skipping the identifier. Like it's already, let's see here. It's already pointing to main. So this will make it point to, this will get the next one. It didn't give me anything. We're expecting something before that. Maybe some of these are returning. If that is not equal to, this is actually supposed to be and. Because it can't be, like it can't have them both. So maybe this is wrong as well. Parse function argument. Yeah, we're skipping the token there. You're skipping a colon. Okay, so I think that was the issue. Okay, so declaration kind failed. So this fails. We're saying declaration kind. Why the hell does declaration kind fail? Wait a second. The declaration variable is 0. So we can actually start at So we have a declaration error there. That should work. Declaration type is not handled. Okay, so we have a type which is not handled. So we're getting some kind of thing which is not handled. A declaration kind. That is if list is 0. And that's right. Remember we supported the typedef here. So we're actually going to support typedef. So if declaration, if that is the declaration type, we're going to add it to the list types. Thank you for following, by the way. Oh. Else the declaration kind is equal to declaration type. What? Isn't this working? So a declaration kind 0. So this is probably because of this one. So when we make, yeah, that makes sense. So when we parse the function arguments, that's a separate function that's up here. So we have to make sure this is not gonna fail. So we can just set the kind equal declaration. What are we going to use here? Declaration variable, because this is a variable. So it's parsing a whole lot, and we're getting the error message. So this is actually right. It is expecting, what the fuck? Yeah, it's expecting this one. It is expecting an empty compound statement. And that's because of the expression statement parser failed. So it's expecting a semicolon. Yeah, because we're gonna allow a statement. We can make the error message a little bit more clean, I would say. But that's fine. And got the kind, we're gonna remove that printing here. All right. It is almost working. Let's do this. So let's see if it can actually handle these complex types. It says declaration type is not handled. Are we getting 0? We're getting 0 there. So something which is calling this is returning, or this, which is just here. And this has a declaration kind. And this is not 0. We have to mark this as, okay, this is the one which is failing. This is happening if we're going to push this entire function to the scope. So in case this is a function, we're going to say that this declaration is in fact a function. Okay, nice. That's it. And it's parsing the program. I think it's going to print it. I don't know why it doesn't say that. It is parsing a program. We have an assertion. Statement kind is equal to compound. That is line 468 in the parser. 468. Day 2, I'm sorry, I didn't check chat. I was so in my own world. Yeah, I started like yesterday. This is luxury, yep. I don't think there's a valid argument for abbreviations in a world where you have autocomplete. No, I don't think so either. I mean, there are so many books which is telling that you shouldn't comment in code and commenting is bad and the code should explain itself, and I actually agree. The problem with Linux is that it doesn't explain itself, in my opinion, and Unix tools in general. Like, yeah, 2-letter words, 3-letter words, they're just so hard to understand. But if I'm writing code like this, I feel like I don't need much commenting here. I'm gonna of course add a little bit, and there is some places here where the algorithm is a little bit like complicated, so I might explain that a little bit more. So when I get back to this project like in a year, I can just really comment and understand like how you should think about the code. That was a function. Where was the assertion again? The assertion was at line number 468. 468. Oops. Okay, so we're parsing a block, but we don't get a compound statement. So this doesn't return a compound statement. And the only thing we do is add a new compound statement. So this is adding a new statement, and this is setting the kind. So this should make a compound statement. I don't understand why that doesn't work, unless I'm not returning though. So I'm gonna return a statement pointer, which is the compound statement. This is the same address as this one. I'm just casting it to something else. So now it should work. And I'm printing the program and I'm generating the program. The reason it doesn't work to print is that I don't have a function for it. So now we're gonna actually try to print this thing and see if it works. And then we're gonna have a little second pass. We're gonna do pass number 2, just typing out what we don't know. And then we're gonna generate the code for this. So now it should be able to like parse anything like, let's say if this is also working. This is an inferred statement. That should be working, and it is. Hopefully, we don't know before we have printed the thing. So this is the current printer. I should actually have the, do I have the stream from yesterday? I'm actually gonna go in here and see if I have the stream from yesterday. Because we did make this, so it's easier to like understand once you see an example. There we go. So where is the printing here? I guess it's here. Yeah, something like this. It might be hard to see though. I hope you can see this. But what we're gonna do, this is printing the tree. So we're drawing these lines downwards. And sometimes you want to draw these lines and sometimes you don't. So here you don't want to draw these. So what we're doing, we're keeping like a mask. So each of these indentation lines, this being 0, this being 1, and so on, has like a Boolean value if you're going to paint that line. And we also have one global variable which is going to track the indentation. So here the indentation is 0, here the indentation is 1. So we're tracking the indentation of the what we're writing here. So not the indentation of like this line here, but of the binary expression. So if I want to, for example, paint this one, I have to say like binary expression indentation -1, -2, I mean. So this is -1, -2. So that's how it works. It's going to look something like this. So that's currently working. We're not going to deal with that now. How about compiler warnings? It should find missing returns. Yes, that's going to go in a later pass, I think. This is just going to parse it. Yeah, returns are going to go in a later pass. Like warnings. Yeah. What other languages do you think should be good for making a compiler? I don't know. I want to make one, but I feel like I'm going to have a hard time learning C. Like learning C is a really good start in learning how to make a compiler. Because it's very, like, I don't know. You can basically make it in anything. As long as you can make it in whatever you want. Like Python. I guess Python has some libraries for parsing. But I wouldn't use it. I want to like know how to do it myself. Like I would have a very hard time doing this in Python. Oh my god, this would have taken like weeks in Python. Oh my god. Like iterating a char buffer, like some chars, and getting each character, and even making structures, like I wouldn't have been able to do that. Interpreter is usually a good start to writing a compiler. Yeah, that sounds about right. We're gonna make an interpreter as well, because I want to do some compile time execution. Not very much. Like I saw this guy Jay, who was like running the entire thing in the compiler. That's crazy. But we're only gonna do some very simple stuff. I was talking about your C code regarding the warnings. I don't know what you're meaning. Like, if my compiler should find the warnings, yeah, it should. But it shouldn't do it in the first pass, because it doesn't know it. Yeah, John Blow. Okay, so this is the indentation mask I was talking about. And this is the current indentation. So we have to print this program here. So I'm going to, and we also have like a specialized print, which is called indented print. I'm going to call it something else, but it's fine for now. And this is printing with the current indentation. So now I want to print, actually I want to make a new function. So I'm going to print the code units, and this will iterate through all the code units in the program. And it's going to call this print code units. Let's just struct iterator code units, and each list member is just called list node, I think. And we're gonna print this code unit here. So this is just iterating through all the source translation units we have. The code unit has a global scope. It has a file name though, so we're gonna probably print that this is a code unit. And print the file name. And we're not handling that, are we? So parse code unit, this doesn't have the file name. So what I want to do, because the parser, or more specifically the lexer, has the code units. No, has the file name. So if I do parser lexer file name, I should get the string. So I want to say code units file name equals this. So then the code unit has a file name. And we're going to also assert that this code unit has a file name with a valid pointer. Okay, so far so good. And this has also a list node. This is just for listing it here, and a global scope. So I want to make a printer for a scope. I'm just going to call that function here. Probably I want to indent the print first. So I'm going to say, let's print the program first. Indented print program. And then we're going to do an indentation. So we're printing this and then we're indenting whatever's underneath it. Like this. And just assert that the indentation is 0 at the very end. And then we're printing the code units. Actually, wait a second. I don't know how to explain this, but basically, this is gonna make lines. Like, I want the program to have like a line, and then the code unit is gonna, I'm gonna just draw it here. It's gonna be like program, and then I want to have these lines here. And maybe this might be like this. So this is the first code unit and it goes down here, and this is the second code unit and it goes down here. The problem is that I don't want it to be like this. So if this is the first one and this is the second one and final one, I want to disable this printing here. So I want it to be like this. So there's still stuff here, but it is not something under here. So therefore I'm gonna first save the current indentation. Indentation is equal to indentation plus plus. We disable this, and then we're gonna paint this mask here. We're gonna say that it is gonna do this. And then we want to check if this is the last one. So I want to check if the iterator is the last one in this list. In other words, if iterator next one is equal to the program code unit itself, this is the last one. So if this is happening, this is the last one. So then I'm gonna unpaint this. I'm just saving the program indent for making it simpler to understand what I'm doing here, like what I'm indenting. Like possibly I'm gonna have probably like indentation -2 I'm clearing, and you don't know what indentation -2 is. Indentation -2. And if this is not happening, we're gonna clear it anyway. Something like that. That should track this. We're gonna do the same thing here. We have a code unit, and we're gonna list a name. So that will be, I'm gonna make a string first. Code units file name. indented print, we're gonna save the indentation. Indentation is equal print a code unit. This is not gonna paint any indentation. This is just gonna be one single node. So we do just indentation plus plus, minus minus, and we print the scope, which is code units, global scope. And here, I'm just gonna print the scope here, so we can see how that looks right now. File name in parser. So we're having a program, basically, and we have code unit file name text failed. In other words, this is not right. So the lexer doesn't know the file name. So the lexer file name doesn't exist. So I'm calling the lexer with the source file name. And it is setting the file name here. String source file name. Oh, this is just an empty one. This doesn't really... New lexer. This is supposed to get a file name, not return it, because we're setting it there. So this is an input to the function. So we need to make sure this is actually tracking the file name length. Let's make a string length function. String length. It is taking in a char data. Okay, so that's the length. Returning that length. And we're gonna try to figure out what this name is. So the source file name is equal to a string, which is just a structure. It's gonna be like this. So text is equal to arguments of 1. I think this is the arguments of 1. And the size is equal to string length of arguments of 1. So the first argument is the file name, and that's because it's compiling that one. And the size is string length, and that should work now. Okay, so I'm getting the program, which has one single code unit because we don't have anything else. Also, this should be indented further. One, 2, 3, 4. That is 4 spaces. There is something in the print which is not right. Let me see, 1, 2, 3. It's supposed to be 4. So then it's gonna line this neatly underneath each other. And let's do like a spacer instead. Is that looking better? Maybe, maybe not. So the code unit, we have one single scope, and that's the top level scope. So now we need to parse all the content of the scope. We're just going to parse the statements currently. I saw right now that your compiler is getting everything assembly, so it depends on another compiler. Yeah. I'm gonna emit machine code for ARM because that's simple, and emitting machine code for x86 is impossible. And besides, if I'm gonna emit machine code for x86, I don't know. If I'm compiling for x86, I have the computer, so I'm just gonna use the GCC assembler. Making machine code for ARM is very simple because the instruction set is very simple. So we're gonna do that. Parsing expression. I learned about the shunting yard algorithm in school. Yeah, that is one algorithm that's mostly used in regex parsing, I think. I use that in the regex parser. I'm not going to be grinding like this every day. I'm having like exams in a few weeks. This is probably... Yeah, we're going to take like probably one stream 1 week, like each week or something. Yeah, so let's just go through, before we start printing anything more, let's just go through how this expression parsing actually works. So I can now parse expressions like data. I cannot parse data. We have to sort that out. Or maybe we can. Did I do that? Because this is a primary expression. So you need to go in the primary expression to check. And this is just the kind. So I guess that works because we're declaring these variables. If I were to do this, it should probably not work. It is going to give me an error. So we're expecting this one, but we're getting equal. So I don't know, this doesn't seem right. I have to go back to the printing. It is basically complaining about this. It's very simple to fix that. We're gonna do that first. So in case the token is an identifier, oops. Have I been writing identifier wrong all this time? Like this. So if this is an identifier, we're going to say the primary kind is equal to primary identifier. And we say that the primary token is already up here. So we're going to set the primary name. This is equal to primary token name. So this is now working. Now it should be able to parse this. Or maybe not. It's the equal sign. So it's complaining about the equal sign. So this is the precedence table which we're using. So I have to make a new node for a sign. And that's probably the lowest priority. So I'm going to add it down here. And then I'm going to explain how this works, because the algorithms are really beautiful. Well, no priority is 0, so I'm going to give it the priority 1. There is nothing really which is below this priority here. It should be able to parse this now. What the hell? Binary assign. Oh, binary assign. We do not have a binary assign here. So in case we get a token assign. We're going to return a binary assign. So now this should work, and it's working. So how does this expression parsing work? And I can literally do anything. All right, like this will work. Like whatever, it should work. So it's very simple. It is just the recursion which is a little bit difficult. But we have a priority table which is telling what priority a binary operator have. So I'm thinking about these binary operators here. And the first thing we do oh, we're getting a raid. Thank you very much. Provad. I haven't seen your name before. I'm gonna give you a follow. Thank you so much. Thank you very much. How was your stream? Can I do this? That's better. Wait a second, I'm gonna give you a follow. Electrical engineer. That's cool. Thank you very much. So we're making a... Hello, X-Philip. Welcome to the stream. So we're making a compiler, and currently we're just doing parsing, but we're trying to make the generator as we go. So we're going to try to generate functions later today. But yesterday, we were able to compile simple expressions like this without any identifiers. So this compiles now. That works. We're generating the assembly here. So now we're just trying to like make this compiler be able to compile more advanced stuff. My stream was tiring and crashy. We're corrupting GPU memory somehow. Oh, that's interesting. And I'm too sleepy to figure out what you're making. What language is this compiler for? This is my own language. I'm just trying to figure out something cool. Very C-ish, I would say. But it's not a language that already exists. Thank you for following. Welcome to the stream. What is it for? Like, I don't want to code in C anymore. Because I hate forward declarations, and there is just many things in C that I don't like. And like bit operations in C is horrible. So that's going to require some refactoring. I'm not switching to Rust. I like to be able to do things the thing I want. Do things the way I want. Therefore I like C. There's probably a language called D as well, which is fixing those issues. How far is your own language you made once? No, we haven't made it before. It's basically just this. Thank you for following. Alright, so this is working. I was just going to explain how this parser works. Like how you can generate this tree based on this expression. So the thing is that each binary operator, you're going to give a priority to each binary operator like this. And higher priority means that you have it should be taken first. So if we take equal, that has a very, very low priority. So basically everything here is going to be taken first. So let's take an easier example. Let's take, I did it yesterday as well. So 1 plus 2 times 3. That's a simple example. So each time we're iterating here, we're basically gonna parse a unary expression, which is basically a number or an identifier or, yeah, some like one statement, like one expression. So a unary expression will be the 1 here. So I'm parsing a 1. I'm parsing a 1. And then I'm getting the next operator. So this is a plus. And then I have to check if that priority rises. So as long as the priority rises, I'm going to continue to recurse down. That's the point. So in this case, I'm getting the initial priority of -1. So the first time it will always rise. So this is always going to happen the first time. So we're going to make a new node here, which is plus. So this is basically being made here. And then we recurse down the tree. So we're going to parse the expression again, but we're giving it this priority here. So the next time it goes up here, it's going to parse the unary expression, which is the 2. So it basically parses the number 2, and it checks if this priority here is rising. So it got priority, for example, number 2, and it gets 3, because this has a higher priority. So the priority rises, and as long as the priority rises, it's just going to continue to recurse down. So this will make a new node, which is a multiplication. And a number 2. So this is the second time this is being called. And after the 2, it's gonna call this again. And you just see a 3, and it doesn't have an operator here. So then it's gonna return the 3. It's gonna return the 3 in here. And then it's gonna return this one again. It's gonna return upwards the call stack. Or not the call stack, but yeah, basically linking this plus here to this node here. So as long as that's happening, it's going to recurse downwards, as long as the priority is rising. So what happens if we have, for example, times and plus? And then the first node is going to be this, and it's going to recurse, of course, because we're giving it the initial priority of -1. So it's recursing down here. It sees the number 2 with the operator plus. So this operator is falling. This has a lower precedence. So then it's just going to return this 2. This is happening here. It is just returning the number 2, making this node here. And so that will happen here on the first iteration. And then it will go up here again, and it will check the next operator, which is the plus. And as long as that is this priority here will then be -1, because that's what we call it with. So as long as I give it -1 here, this is just going to continue to loop in this statement here. Yes, this is going to continue to loop, and we're going to recurse down again with this 3. Yeah. Basically, we're switching this pointer. So the left becomes this entire thing, and you recurse down again. So you get the binary operator, which is plus, and the left leg will be this one, and the right leg will be this 3. It's a really nice implementation, though. It is really just this. Unary operators are parsed in here. So we don't support unary operators yet, and I don't know if we're going to support it. To be honest, it's nice to have, but I feel sometimes you can use it in a very dangerous and bad way. So I do not know if I'm going to include it. So unary expression takes care of that. So unary expression will also take care of the sub-expression here. So this will be one unary expression, will be handled first. So that's happening here. So it's a very elegant algorithm, I would say. Sadly, it's not mine. And then it's recursing to parse primary expression. And it would probably do a call before here with the prefix. And possibly do a call here to postfix expression. But that's basically being handled here. Anyway, let's continue with the printing. It's a generic language. It's meant for embedded. I'm coding embedded systems, so I'm gonna be using it for embedded systems. I'm gonna have some fancy features for bit shifting and stuff like that. Maybe this is happening because we're using line number 1 instead. Because we changed the line number to 1, maybe that has something to do with that. Let me just check that really quickly. This is an error. So line count is 3, but it gives us 4. I don't know, this is probably not going to be there. This is probably just going to be 1. I think maybe this is not case. Sometimes it's going to be 1, sometimes it's going to be 0. So I need to figure that out. But it will not explode. What will explode? It will not explode. It is never going to recur. It's only going to recur once you have like expressions there. You can make it pretty big if you make the expressions right. Like if you're just doing this all the time, you're gonna explode the stack. That's right. If that was what you meant. I've never tried web development. Never. Tree printer. All right. So we're currently here. We're printing a scope. So the scope is gonna list the functions, and it's gonna list the declarations. I think I want to list the declarations as well. So each scope I want to list everything. Wait a second, we have to be a little bit clever. So I'm gonna support local functions as well. Thank you for following, guys. I just want to think how I want this. I'm printing a scope, and I'm at least gonna increase the indentation here. This is just like moving the indentation of the printing, so it's easier to see how the lines go. And then I want to iterate through whatever's on the scope here and print that. So the scope might be this is not really a scope. This is a global scope. Okay, this is a global scope. It's kind of an edge case where you have the global scope, because what's returned is actually a compound statement. It is returning a compound statement. That's weird. Like I'm gonna print the scope. We're gonna print. This is gonna print the scope content. This will. And then we're gonna have a function for printing a statements. We're gonna assert that this statement is in fact a compound statement. So we have a compound statement. We probably want to give it a compound label here. All right. Actually, let's just do print the statement, which is going to print everything. I'm going to delete this. Doesn't we have a statement here? So this is printing a compound statement here. Indented print compound. So the only thing we have to do is really printing the functions. And this is a compound statement. Okay, so remember, a compound statement also has a scope. So you're gonna move this a little bit up. So after printing all the content on the compound statement, we're gonna print the content of the scope as well. So you're gonna print scope. And if I'm not mistaken, we have a pointer there. Compound scope. So this will go up here, and it's gonna print this. And I'm not gonna print scope, because I don't really need to know it. So I'm just gonna keep the indentation as it is. And if that's inside a compound statement, that's gonna be indented here. So what I need to do, I need to iterate through all the, let's do the functions first. So I'm gonna iterate through the functions. And remember that everything we place on the scope is not functions or types, it's declarations. It's basically mapping a name to a type. List the structure. Oops. Again, the keyboard is messed up. It's like a programmable keyboard, so maybe I've programmed it wrong. Isn't that working? Oh. All right. We're gonna assert that this declaration has a type function. So that has to be true. Otherwise, this should not be in this list here. So you're gonna assert that this is true. If this is true, we're gonna print this function. So I'm gonna make a function for printing a function. This is gonna take in a declaration. That's what is happening here. Okay, so declaration there. So print function. It's gonna go up here. How do we print a function? Let's first grab the function. And a function has a body, a function scope, and a return type. So really the body will contain the actual scope of this function. So the body here will contain the scope over here, while the function scope is containing the scope here. Input-output parameters, we can possibly print those. So I'm going to print a declaration. It's a function. Okay, so we're going to list. We're just going to print the scope. Like, how do we print the scope? Okay, I'm gonna print the declarations after this. We're going to use the same list node. List iterates, iterator, scope, variables, which is the same. Iterates. And we're going to list types to the very end, if I have any type defs. So probably I should be able to type this here as well. So let's make an IPv4 type, which is supposed to be U32. This is a typedef operator. So now I should be able to do data is equal to an IPv4. This isn't supported yet because this can't be parsed. So we need to support this. We need to support a custom identifier here. Actually, let's support that right now. So I need to go down to parse a type. So a type might either be like U32 or something else. Because we're consuming this token. Token kind. So I'm gonna do an else here, else if. Identifier. If this is a token identifier, really everything is going to be replaced with like namespace identifier, if we're going to have namespace before it. If token is equal to identifier, this is really a type, but this is a reference. So the type will be replaced later once we know what this is. Because in this language, we should be able to do this. So IPv4, data is a type of IPv4, and this is declared here. In fact, that should be in any case. So I should be able to use like some token is equal to 35, and I need to define token down here as a U32. That's fine. That's basically the same as writing in C int test and using it up here. That is allowed. And at the same, in the same reason, we have to parse everything first, and then we have to fill in, once we know what type test have, because we know it there. So we need to make like a type reference or an unknown type. So I'm gonna call it unknown type. We don't know what the type is yet. So pointer type, basic type. Unknown. And do we really need an unknown type? Yeah, we kind of do, because we need to store the identifier. So we're gonna have a type like this. And this is going to store the token and probably the string value. I mean, it's not any overhead because this has the same size as this one. In fact, it doesn't. So I'm going to remove this. So this is the identifier. I'm just going to say token here. Alright. So we have an unknown type, and we're gonna make that an option as well. So type is inferred. We don't need anything for this because we don't need to store anything. So we need type unknown. And if this is an identifier, we're gonna just assume this is a valid type. Yeah, we're gonna assume this is a valid type. And type is equal to new type unknown. Doesn't we have token there? Oh, unknown and token is equal to copy token. What token are we going to copy? We're going to copy this consume token there. That's the identifier. Oh, this is already a type. I can just return this one. Okay, so that's it. Now we're going to be able to write something like this, and this will work. Thank you for the follow, by the way. I'm missing operator between 4 and 3. If that is happening, let's see. Like if you have something like this, it's going to parse this one, then it's going to parse 4. It is going to check if this is a valid operator, and since this isn't a valid operator, it's going to return, and it's going to recurse all the way up. And if this is an expression, then we're going to expect this to happen. So we're expecting this but getting F45. So this will be a compiler error. That works now. Compiler building, I don't, I'm very sorry. Just try it out, I guess. I mean, this compiler is really small now. How big is it? It is really small. It is like 4311. Really tiny. So this is a start, in fact. Spaces between two things determine the operation. That's a good one. Yeah. So as Captain obviously is saying, that's a good start. Why C and not C++? Any opinion? I don't like C++, to be honest. I feel it has way too much stuff. I was programming C++ for a year in school, and oh my god, there is so much there, and everything is embedded. There isn't like an operation for everything, and I don't really like it. And classes and overloading and the public and virtual and yeah. I don't know. I feel I'm more control with C. That's perfect. Now we're gonna support this. So let's fix the printer once and for all. So really everything here is just either a variable, a type, or a scope. We're gonna make a function for printing a variable and a scope. Probably not the variable. This is very simple to print. We're gonna print a scope. We're gonna print a type though. So here I'll do the same thing. So all of these are declarations, but assertion is gonna be different. We don't need to assert really. This is always gonna be true. So this is a stupid assertion. And here we're gonna print the type. We're gonna give it the declaration. We're giving it the type declaration. This is not the type, this is actually a type def. So this is, I'm gonna comment that. This is type def. Thank you for follow. Oh, thank you for subscribing. Thank you very much. I really appreciate that. And welcome to the stream. Still writing, yeah. Good night, everyone. Good night. There is no tomorrow. Yes, they're spending too much time on C++, in my opinion. Like, it's a great language. Probably if you're gonna do game development, C is not the right language. Even though you can do like Linux is built using C, so you can do and the early C++ compiler was compiling to C, so you can do everything in C as you can do in C++. It's just a little bit more inconvenient. Yeah. But the object-oriented stuff, I don't know if I like that. The thinking that everything should be an object and functions should be operating on objects. I don't like that, to be honest. I've not tried Rust. No, I haven't. And I feel this is going to be easier to learn. This is going to be way easier than C to learn. Like, way simpler. You're not going to have that much pointer stuff. Like, if you want to do, like I have, for example, a structure. Let's make a structure. If you want to have a local structure, that's fine, of course. So I'm going to do a typedef here. And this is going to have data, which is a U32 and kind. And it's also going to have a union. Which is, for example, and we're going to have a new def here. So this is not a typedef, because I'm not using the typedef operator. So this is an anonymous struct. The struct doesn't have a type, but this is going to be the structure. And this has some, like, variable. So if I want to know some kind of offset here, I don't know if you can do this in C, but if you have a token object, which is type of token, and you do token token test, this should give you 1. This should give you 0. So we're accessing this token, and you're accessing the member token. Since this is an anonymous union, it's going to access this one, which is a structure, and you're asking for the element test. This is going to work. If you want to have, like, this is a token, which is a pointer to token, and you want to access this member test, you're going to write token test is equal to something. It is not going to be like this. And all the things with forward declarations and header files, defines, preprocessor, everything is going to be gone. And makefile is going to be gone. If you want to use this language, you have to do luxury, and you're going to give it a build file, lux. That's everything. If you don't write a command line like this, it's not going to work. So everything with flags and options, every stupid thing, a linker script and so on, is going to be contained inside this build file. So I think it's going to be easier to learn than C, in my opinion. So print the type. This is also going to take in a declaration. A declaration. This is going to print a type. This is not really going to take in a declaration. This is going to take in a type. All right, so we're going to print the type, which is the declaration type. And here we're going to print typedef. And the identifier declaration name. So you're printing the typedef and a name, and then you're going to print the type underneath. So I'm probably going to indent here. Yeah, this is printing a scope. And it's printing a function. So let's print a function here. Function. I'm going to print the function name, which is in the declaration. So that's reprinting the function name. What is the convention here? You're indenting before you're doing something. So this will not do any indentation beforehand. So print function will just print the function and then maybe indenting afterwards. Printing functions. We're basically going to do this. So I want to print a scope. I want to do indentation plus plus, indented prints, and let's first do like indentation. The function indentation is equal to indentation plus plus. We don't need this part. And then we're gonna say mask of function indentation is equal to true. We're gonna start painting this indentation. Thank you for the host. Thank you very much. So we're painting a mask here. So this always has some arguments. So I'm not gonna clear the mask when I'm printing these arguments. Indented prints arguments, gonna give a new line, and we're gonna print the scope, which is the function scope. So that's it. And then we're gonna print what are we gonna print then? Like body. The function body. And that's the statements. So I'm gonna print a function body. And here we want to clear this mask because nothing is there. A function doesn't have multiple bodies. So I'm gonna clear this mask here. And then you clear the indentation afterwards. So it's printing a function. Let's just try that and see if this works. Okay, some errors. This is wrong. All right. We're missing some declarations. Print scope. I'm gonna just add them to the top. I don't really care. I'm gonna add everything. Print expression, that's gonna be static. Print the function, that's gonna be static. I'm gonna change this. Oh my god, that was wrong. That's printing a scope, we have that. Printing a type. Printing a statement, that's gonna also be static. Welcome to the stream, welcome to the stream. Print code unit, that's the last one, which is gonna be static. The final one needs to be called from outside. So I think that was everything, and it was. Expecting, but got an identifier. That's fair. That's fair. So it's erroring here. Let's try this instead. It shouldn't make any difference. Okay, it's still complaining with the data. It is expecting something. Wait a second. When we parse the type, or parse the declaration, yes, that's the point. If this is a function, we're basically handling everything. If this is an inferred statement, yeah, so no, this is going to return. So the thing is that after this, we have to expect the closing, the semicolon. So we're actually going to move this one outside, because that's going to happen anyway. It doesn't matter, because now it's only being handled if we have something like this. But if we only have an assign, yeah, if we only have an assign, if we don't have an init expression, this is not being checked. So we're going to skip it here instead. So there you can see it works. So we have a function main, and we don't have any new line after that. So function name, new line. So the arguments is something, and then you print the body, and this is supposed to be indented. So the body is a compound statement. Since I'm already printing compound here, maybe we can just ignore the body. Yeah, I'm gonna ignore the body there. And I'm not indenting here, that's why. And I'm clearing the mask. Does that work as well? Yes, I'm clearing the mask. That's therefore I'm not getting any paint here down there. So the compound is an expression, a binary null expression. That's interesting. We have to see that. We have to check that. All right, so this is probably the first expression here, which is just a subtraction, and this is handled correctly. This is not going to add anything here. This is going to go on the scope. This is supposed to add something here. This as well. Let's just see if that works. Because I'm getting a binary expression 0. That's strange. I think I know where the problem is. If I delete this, oh, it says primary not handled. Binary 0. That's strange though. Let's try something else. Let's try this again. So that we're getting that. So the equal we're not getting the equal. Let's just try to parse this. Okay, the equal we don't get. So something is wrong exactly there. Hello, Deepbox. Welcome to the stream. Pratt parsing. Pendanic. Yeah, it's a very cool algorithm for parsing that. I'm using Source Code Pro as a font. So it returns a 0. So my question is then, do we have any... Is the equal token actually being parsed correctly? So the assign is just 1, and the binary assign, oops, is being set when we have token assign, if it is a token assign. Also, wait a second. Isn't that the first time we're using variables? These are not including variables. This is including a variable. Probably the primary expression is wrong then. Where's the primary expression? Here. So this is parsing a primary. We're consuming this token. We're actually gonna print and see if this is happening. Yeah, we're just gonna ignore the name. That's actually happening. So we're setting the token kind. Is there anything more we need to set here? So that's why this primary is not handled, by the way. But I don't understand why this should be a 0. Let's investigate this further. Let's go in and just support this unary, like primary identifier. So this is the primary. So that we're getting this one. So now we're going to say else if primary identifier, and we want to print almost the same. We're going to first get the identifier name. The string name. And this is an identifier. So now it's going to handle that. So the binary is 0. I know what the problem is. We're printing based on this table, which is really stupid. I'm actually gonna have to change it all these places in order for this to work. I think we have an assign after this. So if I do this, it is going to give me assign token should have the value like the number 235. So now let's try to make something more complicated. I'm going to define this token here. I'm going to make an inferred define. And this is also happening. But now this is going on the scope as well as an inferred type. Even though I'm giving this a type, it is still going to work. If I give this something else, which it doesn't know, this is also going to work. But it doesn't know what the token is, so we have to go do a second pass and figure that out. Perfect. This is really nice. And by the way, local function should work now. So we have a new function here, which is called print, no arguments, and a compound body, which is just one expression. So this is the body here, and you can see I'm not getting this line here, and this is because this is something different on the scope. And as I can show you where the problem is. So I'm printing this statement here. This is what's printing this thing. And then after this, I'm clearing this mask. This effectively clears this line here. But I'm still needing to print something on the scope. So what I need to do, if this is true, and the scope is clear. So if I don't have to print anything in this scope, So I need to make a function which returns that. Thank you for following. Welcome to the stream. Scope is clear. Yeah, scope is there. So if either, I have to check if all these lists are empty. So I think I have one function for that. So if function list is 0 and variables are 0, let's see, and types are 0, what more are we handling here? There's just these 3. So if all those are 0, we're going to return true. Yeah, so this function will be, it will be like and scope is clear with the current scope, which is compound. I need to track what the scope is, and I'm printing compound scope, so I'm going to use this one. So if I now run this, Alright, this is interesting because we're only printing the function here, and since we're still printing the line, yeah, this is something we also have to do. So in each of these scopes, in each of these loops here, we have to track if that's the last one. So compound indentation is that. So first I'm going to store the scope indentation, which is equal to the indentation minus 1, because we're actually going to access this one before the indentation is incremented. We can probably take this as an argument as well, but we're just going to do it like this for now. Thank you for following, guys. Welcome to the stream. Who is that? Yeah, that's my name. I'm from Norway. Is this for real, making a whole compile? Yeah, this is for real. I don't want to code in C anymore. Thank you very much, Game David. Thank you, and welcome to the stream. Print a function. We need to do a check here. So if list is empty of the scope variables and list is empty of the types, if this is true, it means that both this one and this one is empty. And we need to track if this is the last one. Dang it, okay. So if iterator next is equal to scope functions, if all this is true, we're going to clear this scope indentation mask. And the same thing we're going to do here. This is really stupid code. This is just for making it really cool when we actually print it. So I think it's worth it. I'm going to do this, and this is variables instead. And here we only need to track the last one. So if iterator equals scope types, we're going to clear the mask. We're going to do this. And in any case, if this doesn't happen, we're going to clear it anyway, just to make sure. And we're not going to do any indentation there. Mask scope indentation. I think that's going to be right. Compound failed. 162. Testing generator, okay. This is still printing something wrong. Because I'm printing the scope here. Because there is something after the print. I think I'm just not printing it. That's the point. I'm not printing it. Yeah. So if this is a type def, we can do the variables first. So indented print. This is a declaration. So I'm going to call it a declaration. I'm going to give it a name. So name text. So this is just printing the declaration, and I'm going to print the type underneath, because that might be a complex expression, like a structure, something more complex than one line. So I'm going to indent one step, indentation plus plus. I'm not going to draw the line here, so that's why I'm not doing anything with a mask. And then we're going to print type. Which is declaration type. So here we have a declaration token, and it doesn't print the type because the type printing is not doing anything. We're gonna switch the type kind here. So in case we have an unknown, this is an inferred type. No. This is an. This is, for example, a structure reference or something else. So basically, the first time we're printing this, like if I'm printing this after the parser, this is going to give me a lot of unknown expressions. And once I've done the first pass, this is never going to happen again, because all these types is going to be replaced by something that's actually valid. Thank you for following, by the way. Will you maybe upload this on YouTube? I don't know. I can at least make it like permanent on Twitch, so you can look it on Twitch later. I can do that. So this is an infer type. We can do this. Pointer type, we do this. Base type, we do this. Unknown, so we say unknown, and we're going to print a name, because even though it's unknown, we know what it's supposed to be called. And the reason I'm doing these brackets here is because then I can define variables inside a switch. That is very nice. And instead of just having like brackets whenever I want to define variables, I'm having it all over the place, because I want to be consistent with my coding. So that's why. So this is a type unknown. So I'm going to say type unknown, and this has a token which has a name. And then I'm going to print name text. That should work. Infer type. This isn't really anything to print, so I'm just going to say this is inferred. Pointer. How are we going to do a switch again, or an if statement? So if this has a type, we know this is an array. Thank you for following. Thank you very much. if this is a pointer, we need to be a little bit smarter. I'm gonna print this in one single line. I want to print this as the text you're reading. So I'm gonna check the pointer count. I'm gonna check if this has any count. I need to do this only once. Do it in because we don't know if this is the first one or we have multiple of these. I'm gonna say if this has a count, we're gonna print array of and here I'm gonna print a number, and that will be pointer counts. Just that. And it's gonna print a new line. And it is printing array of, and then I'm gonna do a new indentation here. So plus plus, it is not gonna paint anything because I'm gonna recurse out right away. I'm gonna print the type again, which is type pointer 2. I'm gonna recurse out. And if this is not a count, we're gonna say pointer 2 and break. And basic what are we gonna say? I want to print a number of bytes. I want to print the unsigned first. So if this is unsigned, I want to print a string first, which is either unsigned or signed. Unsigned, and then I want to print a number. I want to print bytes, and then HR if this is multiple. So the string here is going to be if if basic is signed, then this is going to be signed. I'm going to do full screen. Wait a second, let's do okay, let's do S here. So S signed. So basically if this is unsigned, if this is false, I'm gonna do un, otherwise I'm just gonna do this. If basic is signed, and then we're printing the size, and then we're printing if size is bigger than 1, then we're printing a C. Otherwise we're just printing like space, I guess. So this will print either unsigned or signed. Actually, let's do this manually instead, because I want to have capital letter. So this is unsigned. Or signed. Okay. So now we have a declaration, and this is assigned 0 bytes. So why the hell is that 0? It says that the type size is 0, which is really weird. Because token, what is token? token is a token. So this is actually a reference. This is an unknown type. So this is really unknown. So somewhere in the code I'm not setting unknown. That's in the parser. So in the declaration parser, or basically here, I'm setting this as a type unknown. Let us check if this is happening. We're getting okay. Let's just double check. I'm gonna say 2 O's instead. So that's happening. And this is the type unknown. So new type, we're not setting the type here. That's a mistake. So I'm gonna say type kind is equal to kind. And now this is gonna work. So the declaration token is having the type unknown. It doesn't know what it is. And the identifier is token. Let's try to make some more stuff here. Let's try to make some kind of inferred type. Data is just going to be like a number. Then we have data, which is inferred. And also note that this is, where is that? Like you can see data is inferred. That's one thing. Like let me set this like 3-3. So data is first of all inferred, but it also is right here. No, I was supposed to set this to 4 or something. So even though it's here, it is also here. So this is just expression and the declaration is on the scope. And I can very easily look up that expression later. So when I'm, for example, parsing, doing the second pass on this, I will, for example, say like, okay, this is the identifier data. So I have to check the current scope and then recurse out the subscopes and I have to try to find this data. And in this case, it will actually find the data in here. And this is inferred. But let's say this was like of type pointer to 50 U60 or pointer to char. Something like this, more complex. Then I would get, what the fuck? Generator restarting. Pointer to, we're not doing anything here. This is supposed to happen anyway. So you're gonna do it like this. And this requires a new line. Okay, so basically you're looking for like the generator is going to generate code for this, or this is really the type checker, and it's going to go in here and it's going to look up data and it finds it here. We have a declaration for data, so immediately we have the type. We know how big it is, we know if it's a pointer, we know what it's pointing to. So this is a pointer to an array of 50, pointer to signed 1 byte, which is a char. So that's the way the typer works. It's very easy for the typer just to go over and check everything. This is wrong. Arguments. Oh, we're actually getting the arguments. We're printing a scope, and this will automatically force to like disable this. So I think I maybe want to indent this a little bit more. So I want to have this indented. So after the arguments, because this is actually parsing the arguments as well. This is working really well. So after this, I want to indent before I'm printing the scope. Indentation plus plus, indentation minus minus. So now I'm getting the arguments of the function are a declaration, which is 4 bytes, which is also wrong. Oh, that's a C, it's supposed to be an S. So 4 bytes. Let's make some more complex arguments. So I want to have, let's see if we can parse multiple arguments. So I want to have something which is a pointer to token. And we have one data. And again, this is wrong because we're gonna paint this one. So this is just printing the scope, which is forced to be just this. So there is a problem in here. This is already false, I think. So what we're gonna do, we're gonna just make that true right away. And then if this is false, we're gonna make it false. So you're gonna force it to true in the beginning. I think that's gonna fix the issue. Yeah. So now we can see we have a function main, you can see the arguments. The declaration token is a pointer to unknown. We can also colorize this if you want. That's gonna probably make it simpler to like spot the functions and declarations and so on. And the body is a compound statement which has a new function which is called print, no arguments, and is doing just a binary equal. And this has some declaration, this doesn't have declarations. Actually, let's try to make some declarations on the sub function. So I'm gonna make this an inferred statement. So then this is gonna pop up here. So this function is gonna have an inferred declaration there. Wow, okay, that's cool. Now I just have to think, do we need to do more or can we start generating the code right away? We know the size of all the pointers, a number. Because eventually we're gonna type this, so each expression is gonna have a type. So you're gonna annotate each binary expression, each, probably this as well, with its own type. So in this case, it will get the type from the token here. And we're gonna check that this has the right type. They're CAS compatible, at least. They're compatible. The question is, do we need to do that now? I don't think so. But we're definitely gonna be able to go over the tree once and yeah, just yeah, we're gonna go over this tree once and filling in some of the types. So that's very important. Like normally in C, you, for example, like you have to forward declare stuff. So you can do like, this is a variable and you set it to some value here. And you change it here, and then the C compiler knows that this has to be declared. So the C compiler does only one pass, at least for the parsing, because it knows everything. In our language, we can do it like, we can have like data is a U32 and we can use it up here. Something like this. So we have to first parse this and then we have to go back and we have to check like, Okay, we have an identifier data here. Has that been defined on this scope? So that we have to do in the typer before we can start actually generating this code. We can actually start generating the code, but it doesn't really make sense because we can't use identifiers. Because if I'm going to generate this, I want to be able to look up the data, and that's going to have a type, but that's going to have a declaration, and that declaration has an offset because we're assigning that offset in the stack frame. It's gonna make sense in like a few minutes. But this is cool. Maybe I'm gonna go to the toilet first. This is so cool. Thank you very much. Is this recursive descent? Yeah, that's right. This is a recursive descent parser with like priority tracking. So somebody, you can do it different ways. You can either have like multiple functions where actually the function recurs. So we say like, you have a function called parse binary expression. Now we have a function called parse equal, and that calls parse multiplication, and that calls parse plus, and that calls parse unary, and so on. And there is also a way where you like just recurse down without tracking the priorities, and then you fix the priorities on the way up. That is the different way. But I think this is the best one. So I'm just gonna go to the toilet. I'll be back in like 3 minutes. Hello. Okay, thank you for following, by the way. I heard you. C is more beautiful than Python. That's right. That's right. C is much more beautiful than Python. Like, Python is a great language, but I don't like the indentation thing. Like, it is very hard to... It's very easy to make mistakes there. Okay. So I think so far the parser is working as we would expect. So I think it's time to do the second pass now. So now we're gonna traverse this syntax tree again, and we're gonna fix everything. And this is gonna be easier. This is gonna not be that much code like this, because we do not need to handle everything. We're gonna recurse down into all the leaf nodes, and we're really only going to track the identifiers. So if I'm using an identifier, I'm going to look it up and I'm going to link it to the declaration. And that brings me to something very important. So I don't know if that's the case per now. Yeah, so this is a primary expression. So basically when I'm generating this code, I'm going to get the primary expression, which is just a string. And that is, for example, like data or a variable. I need to be able to find the address or the offset of this variable from just looking at this. So I need to add a declaration here. Which is going to be 0 by default, and then I'm going to link it in. So I'm going to link in the actual type there. That's going to be done in the second pass. And actually, I think we can make typedef work right now. I think typedef is going to work. Let's just do this. So first of all, I'm going to do int. I'm going to type the int to be like U64, just to make it interesting. And I can place that down here. I don't need to consider the order. And then we have test which is equal inferred equal, let's just make it int, 256 plus 45. And one last thing we have to implement. I'm going to implement return expressions. So I want to be able to do like return test. So that should be very simple because it doesn't introduce any like more operators or any crap. So we need to be able to recognize this keyword return. So I'm going to go in the lexer and I'm going to add the keyword return. And then down here, I'm gonna say that return is gonna look like this. It is just return. So now I can use like is keyword and use return here. And then that's gonna compare with this entry here. Yeah, so when do we actually look for this? Well, this is a statement, and this is not a declaration either. So this will be in a declaration, this will be in a statement parser. This is parsing a block, which is doing parse declaration or statement, which is parsing a statement. So here we would need to track this either before or after this. We can do it after. So we're going to check if is keyword. This is returning, by the way. Is keyword token and yeah, keyword return. So if this is a return keyword, we're going to make a return statement. So I'm going to make a new node for that, just to make it expressive. So this is a statement, and we're going to have a return expression here. Since we're going to be using the first statements, and we need to figure out a few things when using defer. So I'm going to make return like a separate statement. I'm going to do this. No, I can't do this. This is a keyword. This I can do. Can't do this. Let's call it return statements. I'm gonna maybe fix this later. Oops. So a return statement is really only gonna contain an expression. That's what it's returning. Because it needs to return something that can evaluate to a value. So an expression evaluates to a value. It is basically a value. Return expression. And then we have the statement type, which we have to add one entry for the return. So now we should have a return statement. So if this is a return, we're going to allocate a new return statement. Let's just call it statements. And the statement kind is statement return. And yeah, this is the one we want. We don't care about this. So we can actually just do return here. Return. And then this will be a return statement. And we're going to parse an expression. And we're going to wait for the terminating semicolon as well. So you're going to skip token semicolon. So this will parse. Okay, the current token here is going to be return. So first I need to skip the return token. So I'm going to say next token. And then we're getting a new statement here, and then I'm parsing whatever's here. And this might be something really complex, that doesn't matter. But it has to be an expression though. And then we're skipping the semicolon, and then we can just return that statement. I'm gonna need a cast. This is really return. I'm actually I'm gonna say return statement here. And I'm gonna call this return. This is gonna be ugly. Maybe I'm gonna name all these like compound statement, common statement, and so on, just to make it like unified. Yeah, this is gonna parse the return statements. And then we need to print it as well. So print statement, and we need to make a case for statement return. So I'm gonna do an indented print, which is just return and a new line, and we're gonna do an indentation plus plus minus minus and print expression, which is gonna be statements return statements. Oh, that's fine. Yeah, okay, that's fine. Yeah. So statement, return statement, return expression. This is gonna be printed. So if I now try to do this, yeah, that's wrong. Parse expression. We're also parsing an expression here, and we need to give it the initial parity of -1. So we're returning an identifier test. And we're just going to check if that can work with something else as well. Plus, minus, data, or something. Then it's returning this complex expression there. Perfect! This is working so well. So currently we're just going to return this thing here. We're just going to evaluate what its what a value is, and we're going to place it in RAX register and just do return. You can, oh, can you not do return like in C#? Like, how does C# does return? I haven't programmed that much in C#. I've only done like a few Windows applications, like serial terminals and RS-232 or something. I can't remember it. I'm kind of new to see how does that union and struct work. That's really a really good question. And we're gonna be able to, we're gonna implement this in like a few streams. The way it works is that this is gonna allocate space for, this is basically gonna be either this one or this one or this one. That's a union. So this is gonna allocate space for the biggest member. So if this is, for example, like 5 bytes, and this is 1 byte, and this is 50 bytes, it's gonna allocate 50 bytes here. And if this has an alignment of 4, this has an alignment of 1, this has an alignment of 1, then this entire union needs to be 4 byte aligned. So it's going to allocate the biggest size and the biggest alignment. So basically, both this one, and this one is going to have the same offset. So both is going to be offset 0 from the address of the type. So if I'm having like a type, so this is a pointer. So I read pointer as address. So this is holding an address where it's placed a type. So if that address is like something like this, and you print the address of, for example, pointer, that's going to return the same address. So that's why I'm always like casting here, because I'm basically talking about the same address in memory. So that's very convenient for making these kind of structures in these kind of tree structures. It's very nice. Okay, I think we have everything now. And statement kind is not handled. Where is that happening? Statement kind is not handled. There seems to be one statement we're not handling. Let's print this type as well. Number 3, which is 0, 1, 2, 3, return. Oh, we need a break here. So now it's generating. We're gonna do one more thing first. We're gonna make a typer. So we're gonna make the type checking file here. I'm gonna call it typer, or type checker. I'm gonna call it typer, it's shorter. And we're gonna add it in the make file so we can actually compile it. Okay. And now we're going to do one tree traversal. I don't know if I pronounced it right. Tree traversal. We can make it, like, possibly we're going to make multiple ones, but I think I want to... There were one guy that told me to rebuild like linear tables the first time. So I'm going to only traverse it once, and I'm going to rebuild linear tables. But I'm not going to do that now, because that's more complicated. Thank you for following. Typer. So this is a C file, so I'm going to include a typer header file. And this is my worst word. If not define. It's so hard to write right. It is so hard to write. This file is only for the types I'm using, so that allows me to use like U32 and stuff like that. It's very neat. So we're gonna have one top level function, I think. Type program. And this needs to include the tree for accessing these members here. Okay, so we're going to type the program. We're going to make it really simple. Typer. We might include a printer. Sysidy.io. And also, thank you for following, by the way. I'm gonna move these types here to the typer file. So I'm gonna do this. Oops. I didn't mean to do that. And we're gonna grab everything here and we're gonna make them extern. So any file including typer will actually get the types here. There we go. Okay, so we're just gonna delete this. And we're gonna make this extern. Because we can't really define anything in the header file. Because what C does is just copying things around. So if you start defining stuff here, you're gonna get like multiple declaration of something. So instead we're gonna say extern, and this tells the C compiler that this name here is defined somewhere else, and it's defined here. And this is only going to be included once, so or parsed once. This is not going to be included anywhere else. So it just tells the linker how to operate. Type a program. Oops. So you're going to type a code unit. We're going to iterate through all these code units. Let's say program code units. Okay, so we're iterating through all these, and no problem, VLAD, no problem. And now we're going to type the code units using that. And remember that code unit is only like, it has a name and it contains a global scope. So it has a global scope. So now we need to think. I'm just gonna type the scope, and then we might need to do something like a specific order. Type scope. I'm not gonna print anything, I'm just gonna type the scope. Global scope. So this will get the scope, and we should type everything in here. So this is on the scope. Wait a second, do we have that? We have a type def there. That's actually working. So first of all, we need to resolve these type defs here. Or all right, so let's see. Okay, let's say you have, for example, like you have a token structure defined here. That's fine. And then up here you're saying that you want to type def. Let's say you want to have like 2 eyes. This is going to be type def to token. Yeah, this is going to be type def to token. And then you want to use some declaration using this II. So I'm going to allocate some. I'm going to make a variable called data, which has the type II. And then I'm using data up here. So the first thing I have to do, I have to go through, like all of this is resolved. Like if I'm parsing a structure, I don't need to do this. If I'm parsing a structure, this is linked with this type definition there. The problem is that if I'm having a type def where this is unknown, so if I go into the tree now, you can see that this is, let's do it again. Return. I need to include a typer in the parser. That didn't work. There we go. And it doesn't give me this because token is a structure. But that's fine. I can just delete this temporarily. Okay. So the thing is that I have a type def here, but I don't know the type here. And we can see that from, we have a type def, but it is unknown. The point is that when we have parsed this entire thing, we know all these structures. So first we have to go through all these type defs and replace this unknown token with the actual structure, which won't be a problem now because we know everything. This might be a problem when you're nesting, so it might require several passes. I think we're just gonna ignore this for now. So we require that we only have known types here. Yeah, so only known types there. So that should be fine. So basically we have the type of this. So we don't need to do anything here. Yeah, so we have to go over, let's delete this. We have to go over all these declarations because as I was saying, this will be like, this will be the same as test is an integer and then test is assigned to 56 plus 45. And this is gonna go in the scope. So what we need to do, we need to iterate over all these declarations first. And for each declaration, For each declaration, we need to replace this integer with this actual type here. The question is, do we need to do that for all subscopes? So let's say I have like an if statement here. And I don't need to do that because I can't use anything in here. I can't use anything out here which is defined in here. So I think that will be fine. I'm going to iterate on the current scope through all the declarations, and if that is an unknown type, I'm going to replace it with the actual type. So then it also introduces some problems, like if I have two lists I have to iterate through, or it's really only going to be one. It's really going to be just one. I have to iterate this typedef list. Okay, let's make the example as it was. So this is the example. Okay, and also we're gonna try to print this tree after typing this. So I'm gonna include a printer as well. Okay, so we're printing it after. So we typed the scope, and now we have to be careful. We're gonna go over. Oh, wait a second, it didn't have it up. Okay, so iterator, we're gonna iterate using this iterator, and we're gonna iterate the scope variables. We're also going to need to do something with the typedefs, but for now I'm just going to assume they are right. And this is a declaration. So for each single declaration in this current scope, I need to figure out if this type here has kind unknown or something. Unknown? Yeah, unknown. Because then it's going to be switched. So let's try to do that first. If this is equal to unknown, that is equal to unknown, you're going to look up on the current scope. So we need to make a function for looking up something. Yeah, we need to look up from the scope based on this one. So I'm going to look up a I'm not sure if I'm going to specify where I should look up. Probably I should. And probably multiple functions, because I'm going to be recursing downwards, and if I have to specify the list, that would be wrong, because then it will calculate the wrong list each time. So what I'm going to do, I'm going to make two functions here. This is going to return a declaration pointer, and I'm going to say this is lookup lookup in scope. Yeah, lookup in scope. And this is going to look up like a string. Let's make it a name pointer. String pointer. And we're going to specify where to look up this thing. Because we have there. Each scope, which is defined here, has 3 lists where we place various stuff, and I want to specify which of these lists I wanna choose. So I'm gonna specify the declaration kind. And then I'm gonna have the declaration, which is lookup. Lookup in list. I'm gonna say lookup in list. And this doesn't need a scope. Wait a second, can we do this? No, we can't. Lookup in scope. I cannot do this. So the problem with this, if I'm giving this a list, since it has to recurse, it's gonna, on a later pass, it's gonna have to use a different list because it's gonna use a different scope. So I can't really tell it where to go in. I can set the list. Wait a second, maybe let's try. So we're first gonna get the list here. So I'm gonna reuse my code in the printer for this. It was probably in the parser. Lookup in scope. It's in the place or push onto scope in the parser. Here. So I'm gonna be using this one. So this is grabbing a list, and depending on what kind of declaration I'm having, it is gonna choose a list for me. And scope is here. And then we're gonna iterate through that list. So we're gonna iterate through that list, and first we're gonna get the declaration. This is a new declaration, I'm gonna call it new. List to struct, and please ask if something is unclear, like what is this, or just to ask questions, that's perfectly fine. Declaration. So we need to check if this declaration here is a declaration for this name here. So I'm gonna do a string compare. I probably need to include string for that. String compare. This isn't really a function, and that's because GCC is messed up. So my string, which I want to call string, is colliding with some internal library. So I know this takes in 2 string pointers, A and B. So I'm just going to use that. So I'm going to compare name with the address of new name, because that's not the pointer. So I'm going to compare those. If this is true, if those match, I'm going to return this declaration. So I'm returning new. Yes. If I don't find it here, this is the point. So if I don't find it here, we need to go up one scope. We need to try to find it in the parent scope. Assuming we have a parent scope. So I'm going to say if scope parent, we have a parent scope. I'm going to recursively call lookup in scope using this new parents, the same name and the same declaration. And this might return a declaration, but we're going to just return this. Otherwise, we're going to return 0. So this might recurse multiple times, but eventually it will stop because this is going to happen. So this is the edge case. This is the end case. And if this is happening on the top level scope, this won't happen and it's going to return 0. So I think this will actually handle everything with a lookup. Do you stream more often? Yeah, I've been quite busy in the past like months, but I plan to stream more often. I probably need to do some more school now, but like in a few days we're going to continue with loops and more advanced stuff. Nice job, man. It compares a thing that I think I'll never do in my life. I also thought that, but you never know. Probably you're gonna end up doing that. It is a really nice learning experience. And to be honest, writing a compiler is so much more complicated than I thought. Like the operating systems I've been doing previously is like nothing. Because I'm really struggling with this. Yeah. So it's a really nice learning experience. What am I studying? I'm studying electronics. I think it's called Electronic System Design and Innovation. It's a stupid name. It's a really stupid name. I haven't like my brother was helping some girl yesterday and with some transistor stuff, and I don't know this. What is a PN junction? I don't know that. And I'm studying electronics. So it is taught so badly. Or maybe I'm just stupid at school. I don't know. But it's like about electronics, and it is not about what I'm doing now. That's for sure. Okay, so if we have an unknown type, we're gonna type it. So we're gonna go in here and we're gonna look up in the scope, in the current scope, which is here. Actually, instead of passing around this scope all the time, I'm gonna make a type restrictor. I think that might be a good idea. I'm gonna make a type restrictor because we might end up needing some more information, like does this tree has unresolved types? We need to continue to recurse. Has it been a type change since last recursion? If there hasn't been any change and there's still unresolved types, we need to like report an error, like the type checker can't do its job or something. So this is going to go into this typer here, and we might also save the scope here, the current scope pointer. We're going to define this in the type def. Oh. Typer. So this is going to type a program. I probably want to take in a typer or like make a new typer or something. So I'm just going to do like, I'm just going to give it a typer as a pointer. So I'm just going to, when calling this, I'm going to call it from main. I'm going to include the typer. And after the printing here, I'm going to make a blank typer object. This might be changed later. And we're going to type this program with the address of typer. This is just for having this object there. And type program. We'll first update this current scope. Or maybe it doesn't need to do that. I'm going to set it to 0. Yeah, this ends up taking the typer. So we're just zeroing out the current scope. And then we're typing a scope. if we're typing a scope, we're gonna switch the scope. So I'm gonna make some helper functions for switching a scope. I think that might be neat. Thank you for following, by the way. I'm gonna say enter scope. Typer. Enter scope needs the typer, and it needs the scope. So I'm just gonna say typer current scope equals scope. An exit scope will just say like if we're gonna assert something. We're gonna assert that typer current scope is something. Because if the scope isn't something, we can't exit it. You're gonna say typer current scope is equal to typer current scope parents, which might or might not be 0. I'm going to beg have fun you all. Thank you for watching. Thank you very much for watching. And sleep well. Can confirm that formal education quality in this industry is lacking. It is, unfortunately. Yeah. That's very sad though. Use a CPP keyword. It is, but I'm not using CPP. But I can choose a different keyword if that makes you more comfortable. I can say like declaration here, but I'm also having yeah, I'm gonna say declaration. All right. Java for most programming courses. I never tried Java. I just heard it's like laughable. I don't know. Can you separate your backend from frontend? So I can maybe use your backend. I'm separating my backend from the frontend. I'm gonna do that. So basically the backend is gonna receive the tree, either in form like a syntax tree, probably more like a, it depends, like some IR probably. I don't know if I'm gonna use IR with just linear tables, or it depends on what optimizations I want to do. Some optimizations are easier on some structures, while other are easier on other structures. But yeah, I'm gonna do that. C and C++, not a job of high level anything. Just recently got a co-op job. Anything to do with learning school? Yeah, that's right. Like, I worked in Microchip 1 year, and they didn't get my grades even. Like, they asked for it, but they didn't get it. So like, grades doesn't really matter in my opinion. Like, it doesn't matter. It's what you know, and grades really matter. If some companies are very obsessed with grades, and like how I did in my philosophy class, I'm not sure I want to work for them, because I think that's the wrong attitude. And anyway, I want to work for like smaller firms where you actually feel like you're a bigger part of the firm. I don't know. Yeah. Yes. Yeah, so this is the exit scope function. So now we can exit and enter scopes. This might be redundant. I might remove this. Parents. So when we go into a scope area, I'm going to enter the scope. enter scope, and this is going to get the typer as well. So I'm going to just propagate this typer object. Typer, and this is calling with typer. So this gets a typer, and we're going to give it the current scope. And then we're exiting the scope afterwards. All right. So we want to look up in the scope, and we're actually taking in the scope here, and that's fine. That's actually fine. So we can just use that scope variable and look up in the scope. I'm looking for this declaration name, because this declaration is going to map a identifier to an unknown type. So I need to know the identifier name. So I'm going to say declaration name, which is a string, and I'm required a string pointer, and I'm going to look up in the type list, because I'm not, yeah, there might be separate namespaces for those. Probably not. Maybe, I don't know. Maybe that makes sense. Thank you for following, guys. Hello, everybody. Are we still living in the 90s? Is that me? I'm not sure. And this is going to return a new declaration. I'm going to call this typedef declaration. So if this is something which is not 0, if this is something, I can't really just use a typedef. So if this is something, I should be able to do typedef type. So this has the mapping between this unknown type here and the actual type. So then I'm going to just replace the declaration type with this one. And we're going to assert that this type of declaration has a type. So this will not be the case if we have like structures or something else, or doing like recursive typedefs. Then this won't work. But if it's like now, with only this, that's gonna work. As long as this is known immediately, it's gonna work. Or, and this is also gonna work, in fact, if I have like I, which is gonna be typedef to U32, I can use I here, because it's the right order. But I'm not caring about that. I'm gonna catch it here anyway. But your code does. Does my code living in the 90s? I don't think so. So here we're just replacing all the declarations there. So if I'm having an unknown type name here, that's being resolved at this point here. And then, while in the same scope, we're gonna iterate over all the functions. Type the scope, it doesn't matter the order. So I'm just gonna type this. Yeah. So this iterates iterator scope variables, no functions. So I'm iterating over all the functions. And this is a declaration pointer. All right. So I want to check if this declaration is a function, which is obviously should be the case. So I'm going to just assert that this has a declaration function. If that's the case, I'm going to type this function. I'm going to make a typer for a function. And we might need to know more. The function type. I'm going to actually give it a declaration instead. Just because I can. And then we're going to say that function is equal to the address of declaration function. And we're going to do type function. And we're going to give it the typer object as well. So I'm going to give it the typer. Okay. You should write this in JavaScript. Why not Rust? I like C. I think that's the best language for me right now. So we're going to type a function. Basically, we want to iterate over this, but first we need to actually fix the scope. We need to fix the scope first. Yes, we need to fix the scope. So I'm going to type the scope here instead. I'm going to say type scope function function scope. This is yeah, we need to type this one first, which is up here. This doesn't really need any typing, so I think I will just ignore it. But I don't think we can ignore it because the parent pointer will be wrong then. Because if I start recursing into this, body, which also has a scope, which should have a scope. Yeah, compound scope. That parent will not be right. So I think I actually need to go into the current. I'm going to do an enter scope here. I'm going to enter this function scope. I'm not going to do anything with it though. Exit scope. And then I can do whatever I want here. Then I can actually do type scope, which is the function body compound scope. I think that will be right. Typer. And after this is being typed, I'm going to iterate over all the statements here. So I'm going to do type compound statement. This isn't defined yet. I'm going to define it later. I'm going to really do type statement, which will be function body, which is the statement. And I'm going to give it a typer as well. So this is going this, and now we're actually done with the type swapping here. So we're just going to go over not this kind of stuff because that's already being done. We're just going to check like test is equal to this. We just want to go into the expressions and track down if we're using any primary expressions there. If we're using a primary expression, we have to switch. We have to make sure the primary expression is pointing to some valid declarations on the current scope, if that makes sense. write this on paper. Write this on paper. Yeah, that's the 90s. This is using assembled, like just x86 assembly. But I'm gonna be able to do like binary output in case of ARM. So I think I will target ARM. I don't want to make that many backends. I'm probably gonna target ARM v7. Is that something? I think ARM v7, like 32-bit ARM. We could do 64-bit ARM, but that you can't program any chip with 64-bit. It is so hard. And the BIOS and the boot sequence, and it is like sign images and stuff like that. That's so stupid. But 32-bit ARM is very simple. And it also has some decent chips there. Like taking a quad-core A17, for example, that's going to outperform an A53, which is 64-bit, by far. So 32-bit doesn't necessarily need to be slower. And it's the same instruction set, so I'm still going to have a lot of platforms available once I'm done with this. Use a light switch to generate an electromagnetic interference which switches bits in specific location in RAM to write this code. I doesn't think that's possible. This is called Source Code Pro. It's from Microsoft or something. So you're going to be using a switch here. So you're going to switch on the statement kind. Thank you for following. And if we have statements return, we have something. Expression, we do something. And comments. We don't support comments yet. We're probably gonna do that later. This is really the only ones. I'm not gonna make a default one. So just if nothing here hits, I'm gonna print some error message. So this is typer. So just exit there. And if this is a compound statement, we're just gonna recurse down. So let's make a list node. Statements. And this compound statement just includes other statements. I'm gonna call it new statements. I can actually call it the same thing. I didn't know that. Is this going to be using this then, or this? That's in a for loop. I'm going to call it new. I don't know this. Okay, so we're iterating over all the statements, and we're just going to call type statement recursively. And it's not going to return anything. So that's the compound. Let's do a break here as well. The return statement, that's going to go and parse an expression, or type an expression. So this will type expression with statements, return statement, return expression, and a typer. And the expression statement is simpler. This will just do like expression here. The reason we have to separate those is because maybe the return statement is going to do something more. Maybe we have to check that this return statement here is actually equal to the return type of the function. So that check is going to go here. So now we need to type an expression, and we have some cases here as well. So we have an expression binary, unary, and primary. That's all for now. We're gonna also add like call expressions and dot expressions for like strict reference and stuff like that. Let's add that as well. So this is in typer, and I'm gonna say like expression is not handled. So if this is a binary expression, like I don't want to do anything with like propagating the right type up the tree. I'm not gonna do that. I'm only gonna resolve these identifiers. But I still need to recursively call these sub-expressions to get to all the identifiers, if you know what I mean. So I'm gonna type expressions of, we're gonna assert that this expression okay, so this is the same address. I'm just accessing a union member. And we're gonna assert that this binary has a left and has a right. And then we're going to type expression binary left and right. So this is recursively calling this one. For unary, let's do the same. And this is a operand. We also know what operator is going to use, but I'm just going to choose the operand here. And then we're typing the expression unary operand typer, and actually we're gonna I'm gonna do an if else there. So if primary and primary has to be either one of those. So I'm not going to handle anything, like everything. I'm just going to handle these primary identifiers, which is these like test in your code. So I can, for example, like here we have it. So return test. This is a primary identifier. I can say like 56 plus 4 minus this. And this is going to be a few binary expressions. And this is just going to recurse down here. And eventually it will come to this primary, which has the name test. So here I want to look up the identifier. So I'm going to say lookup in scope. And I'm going to look up this name here. I'm going to look up in the current scope. What is the current scope? We can get the current scope from the typer, but I also want to do like lookup in current scope. Lookup in current scope. This is gonna just take in the typer and a string pointer name and a declaration kind. And it will call this one. So current scope, name, and kind. There we go. So now I can call lookup in current scope. I'm gonna give it a typer. The name is primary name. And the kind, I'm gonna look this up in declaration variables because this is a variable. And this is gonna return a declaration. Thank you for following. Welcome to the stream. What I'm gonna call it? This is the first declaration, so I'm gonna just call it declaration. If declaration is something, we're gonna switch this. We're gonna say primary declaration equals declaration. Actually, we're gonna say that anyway. If this is equal to 0, we're gonna give a warning on this primary identifier. So you're gonna say error token primary token. So this is the primary token, which gives an indication in the file where it's at. And we're gonna say it's not declared. Thank you guys for following. It's very nice. We need the error in order to do this. Okay, so I think this is it. Yeah, I knew it's not a good word. I know, I really know. Fuck C++. I'm making the code C++ incompatible on purpose. That is totally right. We're using Visual Studio Code and not VS or C-Line. I don't know what VS are or C-Line. I think VS Code is great. Yeah, so I think this will work. We only have to consider now how we recurse down all the places. Do we parse any construct that it doesn't recurse in? And I don't think we are. So we can actually try to run this now, I think. Probably gonna get an error. Include string. Fail error. No such file or directory. Shut up. This is right here. Typer line number 4. Huh. That's weird. String.n. Is it n? It's oh. Yeah, that's right. Thank you very much. It's supposed to be an H there. That was hard to like see that. Okay, so we're using some exit function, so we need stdlib. Stdlib. And the declaration is undeclared. Line 31. This is undeclared. All right. So we're looking for a name. Okay, we're just going to do declaration here. We're actually getting the declaration kind as an input here. So let's just do this. List merge. List iterates. Do I have a lister? It still complains about the list. Iterates on line 107. List iterates. Oh, I need the iterator first. Like this. That's better. And this is an address, so statement is an object, and we need a pointer. And type expression is too few arguments. That's too few arguments. Oh, here. That's better. Implicit function declaration type scope. We need to define things on the top level here. So the type scope I'm gonna define here. I think that's the only one. But I'm gonna just declare everything. So we just have it there. And we have a type statement. We're gonna be calling these all over the place anyway, so it's nice to have them declared in one place. And if you wonder, this is why I don't like C. This is one of the reasons I don't like C. And enter scope. Okay. So now every error should be fixed here. And this is interesting. So we have a variable which is not declared. So apparently something is happening here. So we're looking for test, and it says that this variable is not declared. So it doesn't find a declaration for test, which is interesting because we're it doesn't find a declaration there. So I wonder how many times this is recursing down. Is it ever going to look up in the parent scope? It should find it in the same scope though. So this shouldn't be necessary. Okay, it doesn't find test. So test is defined here. It has the type integer. So when we parse this, we're gonna go down the rabbit hole. When we parse this, it is happening here. So we parse the declaration. And this is that is working, I think. And we can see it here as well. Declaration test. So my guess is that the lookup in scope doesn't work very well. So this is a primary expression. We're going to go into the primary expression in the typer, just see what it does. Because this is happening. Thank you for following Adam. We're going to print the name. So looking up this is primary name size. Primary name text. So this is going to print just a word. So we're looking up test, and it doesn't find it here. So the question is, why doesn't it find it? Why doesn't it find it? So look up in current scope. This is looking up in scope. And this is eventually doing a string compare between these two here. So in the string compare, I want to print what I'm string comparing. So this is happening here. Maybe this is wrong. I haven't really tested this out. So this is going to compare A with B, which is also this. std lib. So this is looking up, it's comparing test with integer. Anyway, it's comparing test with data and test with token. So where does it get those things? It is here. So the thing is that it is using the wrong scope to iterate. So when I have something declared here, because for the new ones, we're having two different scopes here. This is one scope for the parameters, and then we have one more scope here. So for some odd reason, we're not having a new scope for this compound statement. So when we enter a function, I'm typing this compound scope here. So the question remains if the function scope is equal to the function body compound scope. So I'm gonna assert that the function body compound scope is not equal to function scope. So let's see if that triggers. Okay, that is fine. I'm typing the scope. Then I'm entering the scope here. So I'm entering here. So even though I'm parsing, I just enter the function scope and then I enter the there's something crappy with the scopes here. Don't use that syntax. I have tried. I hate the Pascal syntax. It is actually kind of clean. It just depends on how you're writing the code, I think. In the same way that you can write very ugly C code, and you can write C code that actually looks good. Yeah, I've read typing the crafting interpreter. That is a good start. Namespaces, yeah, this is going to include namespaces. It makes the thing easier to parse, and it makes it more like, otherwise I have to deal with some kind of let syntax here. So let, and additionally, like how would you parse, how would you like say, if I'm gonna have a pointer to an array of int, I cannot do it like this. Because this is ugly. It shouldn't start with this. So yeah, you could do like int and some array here and then a pointer. But then you have to read it the opposite direction here. So even though it probably is a little bit to get used to, I think it's very clean. I really think so. But again, we're not gonna hard code, like, we're not gonna determine anything now. We might change stuff later. yeah, so okay, so when I'm parsing a function, I'm gonna print both scopes. So I'm gonna print the current one, which is a pointer, which is a function scope. Oops. And then we're gonna print the function body compound scope. Let's do, I'm gonna call this new. So they're different. So the question is, when I'm looking up this, what scope am I using then? So let's see what scope I'm using here. So I have to look in typer current scope. So this is using the current. I wanted to use this one, but it's still using the old one. That's why. And that's weird. Because I'm saying entering this type scope, this is gonna get a scope. And this will manipulate the pointer itself, like the address. I'm just saying that current scope is equal to scope. So here, this is typing a function. Typer current scope. I'm gonna see if that's still wrong there. What the hell? I'm doing this first, and then I'm doing, like, I should be doing this first. Okay, this doesn't make any sense at all. Like, I'm typing a function there. That's fine. Oh, wait a second. I'm typing a scope and I'm typing a statement. So this will, oh right, so this will actually exit the scope. But a scope might also contain statements. So when I'm typing a scope, I actually want to do type statement as well. So this is gonna happen inside here. And this is just a scope. Does that make sense? No, not really. So I know what the problem is. The problem is that this enters the right scope. But it leaves it here. I want it to still be in it at this point. So now I have to think like a little bit further. What happens if I, for example, have loops, or what function do I want to call on a loop body? I want to call type statement, probably. And this statement is going to, we can do this enter scope in the statement as well. I think I'm going to do that. That makes sense for me. So if I have a compound statement, I'm going to enter the scope with a typer, and this is going to be like compound scope. And then I'm exiting it here. So exit with a typer. So now I think this will work. So this is interesting because now we're printing two different trees. So let's consider this one first. Yeah, we don't consider this. The body here, is having an identifier, which is called test. And actually I want to print a little bit more. It is not going to take that a long time. When I get to an identifier, I want to check if this primary has a declaration. If this identifier has some kind of declaration, I want to print that one. Indentation minus minus. So where do we print a declaration? We doesn't really need to print a declaration. We're gonna just need to print a type. So if that has a declaration, we're gonna assert that this primary declaration has a type. And then we're gonna print type, which is primary declaration type. So if it has a type, it's gonna print it. In other words, we're getting nothing here. So test is just an identifier, and the same thing here. But if I'm right, then we should get it here. So this is cool. So the identifier is an unknown integer. So this proves that something is working, but some things are not working. So we're not replacing that integer. This is an unknown integer. But we should replace this integer with U64. So that should happen before this. And that is happening in the typer. Oops. That is happening in the typer scope. So this is gonna go over all the unknown types. So here I'm just gonna print unknown, typing unknown. I want to print its name. So I'm typing this unknown test, and this is typedefing integer to unsigned 8 bytes, and this should be like we're having this declaration here, and we're saying this type is equal to whatever's here. Is this happening? That is not happening. So we're looking at this in the scope. Because this is typing unknown, that's happening. We're typing this unknown test variable. And we're looking up in the scope. So basically we should find this test wait a second, we're typing unknown. We shouldn't look up in variables. Fuck me, we should look up in types. Of course. We should look up in types. So this is just resolving the type defs. So if I now do this, oops, types, there we go. Then it's working, but this is not happening. Then we're having declaration test is an integer. and integer is a type of which is 8 bytes. And you're looking up, you should be looking up this integer. This is unknown integer. Okay, so it's not working yet. Scope types. So this will work, assuming that that this is even happening. If this is not even happening, I think I'm pushing things to the wrong list. I'm just gonna print something. I don't really care. Okay, so this is happening once. And the type is not unknown. Declaration type kind. This is still a declaration, so I want to print this regardless. So I'm typing unknown integer. So the integer is unknown. This shouldn't be unknown. This should not be unknown. So I'm gonna assert this is actually true. That makes sense. Just gonna double check. What types do we have? We have basic pointer, inferred, unknown. Yeah. I'm gonna assert that it's not unknown. That the type it's pointing to is not unknown. And then we're gonna look up this in the scope. Anyway. So now, this should start happening, and if I now go in here, this is still an unknown thing, which is fine. So I'm comparing integer with integer. So this is really happening. We are replacing this. Unknown integer. So unknown integer, wait a second here. If the identifier is unknown up here, how does this work? Like, if this is an, yeah, okay, I get it. I get it now. So first we have to go through these, and then we have to go through all the declarations, replacing those with unknown. I was just doing the wrong thing here. Type scope. Was it actually supposed to be variables? I think it was supposed to be variables. And then you get the declaration here, which is test, which has type integer. It was right. So you're gonna print it anyway. And if declaration type is unknown, no. If the kind is unknown, you want to look up in scope, but it's looking up the wrong thing. That's the thing. This is looking up the completely wrong thing. So this is not going to look up the declaration name, because I don't want to look up this tester. I want to look up the type unknown name. So I'm asserting that this is unknown, and And then I can say declaration type unknown token name. Like this. I'm probably going to make a string first. Let's make a string name, which is equal to this. There we go. So if that is unknown, you need to know what type this is. You're gonna look up in the type scope, the typedef scope, what this is. And if that yields some kind of declaration, I'm just gonna swap the type here. So now this is still happening, and now we know this test identifier is unsigned 8 bytes. So we're actually swapping this, which means I probably can make more complicated expressions here. So even if I'm defining something without, like after the return, I want to have like an, I'm gonna call it like II. Yeah, II. I'm gonna define this as a pointer to an array of 50 pointers to char. This is the II. And then I want to have and I can't really use them there. And then I want to have a data which has a type II, which is equal to some value. I'm setting it equal to some value because then it's going to pop up in the scope here, in the diagram. So now we have a type def here. That's fine. It's just printing that. But the first one, we have a binary equal between data, which is a pointer to array of 50, which is a pointer to signed byte. Fuck yeah! That is awesome. This is working very well. So now we can actually start generating the code. We know everything we need to generate the code for this. So we're gonna be able to generate code for this. Probably not the array and stuff like that, but simple expressions like U64, it's gonna be simple. So I'm gonna delete this. So this is gonna return let's just return test here, which is an integer, which is the type def here. I'm not gonna comment anything. So generator is starting and it's having a assertion fault. Okay, I'm gonna catch up with chat. I'm making a new language, yeah. Lock the title of the stream. How do you lock the title of the stream? It's supposed to be right. I'm using the C language to build a compiler. Yeah, it's going to be available for the public to use. It's on my GitHub channel. I can give a link. If you want, I'm going to push the changes after I'm done with the stream. So it is this one here. And it's going to be specifically made for ARM. Even though I'm making an x86 assembler, that is just for making it easy to test, because I can actually run it on this computer. I'm actually going to get the previous OS I made to work, and then we can start making a backend for ARM. But then we probably need to use the ARM, like GCC non-EABI assembler. I hope that's gonna... I have to think about it. I think you can see the snippet. Pointer to int, or that's gonna work. That's a good one. Thank you. That's right. It is easy to fix. We just need to recurse into each type and resolve that. So basically, in the typer, when I'm resolving this, I'm not really going to resolve just this. I want to call a function which is resolving a type for me. resolve type. And what do we need to know here? I'm going to say resolve I only need to know the type, and we need to know the name, and we need to know the scope. And this is going to look up in the current scope. So I can just say look up in current scope here because I'm entering the scope. And if this, I need to set the declaration type equal to the type there. Okay, so I need to use a scope. Okay, I'm gonna make a function which is called resolve type. This is gonna be a static function. This is gonna return the resolve type, and it's gonna take in a type, and it's gonna take in a typer. So typer is just the object we're using for transferring, like keeping information when we're typing the tree. The type is the actual type. So we can do a switch on the type kind. We're doing it up here as well. Probably not. Or actually, we're only going to check for if the type kind equals type pointer. If this is a pointer, we're going to recurse down. So I'm gonna say return resolve type, and I'm gonna call it with the argument here. No, I'm not gonna call it with that. I'm gonna call it with type pointer 2. What the hell? 2 seconds. Hva er det du? Hæ? Hva er det du smaker på? Punkte du ikke på? What the fuck? Banket ikke du på? Nei. Det var noe som banket på ruten. Jeg gikk ikke ut her nå hvis det ikke var det. Men jeg streamer, så jeg må stikke. Det snakkes. Okay, I'm back. Someone was knocking on my window. I don't know who he was. Yeah. So I'm gonna recurse with a pointer. And I'm gonna get the same typer here. Thank you for following. Welcome to the stream. Welcome. And then we're gonna check if type kind equals type unknown. In this case, we want to do what I'm doing here. So we want to have a string name, which is equal to declaration, no, which is equal to type unknown token name. And then we're going to do the lookup here. I'm not going to call it typedef declaration. I'm going to just call it declaration. And since we're only using a type here, I'm going to assert that the declaration is valid and the type is also, it's pointing to some kind of type. I'm not going to print anything, and we can't really do this because it doesn't have the declaration. But I can return it though. So I'm going to return this declaration type. Does that work? Does it really work? Does that really work? No. So here we need to set, this is gonna say type pointer 2 equal to that. We're gonna resolve this pointer into this pointer again. And then we're gonna return the type here. So only if this is a type unknown, we're going to return something different than the type. And if nothing is happening, we're also going to return the type. So this should be able to resolve any type. Also pointers. And this is much more clean, so thank you very much for a nice suggestion. We're going to type this declaration type. And we're going to give it the typer. And we're returning this into the declaration type. This is far better. Lookup in scope. This is going to be calling lookup in current scope instead. Lookup in current scope. Takes in the typer, the name, and we're going to look up in the types, the type table. So it is doing the same thing here. It is still typing our tree, but now we can do something like pointer to something like this, and it is still going to resolve it. So up here we have a pointer to, first of all, we doesn't have it, but the actual type is pointer to an array of 34 unknown, and here it's pointer to something which is an unsigned 8 bytes. So this was a really good suggestion. Now it works. Yeah, that's right. For pointer handling, shouldn't you wrap recursive lookup in a new pointer type? Yeah, that's right. I do that. So int 64. Int is 64, superint is int. Yeah, that's another thing to handle, but that requires different passes or more logic. So I think that will work if I'm writing it in the right order. So if I'm saying I want to have like type AA of type U32, and then BB gonna be of type AA, CC is gonna be of type BB, and then int is gonna be of type CC. I think this will propagate and actually do what we want. AA is 4 bytes. No, it doesn't, because it doesn't update the actual table. So yeah, that's right, we need to handle that. But that we're not gonna do today. We're only gonna try to compile this code here. So let's make the output a little bit cleaner before we head on. So this is just printing 2 programs. And then I'm gonna generate this. I'm gonna generate assembly from this. And we already have assembly code for handling this kind of thing. We need to handle equal signs though. So the first thing we have to take a look at, how much is the clock? 1 a.m. That's fine. We're gonna keep going a little bit more. I want this to work before we head off. So I'm gonna make a diagram. Did I delete this now? That's weird. Should we just take a quick recap how I'm generating the assembly code now before going further? I think so. Let's actually do this. And I'm gonna go into the generator. I'm gonna just take some water before. There we go. Okay, this is the cool part. So what I'm doing, what I'm generating here, if I'm generating anything, I'm not. So I'm only generating this part after the equal sign. So the way it works is that I'm using some kind of a stack machine, I think. I think that's a term which is normally used. I'm really only doing one thing here, so I'm gonna make a diagram instead. So we have different registers. Maybe you're familiar with x86. I'm not, so I'm not an expert on this. But we have at least two registers called RAX and RDI. The A register and the destination index. So we're only using these two registers currently. And the assembly code is like very bad, but that is fine. And then we have some kind of stack over here. Let's make it like this. Make it easy to understand. Oops. There we go. I probably don't need anything more. Okay, so this is for just placing the values there. And this is a stack frame, or this is just a stack. And then we have something called RSP, which is the stack pointer. And then we have the RBP, which is a base pointer. We're going to be using this later, so I'm just going to hide it over here. So it's always growing downwards. So this will be pointing to the top of the stack. So there is probably something here already. So this is pointing here. So what we do when we have a new expression, for example, like binary plus, I'm first of all iterating until I'm first recursing down the tree, taking this here first. And this requires us to do 56 plus 45. So whenever I have a binary expression, like I want to do plus, let's do 1 and 2. Let's make this a little bit nicer. So I want to have, this is a multiplication. And I want to do 1 plus 2 first, and then you're going to multiply that by 3 afterwards. So this will give us like 9. 3 times 3 is 9. I don't have a register allocator. This is going to behave like a stack machine. The register allocator is going to be something I'm doing after this is working. Tree address code, turn it into SSA. Fine analysis for learning purposes. I probably will later. Like, I'm not just going to generate this code, but this is a nice starting point. Way faster than an interpreter. Yeah, that's probably right. Cool that you made a compiler though. You probably know all about this stuff, so you can just arrest me if I'm saying something wrong. But basically we're recursing down to this node here. And we're starting with a right node, which is this one. And if this is a number, which this is, we're loading this number into racks. So I'm just gonna place the number 2 here. We're loading this into racks. And then I'm gonna handle the left-hand side. So I'm pushing this to the stack first. So I'm pushing this to the stack, moving this down, and then I'm handling this left-hand side. So this is a 1, which is also moved into RAX. And then I have computed both the left and the right-hand side. So then I'm gonna pop the value at the stack pointer back into RDI. It's gonna be in here. This is moving up. And then I'm computing the binary plus between these two. And I'm saving that in RAX. So this will save 3 here. Fuck, I did it the wrong way. I actually did it the wrong way. I'm gonna just do this again. Just erase the mind. We're starting here. And we're always gonna start with the right hand side. So this is first gonna be a 3. And we're loading that into racks. And then we're pushing that before we compute the left hand side. So this is gonna be pushed to the stack. And then we compute the left hand side here. And this is a new binary expression. So we have to compute the right hand side first. Moving 2 into racks. Pushing that onto the stack. This is moving down. And then we compute the left hand side into racks. And then we have to compute a binary operation here. So this is first popping this one, the result here, back onto the RDI register. And then we compute that plus, which is 2 plus 1 is 3. And then we're here. So this is the left hand side. So then we pop the right hand side expression, which is 3, back into RDI. So this stack pointer is now pointing to 3. So this is going to be popped back into RDI, moving this, and we do the binary multiplication between this one and this one, storing it here. So that's the result of this one. If I want to have like return some kind of expression like this, it is just generate this, really, because it's always going to be in racks. And it probably would be like some jump to return, a return label or something. So that's the way I'm handling expressions right now. And now we need to set up the stack pointer. So when I'm entering a function, I need to set aside some kind of space for a stack frame, which I believe needs to be 16 byte aligned. ARM, I do think ARM needs some. I think ARM needs 8 bytes alignment on 32 bits. But we're gonna use 16 byte alignment. So basically, when I make a new function, which we're gonna do here. So when I have a new function here, for each single function, I'm gonna go through all the variables. So I'm gonna go down here, and I'm gonna look through all the declarations in all the scopes. So if this is containing some subscope or something, that's gonna be, let's actually make that so we can see what I mean. So I think we can handle like empty scopes. So if I would have made some kind of data, which is a char equal to 5. Oops. Then I will have a compound statement here, and I will have a new compound statement there. And you can see this is also a declaration. So when I'm saying we have to iterate through all the declarations in the function, we really are going to do that. So we're going to iterate through all of these declarations. And by the way, we're not checking that this doesn't already exist. So this is going to check that first. It is going to work if we're just very like careful what we're writing. But when I'm declaring this, I need to check it first. That is not already declared. Or I don't need to do that. Yeah, I don't need to do that. No, I'm declaring a variable here. So all the declarations, I need to go through all the declarations, in other words. So this one and this one. So I need to go through all the compound statements and recurse down there as well. So what I need to do, I need to save some space on the stack frame. So this is a stack pointer, and now this RBP is coming into place. So what I'm doing when I'm entering a function, I'm saying that RBP is going to have the value of RSP. So basically the base pointer is pointing here as well. And then I am reserving space for all these declarations. So let's just assume all these declarations are 64 bytes. No, 8 bytes, so 64 bits. So then we have the data here. So I'm going to assign data is offset 0. So data is going to live here at offset 0, which is really offset minus 8. So I'm going to say offset minus 8 because it's going to live here. And then we have the test variable, which is an array of, let's say this is an array of like two 64-bit numbers. So then I have to set aside these two things for the test. And this will be at offset minus 24. It will start here. And also I'm gonna check like how much are this all together. I'm gonna add all these offsets together, and I'm gonna find where the stack pointer is gonna be placed. Then I'm gonna move the stack pointer so that it points to where the stack is empty. So any variable I'm gonna refer to after that will have an offset. So I can basically just store from, I can say like minus 5 or minus 8. And I'm gonna get this one. So this is really convenient. So by looking at the declaration, so everyone here has a declaration, and I can get the offset from the declaration, which means I can actually store the variable on the stack frame. And after the function call, I'm just gonna move this up to the base pointer again and return. So that's how the variable allocation works. Is there any questions about this? Otherwise, I'm just gonna implement it. Yeah, I'm just following that. That's correct. All right. Then let's set up the stack frame. So we first need to, so each compound statements, each function creates a new stack frame. So if it has function, it's to create a new stack frame. So if I have a new compound statement inside a function, that is just going to go in the same stack frame. So therefore, I need to iterate through all these compound statements before actually going into the function, because I need to know all the declarations inside this function. Yeah, that's a good question though. Generator. So now I'm generating a program. I think we did this yesterday. And generate a code unit. We're printing the code unit. We're generating a scope. And this is the global scope. So what we have to do, we have to go through all these functions. And this is not really necessary. But I'm going to generate a function based on this list. And for each function, I'm doing this. So you can see that I'm starting by just declaring this as normal code, like the data segment or the text segment. Yeah, the text segment is more correct there. And I'm marking this function here as global. And I'm making a label here saying the same. And then we're moving RSP into RBP. We're basically saying that wherever this points, probably here, we need to push this first. We need to push this first. So we're going to push RBP. So wherever this is already pointing is going to be pushed onto the stack. Like down here someplace. It's going to be pushed onto the stack. And then you're moving the stack pointer, the current stack pointer, into RBP. You're basically moving this up here. RBP. And then we're going to set aside some space on this stack. So we need to move the stack pointer down with a predefined offset. And this offset is going to be depending on how many local variables you have. So we need to compute the offset of all the local variables. Compute local variable offsets. So I think I'm going to give it the function. I'm going to give it the function here. No, I'm not going to give it the function. I'm going to give it, yeah, I'm going to give it the function. Yeah. So this is supposed to go through all these declarations and just type them all. So we know also that the function has a function scope. This is the first scope. So I want to have a different function here. And additionally, I want to align the end address. I need to have two functions. Compute local variable offset. And this is going to compute that local variable offset on scope. Compute local variable offsets from scope. So this takes in a scope, and this is going to recurse down as well. So I might need to call it with an initial offset. Yeah, we're going to call it with a U32. We can just use the offset there. I'm going to return the offset as well. So this is supposed to return the new offset after this function has been called. This is going to recurse itself. This is going to call itself, this function here again. So what we need to do, we need to have an offset there, which is equal to compute local variable offset from scope. And the scope I'm going to compute is the function scope. And I'm going to give it the offset 0. So you're going to start at offset 0. And this offset is going to be the positive value from the top here. So this will live at offset number -8, because that's where we have to load this address from. And then I have to align the offset afterwards. So just align it with 16 bytes. Okay, so how do I find the offsets? It depends on how we're going to set up the stack frame. It doesn't really matter. But I'm going to recurse down first into all the subscopes. So we're going to iterate through all the child scopes. So we're recursing first. And then this is happening on the way up. I'm going to say new scope. is equal to list to structure. Iterator is going to be converted to a scope, and a node is a list node. And then it's going to set offset equal compute local variable offset. This is a really long name. Fuck that. Compute locals from scope. I might change that later. Oops. Compute locals from scope. It's supposed to be locals. And I'm gonna use this new, let's call this child instead. I'm gonna say just child because otherwise it's gonna be very similar to this. So child, and we're gonna use the same offset. So basically the first variable will have the highest offset. And after we have recursed, so where is this stopping? This is stopping whenever this doesn't have a list. So anywhere like the child which doesn't have further childs will terminate the recursion. So this will actually work. So now I need to subtract the offsets. I'm going to say offsets plus equal, and here I need to iterate through all these variables. So I'm going to iterate through all the variables. Each variable is a declaration. Thank you for following. Thank you. So this declaration has everything we need to know. So what I'm changing here, so the thing I'm changing here, if we're gonna access anything from this tree, this basically knows about what we're doing here. So from this data we can actually know the offsets. This is a variable because we're iterating the variables, and we have an offset variable. So first of all, we want to increment the offsets. So I'm going to say plus equal, and the declaration type, thank you. Oh, I think it's just because of the plus equal. Declaration type, which is a pointer, size. Each pointer has, each type has a size. So I'm going to increase it with a size. And should we align it first? I think we should align it first. I'm going to make a function for aligning something. Offsets is going to be aligned with type alignment, just to be safe. And then we're saying that the variable offset is equal to offsets, and this is going to be plus equal. So you're allocating space for the variable, and then you're aligning the offsets, and then you say the declaration variable offset is equal to offset, which is really not true. This is going to be a negative number. So maybe we should make this assigned S32, so it actually makes sense. I'm going to say, can I do this? Minus offset. So this is assigning all the offsets. And then I'm going to return the new offsets from this function. And that's gotten here. And then I'm going to return the stack size. So I need to align this offset by 16, because that's the stack alignment. And actually, we're going to just return that. So we need a function for aligning. No, I don't want that. How to align a number to ints. What is a different word for a number, like align? Shouldn't you put the variables in order? This is just where the variables, the address, which doesn't really matter. As long as the address is known, the order doesn't matter. The count recipe in the makefile. Oh, that's just for counting the number of lines. Like this. So as you see, we don't have that many lines. How do I do this? You're making a language? Yeah, I am. Cast. Align value C. I'm always getting like print alignments. Align pointer C. Oh, sorry. STD align. Okay, maybe it's that one. Standard align. I don't think that's going to work with runtime. Yeah, let's just do it the manual way. If number modulo alignments. So that gives some non-zero value. Let's return that. Return that. So I have like offset is equal to number modulo alignments. And we're gonna align upwards. So if this offset is something, then we're gonna return, we can just say number is equal to number minus offsets plus alignments. Is that gonna work? The std align has an align of operator in C++, but isn't that only for variable alignments, not for runtime? So if I'm, for example, getting 5 here, if I'm aligning with 6 and I'm getting 5, then this is going to be 5, which is a number. So we're doing this minus this, which is 0, plus the alignment. This is going to work. Okay, the generator is starting and we have a segmentation fault. So is that happening here? Okay, so it's starting. We have a segmentation fault. Here. It's going in there. Okay, so it's in the local scope. So this will never be 0. We probably should assert that this scope is valid. Okay, so the scope is valid. We're accessing the type though, so maybe the declaration. Assert declaration type. That's weird. Exactly where is it failing? I'm gonna say this is an iteration. We're getting it 2 times. So possibly this is happening once. Oops. So it doesn't get done here. So a scope always has some child scopes. Like it always has a valid pointer there. So I'm just not understanding why this is happening. So we're doing this, we're iterating, and whatever we get here is not valid. So the next time I'm gonna actually print the scope here, which is a pointer. So we're getting something non-zero but is not valid. Which means that the first scope doesn't have valid pointers to the child scopes. So what might that be caused by? I guess this is in the parser, and it is in the enter scope, I think. So when we enter a new scope, this is the thing we track. So this is going to add it to this child scope list. And we're setting the scope parent as well. So the parent are working because we're, or I don't know, I think the parent are working. We're adding a new scope. And a new scope initializes this list, the child scope list. And we're linking it in the previous scope child scopes. So the yes. Okay, let's print the parent here. I'm gonna print the parent pointer. So I'm gonna print the previous scope. We're getting a scope here, and that should be one of those. So FFFC, okay, let's 7FFF 29 EAC 20 C0. That isn't there. The function scope is here. So I'm generating a function. I shouldn't really do this. I should do declaration function. That worked. What the hell? Okay, so what did I have here? I just had a declaration. A declaration is the same address as a function somehow. That is very weird. But we're getting an offset, so it seems to work. Fuck that, why didn't that work? Okay, does anyone know why this doesn't work? I'm gonna try to print 2 addresses. Which is this address and this address. They should be similar, equal. And they're not. Why isn't they equal? They should be the same. Oh, I'm using a structure. Oh my god, that's a mistake. So this was right. If I have it like this, it doesn't work here, but it's gonna work now. Perfect. Stupid mistake. Does the function have the possibility to put numbers on the same alignment? It can, but it isn't really a point in doing that. Does the compiler design for language with header files? No, this is just gonna have implementation files. Maybe we're gonna make some modules on them, like API syntax, but I don't know. So I'm gonna still fix this one because I don't like it. It's better to just use function, no, declaration function, I think. So now, no. Did I delete the offset here? I should actually print the offset. Okay, so offset is 32, and that makes sense because I'm having offset is 32. I don't think we tracked pointers yet. Or this pointer is going to be 8 bytes. And then we have a char. Let's see what I'm adding. I'm adding this. Okay, so I'm adding the offset 1848. Oh, we have something here as well. So this is a char, that's 1. That's this one. And then we have a U32, a pointer, and a pointer. So this is just a pointer. So actually 32 makes sense because that's for 8. This is going to be aligned to 8 bits. So I'm going to print the size, and I'm going to print the offset as well, because each variable has an offset. I'm going to print a positive number. Wait a second. This is a size. Okay, so the first one has size 1 and offset 1, and this is because this is already aligned with 1 byte. The next one has the size 8, so this is going to be moved down to have the right alignment. And this is 4, so this is going to be aligned by 20, which is also correct. And then you do 28, which is being aligned to 32. So that's why the offset is 32. And by the way, we're also making these, the stack frame contain the arguments. So this seems to work very well. So I now know what I have to reduce this stack pointer with. So I'm gonna say, how is the syntax for sub? AT&T sub. Here we go. So this is subbing a subtract to something from EX. So we're going to be using, we're going to subtract this number from RSP, and this number being the offset. We're gonna call this the frame size. So this is able to contain everything here on. This is allocating every single variable, space for every single variable. And the declaration name we're using down here, so I'm gonna define it there. Print the offsets. Cool. And then we have to fix this. So we're going to move the base pointer into the stack pointer, and we're going to pop the base pointer from the stack, RBP. So this is undoing what we're doing here, and we're asserting that the stack level is 0, so nothing unexpected should happen there. This will be a compile language. Okay, so we're very close now. The only thing we have to do now, we're gonna make this a little bit simpler, because we don't support pointers yet. So we're gonna store this value in test, and we're gonna return test. We're not gonna have anything here. Let's see if this also works. And now we can probably see this is adding a code unit like this. Okay, I need a space there. I need a space after this. So we're compiling this code unit here, which is the file. We're making the main, and we're subtracting 16. And we only have one variable, but remember the stack always needs to be aligned with 16, especially when we're gonna do more function calls. That's why this is very important. And then we do stuff here. We're doing the plus, which is supposed to work, and then we have to handle this equal, because now I think there is some thing we're not handling. We have an error 1. I think that came from here. So this is a primary expression not handled. handled. All right, so primary expression is not handled. And this is the identifier. So when I'm getting, for example, test here. Thank you for the follow. Welcome. So we're gonna check if the primary kind equals isn't there missing? I think you're right. Thank you very much. It's you're totally right. I'm not very used to x86 assembly. So we're gonna check for this identifier. And if this is an identifier, we're gonna print we're getting an I, stands for identifier, and then we're gonna print the offset. So this is really cool, because now I should be able to do primary, declaration, and variable offsets. So just from this identifier in the code, I should be able to get the offsets. And we get the offset as -8. So if I load anything to base pointer -8, I'm gonna get a valid space, which I can store things in. So in case of an identifier, we want to store, this is really gonna read an identifier. Because this is primary. So what this is gonna do, I'm gonna place what's at this address into RAX. So first I need to load this address into RAX, and then I need to load from that address into RAX. And then we're gonna handle it a little bit differently with the binary expression. So this is generating address. We need to check if this is an assign, because then we're gonna do it differently. Thank you for following. Let's make a function for generating the address first. Or for loading the address into the register. Generate address for an expression. And then we want to load from the address racks. So I'm gonna make a function which is gonna load from racks into racks again. We're gonna load something from racks, and that's gonna take in nothing. And we're gonna emit. We want to move from this address and place the result in here. That is load from racks. So in case of this identifier, we want to generate the address first of the expression here. So I'm gonna just give it this primary expression. That's fine. We already know that this is the same as this, so I'm gonna just give it the expression. So that will place the address of the identifier into racks, or whatever. This is gonna be expanded later. And then we need to load from racks. We're just gonna call this one. This is gonna load from the address of racks, which is gonna fix into racks. So generate address. We need to check if this expression is a primary expression. And and primary kind equals primary identifier. So if this is an identifier, we're going to load the address into RAX. So we're going to use the assembly instruction LEA, which is load effective address. In ARM, this will probably just move or something. Yeah, move. So we're going to load the effective address of, we're going to have to do some kind of like -8, and then we have RAX, and we're going to load this into RAX. This is RBP, the base pointer. And we need 2 of these, and this is going to be a decimal number. And we're having the minus, so we're just going to be a decimal number. And what we're going to load is this primary declaration variable offset. We're going to assert that that's actually the case. So primary declaration variable. Yeah, that this has a variable. No, we're just gonna assert the declaration here. Okay, so this is gonna give it something like -8. So this will take this address, so it's gonna subtract -8 from the base pointer and move that effective address into RAX. So this is gonna contain the address of the base pointer, -8. And that's it. So after this function, the address is placed in RAX, and it just loads from that address. So if I'm trying to generate this, yeah, so it is first adding those together, the 45 and 56, and then it pushes this onto, it pushes this because this is the right hand side of an equal expression. And then it loads the address here into RAX, and then it moves the value RAX like here. So this is not really right because, as I said, we're going to do it differently on assign expressions. But this would have been the case if this was like a return. In fact, maybe this is the return. I don't know. I think this might be the return. So we have to track the assign case. So if we have an assign here, because then this is not going to be an expression. We're going to have a store as well. So static void store to, I'm going to say store to RAX address. So this is going to emit, it's going to move, it is going to move RDI, which contains the right hand side, and it's going to place it in RAX, the address of this one. So this parenthesis operator is basically the address, if I understood this correctly. I'm very tired now. I think we're just gonna make a new case here. So if the binary kind is equal to assign, and we're gonna return after. We're gonna generate the expression for the right hand side, and we're going to generate the address of the left-hand side. So I'm going to generate the address of the left-hand side. Left. And then I'm going to store to the Rex address. So this is going to generate an address and place that in RAX. And then we're storing whatever's at RDI there. We probably need to pop this back again first. So I'm going to do pop RDI. Pop into RDI. And then we just store this. So if I have a more complex expression in here, oh, thank you very much for subscribing. That's really kind of you. I really appreciate that. Thank you very much. Isn't there a missing, like, how will this work on system of different architectures? Like, I will have to make a new backend each single time. I will have to do that. I don't know. It is going to be very similar though. Like everything is going to be almost the same. Very cool project. Thank you very much. Thank you very much. Yeah. So this is a primary expression, you do this. Like you generate, if you have some binary expression here, that is not going to work. No, that's not going to work. So this will have to be checked first. So the typer needs to do a little bit more work. But we're generating the address of binary left, and this has to be able to be done. Or it has to be like a deref, but that's going to be handled in the address. Pop RDI. Let's try this. We have an error. Generator is starting. What kind of program do we have? Okay, so let's just check if this is working. It is adding that and pushing to Rex. And then it's loading this address into RAX, and it's popping this from RDI, and it's moving RDI to RAX. Isn't that supposed to work? And isn't that supposed to work? We're getting a different error code. Let's try to return just a number. The return doesn't work. Thank you for following. Respect the hustle. Yeah, it's a so tiny function. But this is going to work with bigger expressions as well. So you just need to nail this case here. I'm pushing Rex. No, wait a second, this is not right. Oh. I'm loading for I'm pushing rex. Okay, maybe the return expression isn't handled. I'm just using moving 4 into that. So I'm moving 4 into RAX. If I return from here, or let's do jump end. Then we have error 4. Make compiler is just going to compile whatever's in here. So here it's returning the right value. If I'm loading this does, like, okay, I know what's going on. This does simply not work because we're not returning anything. We have to support the return instruction as well. So generate the statements. We have the default case as well, which is going to print some nasty message. This isn't a generator. So generator statement is not handled. And then we're going to handle the return statements. All right, so if we have a return statement, we also need to do some more, because here we want to place the return value into RAX. So here we're going to generate an expression. Generate expression, and it is a return statement, return expression we're going to generate. And then we need to emit, we need to jump to the final thing. So we need to basically do this. So if I have a return up here, I need to go down here. So what we have to do, in the function, I need to make a label here. Make it label. So I think the usual thing for like GCC is to make like a big L, which is for label. I don't know. I think I'm just gonna call it and we're gonna say the function name. So we know that it's unique. So this is end function name. And we're gonna do the same thing. Give the name of the function here. So whenever I have to return, I just have to jump there. So jump to that label, which is end, and then we have to insert the current function name, which we do not know, so maybe I'm just going to make a global variable for that, just to make this actually work. That doesn't work. I need to know if that's the right thing. This doesn't really include anything. So I'm going to make the function declaration global. Yeah, the function declaration pointer is going to be global. And we're going to assert that that's actually valid. Assert function declaration. And we do string. Name is equal to function declaration name. Text. Okay, so the thing we have to do is just update this function declaration when we're computing a new function here. So I'm going to say function declaration equals declaration. Oops. So here we have end main, and this is wrong. Oh, we're missing an S there. We're getting error 5? That's a really good... Is it actually working now? We're jumping to end main. So this is returning 5. If I just like delete this, it's gonna return 4. Oh my god, this is working. Oh, so cool. That is so cool. I'm gonna just clean up a little bit. Let's make something more interesting here. I think this can return only between 0 and 255. But let's make a more complex expression. Let's make a few more variables as well. So data, which is a U32, is equal to... I have to use U64 all over the place because I only load a U64. I have to change this load based on the load type in order to use like U32 here. But that I'm going to do later. I'm going to only do 64, so integers there. So data is int, which is equal to 56. And by the way, let's do one more thing. Let's do one more thing. We're always typing. Yeah, let's do something cool here. Typer. Is this the entire typer? What the fuck? In type expression, I'm gonna parse the right hand side first. So the expression is gonna be typed here, and if this expression ends up being like a number, if this ends up being a number, if this ends up being a number, now we have to think. I'm gonna say the primary declaration. No, I'm gonna say that the primary, this is really an expression. So I want to do two things. In the tree, I want to add a type here. So each expression is going to have a type. I'm only going to use it one place though. So we're tracking the expression here. So expression and a typer, okay. So I'm going to give it the type U64 if this is a number. And if, let's think a bit. I want to do this. And this is infer, it doesn't have a type. We also know that if this is an infer statement, we know this is going to end up being like test equals data. It is never going to be something more complex here. In other words, here, if binary left kind is equal to binary, no, if binary left kind is equal to primary, expression primary, and binary left primary kind equals primary identifier. If this is an identifier, this should have a declaration. So then we're just going to assert that this has a declaration. Oops. We're going to assert this. And we're also going to say that binary left primary declaration type is equal to binary right type, if we know this type here. So here we're also going to assert that we know this type, which is only the case for some expressions. So if we have it as assert, we have to do something simpler. That's fine though. So assigning the type here. Else, we're going to type the expression. Alright, so this should do simple type inference. Very simple type inference. We're typing the binary right first, and if this is a primary number, or if this is just an identifier, like this won't probably work. I'm gonna make it work with numbers and identifiers. So expression type is equal to declaration type, I think. I'm just propagating this type up. Let's check. We're gonna watch this first. Type expression binary. So if this is a primary, an identifier, I don't know. Let's just ignore this for now. It doesn't really matter. It's still gonna work. Floating point exception, perfect. We're gonna use 64. We're not gonna do this. What is the fucking floating point exception here? Oh, I can't probably do this. Okay, so data is an integer, which is 56. And then we have a test variable, which is also an integer, which is equal to data minus 54. So this yields 2. And then we're going to make a new variable called int, which is equal to test plus data times 2. So this will check the precedence as well. So it will do data plus, I'm going to switch this there. So test, let's use data. So that's, let's use test here. So test is going to be 2 times 2, that's 4, plus 56, that's 60. So we're going to return variable divided by 3, which is going to yield 30. And let's just return here, just for fun. It's going to yield 2. Dang it. Return undefined reference domain. Thank you for following. I'm not a big fan of the font. I like it. It doesn't generate anything. Let's just return this. It is doing something with expecting. It's expecting something. Oh shit. Yeah, there is something wrong with the error handling. I don't know exactly where that is. So this is going to define error 2. That's because we're doing 56 minus 54. And if I do this, it should yield 30. If I don't do this. And 30! No, 20. Is that right? This is supposed to be 60 divided by 3, which is 20. So this is right. This is crazy. So I can actually compile whatever I want there. I can do like plus test minus whatever, and it's going to compile it. 38. This is really cool. This is really cool. Yeah, so what do we do? We actually let's do one final thing. Well, how much is the clock? Let's do one final thing. Let's do like super quick. I'm gonna go to bed before 3 a.m. Isn't there a missing? Yeah, that was right. It was a missing semicolon. Hello, Ravioli Bakery. Welcome to the stream. We're gonna implement one final thing. We're gonna implement print. We're gonna be able to print stuff here. So I want to link it with the standard IO. So by linking it with this, maybe we'll have to make some function here. I don't know. I'm just gonna make a print function which takes in no, that's really a lot to do. We have to implement the call, like placing things in the calling registers. I'm gonna take that for the next time, but it's very easy to add printing and stuff like that. It's very simple. So the next time we're gonna take a look at like calling functions and taking input parameters, setting up that correctly, and doing like control statements. So I'm thinking something like, I want to have simple for loops. So for I in 4 to 5, for example. This is just gonna iterate, and like if statements, it is not gonna need any parentheses. Yeah, just that kind of stuff. We're gonna implement that next time. And pointers. So loading and reading from pointers and arrays and stuff like that. But this is a really good start. I like this. And one final thing, because this is now beginning to look ugly. So what I want to do, I want to be able to place in some commenting. So I want to say returning. Does this fail now? I think it might. This is failing. Because this is being interpreted as a real token. So this doesn't really need a semicolon after it. So we have to go into the parser. And we have a note for commenting. That's a normal statement as well. So I think this will be really simple. We're going to parse a declaration or a statement. So kind of like as it is now, a comment is also a statement. So I'm just going to go in here and parse this statement. So that's a keyword. I'm going to check for a comment first. So if token kind equals token comments, we're going to make a new Oops. New comment statement. And we're going to say that if this is a comment, we're going to set the token equal to this token here. So we're going to save this token because Elixir doesn't really allocate anything. This is just like a persistent buffer. So you need to do the allocation here. So we're going to copy the token. I'm going to return the statements. So in the generator, when we generate this statement, wait a second, do we need to skip this as well? This is the current one. So I'm going to skip this. Copy token, and we're going to get the next one. That should fix it. And then we add a return. So if this is a statement comment, we're just gonna emit this, the entire line. This is emitting a new line anyway. And I'm gonna emit a new line before this as well. So the string, I'm going to say comment is equal to statements, comment token name. So you're just emitting the comment with a hashtag here. So if I now run this, it says statement not handled. And this is in the parser. So for some reason the statement isn't handled. We're probably not returning. Like this is the parser works. This is in the printer, tree printer. So this is print. If this is a print comment, we're just gonna ignore it. So print statement. So if this is a statement comment, we're just gonna break. We're not gonna print anything. So we're getting an error in the typer. The same we have to do for the typer. We're just gonna ignore it. And that's why it's very important to have these kind of things, because it's very easy to know what's wrong. Break. So now it's variable is not declared. Actually, this is helping me because I haven't declared the variable. Let's rename this to data. And this is going to give me 18. And additionally, if you go into the assembly code, we should get something interesting. So this is returning. And I'm still getting this ugly C kind of thing. So what I will do, I think there's going to be a problem with multi-line comments, but I just want to disable having this. So I'm going to go in Elixir, and we have a function for parsing this comment. Parse number, parse identifier, parse comments. So I'm basically setting this token or the name to start where the Elixir is at. What I can do, I can move this down here. I'm advancing Elixir 2 places first, skipping the 2 first slashes, and then I'm assigning this. So then I'm gonna get a nice print here. And let's do more. Let's do Let's print something here as well. Let's do something more complicated. Thank you for following, Rexer. Minus... Okay, so we're gonna say data. Let's do something more simple. So this is gonna be 560 minus 5, so it's 555. And then you do data minus 55 minus 54 minus, in parentheses, data equals 555. So this is going to be equal to 1. Since this is evaluating to 555, this is going to be equal to 1. And then you're subtracting this with 55 and 1. No, 54 plus 1, which is giving us 500. And we're just going to return this variable. Assigning variable. So we have 254. Is that right? Let's just try to return the data. Oh yeah, so we can't really, it is gonna overflow when it gets over 8 bits. So that's fine. We're not really interested in that, it's gonna work. We're interested in assembly code. So this is really nice. Move CLB, this is the division. No, this is 0 extending, because we're doing a comparison. But we have this really nice commenting. This is very cool. We have this code unit. This is so cool. I'm actually really happy. Yeah, 11 hours. It's time to go to bed then. 11 and a half hours. Yeah, we've been making good progress. We have been streaming for 2 days. So 2 days and we can compile like simple functions. We can actually do very much with this, and it's very easy to add more stuff now. This was the difficult part in the parsing. So I'm very happy. I'm gonna take a little raid. Yeah. And I'm gonna push to GitHub. I'm probably gonna be cleaning up tomorrow or something. Because I don't like the way the code is right now. It needs to be commented a little bit more. So I need to fix that. Thank you for the project. No, thank you for the, not thank you for the project. Thank you for the follow. When did you start a project? I started yesterday. So it's all on Twitch. It's like 8 hours yesterday and 11 hours now. Thank you very much, Sebis. Thank you very much. Yeah. Let's find somebody to raid. Python basics, no thank you. Game programming. C like C++. Let's find something interesting here. There is almost nobody who's programming in C. Like very few. What is this 48 hours? I see it all the time. I need to find coding streams. Game Jam. I know what that is. Ludum Dare. That didn't sound English. Probably. I'm gonna rate him. Godot. Is that a language? I'm just gonna pick one. Workshop coding in Unreal. Let's do this one. 1 year on Twitch. let's celebrate together with this guy. Godot is a game engine. All right. I didn't know that. Anyway, I'm gonna be back in like a few days. I'm gonna start streaming regularly again. So that's cool. So thank you everybody for watching, and I see you the next time.